right. Testing? Yes. So it's Wednesday and it's Siggraph. So we're at the very beginning of the Khronos BOF day, and we have a packed day of updates for you on Anari and OpenXR, Gltf, and Vulcan. So we're going to be streaming the whole day, and we look forward to some really detailed discussions following up from the fast forward that we did on Monday. So the first presentation is on the new rendering engine API called Anari, and we're honored to have Bill Sherman from NIST. So over to you, Bill.
Thanks, Neil. So as Neil said, I'm Bill Sherman from NIST. For those of you who don't know, it's the United States National Institute of Standards and Technology. And I'm here on behalf of the Anari working group. I come at Anari more from the user perspective rather than the rendering backends perspective, so I try to represent that side of things. Oh, the slides aren't up. Sometimes if I turn the USB one way or the other, it works, even though it's not supposed to have to do that. Is that oops, except that's the wrong view. There we go. We had this tested, but I unplugged and plugged back in. Mistake. Okay, very good. So, oops. Doesn't like this slide. It looks solidly connected. I can go out and back in. It doesn't like when I go to presenter mode, maybe. All right, let's try one more time here. There we go. Does it stay? No. We tested it ahead of time. It was working. It seems to, yeah. Right, yeah, okay. So I skipped one slide, so maybe that one slide is something it doesn't like, I don't know. Anyway, so here's a summary slide of Anari. As the slide says, it's basically a way to simplify application development, so you have an interface between applications and the rendering hardware, the specialized ray tracing software or rasterization software. Version 1 has just been finalized. It's pending approval of the Khronos board. But you can get it's available right now on the website. And you'll see that a lot of the application examples that we're showing today are kind of scientific visualization based. That's kind of where we started, the beachhead we started on, but of the last few months we've actually been expanding into more VFX and modeling and that kind of thing too. So it's more than scientific visualization, but some of the pictures you'll see today are kind of scientific visualization focused. So this is kind of the classic example of why we have a standard, right? Because instead of having to write all your applications for all the different rendering engines, including ones that maybe don't exist yet, we can put this API in the middle and then write your application just for that API, and then all existing backends can work. So here we already have Osprey, Radeon Pro Render, and VizRTX, as well as a couple other example ones written. Other people are writing some, just kind of get a feel for how to write a new backend. So as future backends are written, your application is kind of future-proof, and you can do a lot of testing between applications. And that's really one of the utilities of having this is you can see whether a different rendering technique produces better results or faster results without having to write your application to a lot of different rendering APIs. So here's kind of the chart broken down into a little bit more detail. Of course, everything sits on top of the hardware, the CPU and GPUs. There's a lot of acceleration APIs that have been developed in the last few years, especially since ray tracing hardware has been added to GPUs in about 2018. And then there's a lot of rendering engines that are built on those specialized APIs. So I already mentioned Osprey, Radeon Pro Render, NVIDIA's VizRTX. And so those rendering engines, a lot of them ray trace or path trace based, provide complete utility for materials, for geometry, for volumes, and then you have these applications that sit on top of it and just render to Anari. All right, so a little bit more detailed information about the SDK. So as it says, it's a front-end library. The specification is specifically C99 based, although there have been implementations for C++, of course, and also more recently there's been a Python implementation. So when you download the SDK from the repo, you'll get automatically a C++ implementation as well as a C1. I should mention that what the product of Anari is really the specification, but in order to let people jump in more quickly, we've already produced an SDK that you can download and get immediate access to. So there's a lot of example applications. As I mentioned, most of the beginning ones were scientific visualization based, but we've added Blender and Omniverse to that. There's also a conformance test suite, which makes sure that when you write a new backend, it'll be able to render, or if you want to have a new API or application sitting on top of the API, you can test that against the conformance and make sure that it's functioning properly. So when you're developing a new backend, the API, the specification doesn't require that you implement every last detail. So for example, there's different primitives that Anari can handle. Triangles, of course, but also spheres and cylinders. But if your backend is more kind of polygon, mesh-based, you can skip the spheres and cylinders and just focus on the geometry. And then Anari provides a way to inquire of the backend what features it handles. So your application can query and say, do you handle spheres? If not, then I'll just send a bunch of meshed spheres as instances. Or if it does have spheres, then it can just handle it right away and take advantage of the sphere rendering capabilities. There's also some, if you download the SDK, there's a debug layer that comes with it, a trace layer. I'll talk a little bit more about those in a few slides. Helide is a sample rendering application that comes with it, and so if both it works, so when you download and compile the SDK, you have an instant backend running. You don't have to go to a vendor and get their backend, but you can. But you have one that's instantly running, builds right with the whole package, and so you can kind of test to make sure you're up and running right away. It also comes with a source code, so you can use that if you want to develop your own backends. You can use that as an example of how to write new backends to suit your needs if you're on that side of things. And then I'll mention on a slide later that we have a user who's not part of the working group, but came to one of our webinars a year or so ago and was so excited about it that he decided to write a little back-end translator that remotely sends Anari commands and receives them back as images. And so that's kind of a nice thing that the API provides. So I mean, here's the kind of general idea of how it comes. This one breaks it down into what you do, what happens at runtime, what happens at compile time. So you have your application, it's built on C or C++. You compile that with the Anari library, which has the ability to then connect to one of many different backends. So I've already mentioned the 3 main backends that we have implemented already. Also, Radian Radian Pro Render is also one of them. Of course, if one of the things that's kind of different if you have Python, that maybe things don't get compiled right at the same time. So the Python doesn't necessarily fit the runtime compile time mode here. I mentioned there's a debug layer, so what you can do is the debug layer is a backend, but it's a backend that can then pass information on to other backends. And what it does is it looks for conformity with the API, makes sure you pass the right types. So if you have a volume, it makes sure you passed it as float 32 data, or if you have matrices, it makes sure it's 4x4 matrices. And so it checks that stuff and prints it out. Of course, it slows you down a little bit, but it helps quite a bit when you're debugging. And then it still passes the data on to the actual renderers so you can see how things look. And I found that quite useful in my own debugging. So Anari provides this kind of world description, or frame description rather, and it's kind of looks like a scene graph. Has some, I guess, conceptual differences from a scene graph, but has that kind of flavor to it. So the main thing for Anari is you're going to render a frame. The frame has a camera, a renderer, and a world. The world then has objects under it, which includes lights, includes volumes, includes surfaces. Surfaces don't have, the geometry doesn't have to be mesh geometry, it can be spheres and cylinders, as I mentioned. You can see the world can have many different instances of objects. There's a one-to-one relationship between instancing and groups, so a group can take a bunch of objects and you can then instance it, give it a transformation matrix to the instance, and move a whole group of things around, so in that way it's much like a scene graph. It shows here that everything's under an instance. You can actually put surfaces and volumes directly under the world. But one of the things you can also do is you can have multiple worlds and then kind of connect different worlds to the frame at different times. So if you want to render it different ways, you can make use, you can build this graph, build this node structure, and then disconnect and reconnect it to the frame, or for perhaps you have multiple cameras, you can disconnect the camera, put a different camera in, do a new render, but you don't have to re-specify the entire scene. It can all reside in memory. So here's 4 applications that are underway. Visit is a scientific visualization tool from Lawrence Livermore, and it's built on VTK. So of course we have VTK working in the lower right there. And so that's part of VTK right now in the GitHub repo. It's not actually part of the pre-built downloads. That's going to happen in a month or two. VMD, which is the Visualization of Molecular Dynamics, has it built in. And then there's also ParaView, which, like Visit, is built on top of VTK. The ParaView interface is not complete yet, but it's underway, and we'll have that available at some time. And as I mentioned, these were kind of our scientific visualization beachhead, and so that's where we started. But we have moved on to other applications, and those include Blender, and which the implementation right now is kind of more of a proof of concept. It actually makes use of Blender's Python scripting language, add-on language, and so the Python binding of Anari is what makes us, gives us the ability to work in Blender and do Blender rendering. Similarly, we have NVIDIA's Omniverse connected using USD to make the connection between Anari and Omniverse. So I didn't mention it, one of the other backends to Anari is a USD backend, which isn't a live renderer, but it's a translator and sends it on to Omniverse or other software. And here's a little picture of the San Miguel scene rendered with VizRTX backend using Anari. I want to talk a little bit about the history of the Anari working group. So it was launched about 3 years ago. When there was this need, Osprey was out there, VizRTX was coming, and software applications were having to decide or render or create applications for both. And so Khronos got involved, and the working group, first there was a exploratory committee. There was enough interest, and so Khronos created the working group. back in March of 2020. And then we have kind of two parallel tracks here. So we've been working on the SDK the whole time. A couple of years ago, the provisional SDK was approved by the Khronos board, and then we brought in some industrial partners to take a look and give feedback on the API. At the same time, the working group was making an implementation of the API so that there'd be things to test against, right, to make sure we're making good decisions, not just working kind of in the ether, but also to have something ready to go once the specification comes out. So Anari 1.0 is not officially approved yet, but we expect it to be approved in the very near future. So at the moment, if you download it, I think it's SDK 0.7.0, but as soon as the approval happens, we're going to rename that to version 1, and that's expected this Q3 of this year. So I mentioned that we've already developed several things. So the HELIDE backend is kind of the example one I mentioned earlier, provides both source code and a working example. You get that when you go to the Khronos group repo on GitHub and download the Anari SDK. There's also the AMD Radeon Pro Render SDK implementation of the backend available. Intel Osprey I mentioned, and the VizRTX backend also includes a VizGL one, which uses more of OpenGL backend, so it doesn't do as much of the ray tracing things, but it's a way to kind of compare ray tracing versus rasterization implementations. And then there's also the Omniverse backend, which I mentioned, which kind of works through the USD system. So once Anari 1.0 is approved, we're expecting all those to be conformant. Many have been tested already. I wanted to talk about some examples of work that's already been done by people who came in early, tested the API, gave us some feedback on how things work. So this is some work by Stefan Zalman at the University of Cologne. And so one of the things he did is he created a new back end that does adaptive mesh refinement. And so he also had a VTK one. So he could compare his rendering, his mesh refinement rendering, both in a VTK version and in his own back end, which he wrote his own renderer, which he initially wrote apart from Anari, and discovered that if he wants to compare, his rendering system with other rendering systems, both in terms of quality of look and speed, that once he discovered Anari existed, he re-implemented his library in Anari and then was able to do tests back and forth. And there's a paper on that cited at the bottom there from earlier this year. And so the data here is the life cycle of molecular clouds, which is actually clouds of molecules in the between galaxies. Another project, which I already kind of mentioned by Stefan, is that he's the one who wrote the back end, which actually takes Anari commands, sends them over a network protocol, renders them on one of the existing back ends on the other side, and then sends images back compressed using JPEG Turbo or Snappy. And so this is a way that he could use a bigger computer remotely and render it on his, or display it on his local machine quite easily. And so he implemented that out of necessity. It's still under kind of in a prototype stage, so it's not part of the default SDK if you download it, but it is available, and once it will be included once it's kind of completed. And something I personally been working on is virtual reality interfacing to Anari. And so I've done it in two different ways. I work both in a cave, which we have at NIST, but at home I have head-mounted displays. And so I've worked on two different ways to implement it. The cave way, I use FreeVR, which is my own VR library. You can see a picture of it up in the upper right. So that's being rendered. That's one of our kind of tests. Rendering worlds that's provided by John Stone, another member of the working group. And so that renders on the cave. You can walk around, kind of put your head through it, and so it's kind of really fun to have real-time ray tracing in a cave VR environment. And then on the bottom, also to have it in a head-mounted display VR environment. And so the bottom one, I used a different library called Elixir, which is from the University of Illinois. And so I render that, and I can test that on my head-mounted display. Now again, these are kind of at the prototype stage. You can't tell from the picture other than the bottom head-mounted display one looks stereo, but it's kind of actually flat rendered. The cave you can't tell because normally when you take pictures of a cave you turn stereo off, but in this case we actually haven't tested with stereo yet. And in the cave, we need to do some work to make it work on multiple screens. You can see that most of the interesting stuff is on the front screen. So still some work to do, but really makes it nice where I can test different APIs or different backends that way. So what's next? So a lot of the work that's done in the backend renderers also takes advantage of other GPU features like what you can do with OpenCL. And so right now, you can see on the left is kind of our current state of things. You have your host application, which works with OpenCL to do some computations, takes that back, and then sends it to Anari. And so our future goal is to make it so that you can actually have the send commands, instructions, information to OpenCL, and have that go directly to Anari, where you don't have to kind of have this extra transfer of data. So that's one of the ways we want to make some progress in the near future. We're also looking at ways of taking cluster systems and breaking up an image rendering so that it hits multiple computers. You get a little bit faster rendering. I should say, kind of backtrack a little bit. So for VR, of course, I want real-time rendering. We have a lot of tools where you have real-time desktop rendering, but Anari also actually lets you kind of do refined rendering where you continue to have it ray trace more and more details. And so you exit the world of real time, but you get a lot more realism. And so Anari works in both circumstances. Here you can try and work on speeding up using clusters and using the Anari API for that. Again, a future project that we're working on. We have some materials in Anari at the moment, basing it off of the Gltf PBR system, but we're also looking to see what other people want in their materials information. So one of the things we're looking at doing is adding kind of more of a shader node graph system that hasn't been implemented yet, and we're actually looking for feedback. So if people who are users of that kind of system want to try out Anari and give a feedback to the working group, that would be great. We're looking at improving the object types, as it says. So right now, like I mentioned, we do spheres, we do cylinders, plus kind of triangle meshes. But if there's some other sort of geometry that would work well or would greatly benefit, like there's a renderer that specializes in some parametric shape or something like that, those are the kind of things that are not in the API at the moment, but the API is a committee, a working group. There's a method of adding extensions before they get approved, and you can test them. And then as they mature, you can bring those extensions, and we vote on it as a committee and add it to the as future specification. We're also looking at other languages, so like, for example, Rust. The debug and trace layers work, but there are definitely ways that they can be more useful. I found a few of those while I was working on my VR work. So with that, we're looking for participation, as I mentioned. We'd like people to download it. The SDK link is on the bottom of the chart here, and the actual PDF documentation is available on the docs version. The working group, I should say, has about 10 people showing up on a weekly basis from 3 of the major silicon manufacturers, NVIDIA, Intel, and AMD. We'd love to have more. We have only a handful of kind of user people coming. I'm one of the regular users from the user side of things that comes, but we could use more input on that end as well. So we really welcome participation, and with that, if there's any questions, I'm happy to answer them. Yeah.
Hi, Bill. What is Anari replacing?
Right. So there are other examples of APIs that kind of do the same thing, but it's mostly, I don't know that there's an exact replacement for it, at the moment. Let me scroll back here. So there are, like I said, there are similar things. So you might think that maybe USD is something that's kind of like this, or Hydra is kind of like this, but really Anari is trying to be more general than those are, and also kind of integrate to those as well. So I don't know that there's really a direct thing that we're replacing. I mean, if there were, maybe it wouldn't have been a good idea to create a new standard, right? So we feel that it's kind of a new thing that the community needs in order to make this connection between applications and hardware. Yeah.
So I had just assumed that all those various rendering engines had serious incompatibilities in terms of what they support, in terms of how they support, in terms of the kind of data you have to provide, in terms of what happens. So I was curious, was that actually the case, and if so, how does Anari address that?
Right. So not all of them necessarily support some of the features like sphere rendering or cylinder rendering. That was kind of a request that came from the molecular visualization group. So I don't know whether, I know that VizRTX and VizGL do. I actually don't know whether the other backends handle that at the moment. And so the APIs, if they're more concerned with fast polygonal mesh rendering, they can ignore that for the moment. Certainly things like, I do know that like Osprey has maybe better materials handling at the moment. So if you want to more refinedly control the materials on your meshes, you would choose that backend. And as I mentioned, Anari has this querying method. So you can say, do you handle this kind of ambient radiance feature? If so, I'll send you that data. If not, then maybe I'll pop up a warning to my user saying the selected backend doesn't handle this certain thing, so it's going to affect the look.
So to feed that back, the cases where something simply can't support it, you can either like polygonize the sphere, or you can simply say, I'm sorry, if you want that feature, it's not available in the API that you want.
Right. So if you don't bother to query whether you can handle the app backend can handle spheres, you can just send the spheres, and the backend will just ignore them. Right. It's not the backend's responsibility to convert them to meshes. It's really that's on the application side of things. So that's why we have this query system, and it's then the application can decide, well, I won't bother with the spheres then, or I'll send cubes instead, since I don't want to have too many polygons in my rendering system if I'm trying to be more real time. Does that answer the question? Yeah.
Yeah, so thanks for the talk. So I was curious about, have you ever considered Anari to be used on the game development side and the game engines? Was it ever considered when coming up with the specs and the design?
Right. So that's one of our facts here. Let me see if I can scroll. So none of us in the group are game engine developers. Some of us use it. I've used game engines on VR stuff, of course. There's nothing really that precludes that. The typical issue with game engines is that they want to involve at more fine-grained level than kind of Anari is going to provide. Maybe they need more of the shader stuff that we haven't implemented yet. But certainly at a overarching level, there's no reason that game engines couldn't use Anari and then have different ways of rendering. Use different. If you're on, say, a machine that has an NVIDIA GPU, use the NVIDIA backend. But if you're on a machine that has an AMD GPU, use the GPU backend. It tends to be that game companies want to know exactly what it's going to look like regardless, right? So they may not want to go in that direction, but there's nothing that would stop them, if they want to try that.
Could you amplify a little bit more, because you're coming from the end user perspective, why, as well as giving the portability, Anari is making the programming task simpler?
Right. Well, yeah, especially for me. So I've wanted to get real-time ray tracing in my VR for decades, right? So now instead of having to learn Osprey and learn the intricacies of getting Osprey to work, or learn VizRTX and kind of the intricacies of that, the Anari API is really fairly simple, right? I can specify my polygons, give it a material, tell it where the lights are, put the camera in a certain place, which in VR I'm going to move around a lot, and so it's pretty simple. I had a slide that I'm not including today, but when I go to render, say, to VTK, I just take my normal VTK Python code or whatever, and I add 4 lines of code, and now I'm rendering real-time ray tracing at least, using VTK, and instead of the VTK normal rasterization rendering, it's just this trivial little change. I just add a few lines of code, and I'm there. And so really that simplification is what gets me, because I didn't want to have to learn, all the intricacies of how ray tracing works and all that stuff. I actually, since joining the working group, I'm learning some of that stuff, but for other people who don't want to spend that time, want to jump in right away, using this API lets you really, you know your mesh, right? It's pretty easy to manipulate your triangles, manipulate your transform matrices, and so really knowing that, putting cameras, putting lights, and you're there, right?
Okay. This is a question from our live stream. Someone's planning to use Anari for an API between Siggraph and a Vulcan render. How hard will it be to integrate OpenXR into this scenario? Is there any abstraction that requires multi-cameras or single stereo pass for one viewpoint?
Right. So let me talk about the last part first. So the cameras we have, the specification does talk about different camera models. So of course we have a simple model, we have a stereo model. Going back to what I said earlier, the backends may or may not implement the stereo model. We've also talked about having a 360 or a cube map model of camera, and again, that's up to the backends to implement that. I don't know that any backend presently implements that, so that's something you can query for and find out. With respect to going to Vulcan, we don't have any backends right now that go straight to Vulcan. I may have skipped over it, but I think it's on one of the slides where that's one of the things we want to do is kind of get to the metal maybe a little quicker, and so you can have a Vulcan rendering. And read me that first sentence again.
Planning to use Anari for an API between Siggraph and my Vulcan
Oh, yeah,
render.
Siggraph. Yeah. So depending on how complex your Siggraph is, I mean, you saw the Anari kind of tree-based node system is pretty simple, but it does allow for instancing. There are some features that I kind of wish were there, and so this is kind of a conversation going on now. So, for example, having a Siggraph where you can turn nodes on and off, right? Instances on and off. We don't presently have that feature, or to have maybe an animated node where you have several children of a node and you kind of go through them. So, kind of a true computer graphics Siggraph, which has a lot more complexity, doesn't, translates to a degree to our current node system. But I think there are some ways, you'll have to kind of do some trickery at the moment to get there. Or join the working group and encourage us to implement those features.
And for someone who could write their own highly customizable or optimized renderer, do you see any benefit of using Anari as a domain expert, or is that not your target audience?
Right. So actually, that's perfectly fits with the use case that I mentioned with Stefan. So when Stefan was working, he was writing an adaptive mesh refinement renderer, right, that does volume rendering. And so he had written this before he had discovered Anari. And so he had it working. It was running fine, but he couldn't, for kind of research purposes, he couldn't compare the rendering quality or the rendering speed very easily without having to say, then go write an Osprey version of his renderer, where he still uses adaptive mesh refinement, but now renders using Osprey versus his own volume renderer or VizRTX. And once he discovered Anari, he realized if he just puts his custom renderer as a backend to Anari, all he has to do is flip a switch and he can go back and forth. I think, did you have a question?
Has Anari been compiled with all the latest Gltf and PBR extensions?
For which?
The Gltf extensions, PBR extensions.
Oh, yeah. So, no, the Gltf integration is something that we're actually undergoing right now. We're starting with trying to get the physically based rendering part of Gltf implemented as a Anari thing so that you could write a translator, but we don't have a if you get the SDK right now, you're not going to get a Gltf.
Right. Okay.
Yep. Looks like we have another question coming.
Yep, another question from the stream. So, isn't Vulcan already cross-platform besides Apple Metal?
Sure, but Vulcan isn't. So Anari sits like several layers above Vulcan. Let me bring that slide up. So you don't have to get down to the metal. Like I said, when I'm writing my my VR examples, I still do not know Vulcan coding, right? So I can free myself from having to go down that learning path. Maybe someday I want to learn it, but at this point I don't have the time to learn Vulcan. I don't even have the time to learn necessarily like Osprey's user interface, I could learn one, I could learn Osprey, or I could learn VizRTX, but I'm not going to spend the time to learn both. And so this gives me the ability to, try one or the other. Maybe I like the lighting of one, but the other one renders faster. So if I'm doing VR, I'm going to probably go with the faster render, even if the lighting's better in the other one. But if I'm doing a desktop interface, I don't quite need the speed, so I'll maybe go for the better look, right? Vulcan just requires you to do a lot more work. And as I said, the using of the VTK, 4 lines of code, 4 lines of Python. For my cave renderer, I just had to figure out how to put the camera in the right position, render to a texture, and then put the texture on the screen. So a lot simpler programming than really learning Vulcan at a deep level. But we rely on Vulcan, right? So most of these things you're going to use Vulcan, and so we get the benefits of Vulcan down at the lower levels.
So does the simplification for the development come because you're not having to drive the low-level Vulcan or DX or Metal commands, but you're just building a model in memory? Is that
right.
the right work?
Yeah, I build a model in memory. There's a few API commands to send basically arrays of data. So I send an array of locations, right, as 3 vectors of 32-bit floats. Then I send, if I'm doing a mesh, I send an array of indices into that. Or if I'm just doing spheres, I send just all the points of the spheres with the radius, and then I send a material. I line those up with a material. So I open up a world. Bring the scene graph, the node graph. I create an Anari world. You can actually create these in different orders and link them together. So I can create a world, and I can create, say, a surface, which is a mesh, has a geometry and a material that I link together, create an instance of that, connect the instance to the world, and then those instances, I can actually have an array of instances, and then each of those can have a different 4x4 transformation matrix, so I can scale them, rotate them, what have you. And so every time you create a thing and you kind of tell Anari, I've created this, now connect it to the world. And then I connect the world to the frame, right? And then the debug layer tells me, oh, you forgot to do this, right? You forgot to connect the world to the frame. That's why you're seeing black. But yeah, it's very, limited number of commands you need to learn, and you're up and running, right? All right, looks like maybe no more questions. All right, great, thank you.
Cool, thank you, Bill. So the next stop is going to be OpenXR, and we'll start at 11, so a few minutes. Stay around for OpenXR, and we'll get going with the rest of the program. Thanks.
Cool. Thank you.
to give us a tour of the API. So over to you, Christina.
So, hi everybody, I'm Christina. As Neil said, I'm from Dimenco, which is a company based in the Netherlands, so I'm sorry my accent, anything that you guys don't understand. I will start with a little overview of what is OpenXR, what to expect from the API, and then the guys over here are going to give you later more a hands-on, practical approach. So, what was necessary OpenXR? Right now, we have a variety of platforms available for development. They range in all the capabilities for input, type of hardware, and what you can do with the platform. Right now, everything is being standardized with OpenXR, but before we have many proprietary APIs. So if you want to develop your application, you have to choose which platform that you use and then decide which API to use, how many users you want to do. You're going to have multiple paths to test. You're going to have multiple devices to test. You have to keep up with everything that is happening if you want to have a broader audience. So that was an issue that the working group decided it had to be tackled. So OpenXR defines a common API that application and engine developers can use to access XR devices and write the application only once and deploy to all the OpenXR conformant hardware. So we're making it easier for companies that don't have to maintain multiple APIs and also for developers to write only once the application and run on any conformant hardware. So what is OpenXR? We like to talk that it is divided into three specifications. So we do have the specification, stations, and API layers, and also the conformance test suite. The specification does not specify any implementation details, so the company code is still confidential. So every company can do the implementation of the specification the way they want, and nobody will know about it, so we have no problems with IP. OpenXR is also an extensible API that grows through the addition of new features. So similar to other Khronos APIs, extension may expose new OpenXR functions or modify the behavior of function existing on OpenXR. So this is usually platform-specific functions that we're talking about. So if a hardware wants to have something that will come across that the others ones doesn't have, you can still have that on OpenXR just by doing an extension for your hardware. And the OpenXR is also a layered API, which means that a user on application may insert API layers between the application and the runtime implementation. One example is when you have a hardware that may get the information from the ambient or input different than the way that is specified in the API. You can do an API layer saying, hey, I have 3 more sensors in the room that I want this information from. So we just do an API layer and that will still be OpenXR compatible. And for everything to run smoothly across all platforms, we have the conformance test suite that everyone that wants to adopt OpenXR has to pass the conformance test, so we make sure that every user and application runs the same on all hardwares. So as I was talking before, what happened before OpenXR? You wanted to develop an application. You have to choose which hardware. You had to choose which API to use. So with OpenXR, you only do it once. You see what you want to do. We decide what is the best way to do the specification on your own way. We don't decide the way for you to do it. You do it on your own terms, and then you will run on all the OpenXR conformant hardware. A little bit of history. The OpenXR group was founded in 2017. The first specification was released also on Siggraph in 2019. And since last year, we have been seeing a lot of companies deprecating their own APIs in favor of OpenXR. One example is SteamVR and Meta. So their own APIs are deprecated, which is good because they don't have to keep multiple versions, and they are also now only using OpenXR. We have a wide variety of adopters across the industry. We have headsets, and lately we have been the adoption of 3D displays. So Acer is one of our latest adopters, and Sony has planned conformance for later this year. One of our latest adopters is also ByteDance with Neo 3 and Pico 4. One thing that is nice to know for developers is that we also have an open source runtime from Monado, which helps us a lot to understand how OpenXR works and how you can do its own implementation. So what about support from engines and browsers? So Unreal, Unity, Godot, they all have been providing support for quite a good long time now. A lot of games, applications are done on that. We also have support from StereoKit, NVIDIA Omniverse Kit. And for all the browsers that use WebXR, the WebXR use OpenXR as the default backend. So I can say that we have good support among the main engines. About OpenXR games and applications, we have many applications switching from SteamVR to OpenXR support. So you can see that Light Migrate, X-Plane 12, Kuzbin, and Lady. We have also Phasmophobia and Beat Saber switching for support for OpenXR. We also have applications, big name applications like Blender, Adobe Substance 3D Modeler, and ParaView, which also provide support for OpenXR. So our community is growing. We're getting each time more adopters. Our latest release of the SDK was released in July this year, is the 1.028. We have an extension explaining more about hand tracking and interaction improvements. We have defined the pinch pose and the aim pose, which was something that was requested from the community. We also have improved support for Android-based devices. Right now, you can also compile the OpenXR SDK on macOS with Xcode. And we have new meta extensions for face tracking and virtual keyboard, which was something also requested by the community. About the conformance test suite, we still have one for 1.0.27. It was released in May this year, and we have a lot of improvements for Androids and the way that the tests are run. We have cleaner code, cleaner logs, and formatting, so it's going to be easier for you to understand what's happening. We are now also doing tests for all the Android support formats, like Vulcan, DirectX, and we enable that you can run the test without any graphics, so we have now console-only testing. So what to expect next from us, from the working group? We plan to increase the accessibility, so we're working on the input rebinding. We plan to do a UI similar to what you have on Steam Developer UI, so that way users and players can play that the way that they want, remapping all the buttons to the input planned by the OpenXR. We also plan to expand our haptic support by including vibrotactiles and PCMs. We're also working with Gltf to do controller handler models so that you know dynamically which button was pressed, and you can link menus to the buttons on your own controller. We also plan new extensions like the future extension, which will allow data to be returned at a later time. This is important for when some actions take more than one frame to be completed. And we are planning on tutorials, which I talk a little bit more here on the current funded projects. So we do have one project which aims to explain better to users and developers what is XR and how to use it. It's not available to public yet, but we plan to release it on October this year. We also have, it was open until last month, RFP for Monado for the open source improvement. So we are looking now to improve its documentation, it's all the functionality, so it'll be easier for everyone to use and understand an open source runtime for an OpenXR. And as I talked before, we are working really hard on the input rebinding UI because we do want to increase the accessibility. So what to expect next? We are working on one extension to modify the suggestion bindings, which is currently not possible, as I was talking before. So we also want to change the way that we do binding action. So also including the future and extending haptics. We also include a little bit more of spatial understanding. So we want to work with spatial anchors, a spatial entity, and a new multiple XR space. We'll also include the handler models that I talked before using Gltf. We're also working on user processing because we want to standardize how detect that a headset is being warm. That is not standardized on the engines today, so it's a little bit of hassle for OpenXR to work on that. And as I talked before, we're working really hard on the input rebinding. So where can you know more about us? We do review every week our open issues at GitHub. So here's the link for OpenXR SDK. Also, the specification for anyone that wants to start. And you can also find everything at the openxr.org. We also have a Slack channel. Please get in touch with us. Anything that you want to ask, we're always available. Thank you.
Morning, everyone. My name is Andrew Apodaca. I'm from Holotchip Corporation. Looks like this slide is
Sorry, guys.
no problem. All right. Once again, I'm Andrew Apodaca from Holotchip Corporation, and I'm joined here by Steve Winston, the VP of Software Engineering. Holotchip, a little background on us. We're a hardware software company located in Torrance, California. We specialize in various 3D display technologies. We started to work especially with light field displays in 2017 and OpenXR in 2019. We currently are involved with various contracts with Khronos, Department of Defense, various tech giants. With Khronos, we are currently involved with Vulcan, OpenCL, both development and testing, and we are actively developing our own compliant OpenXR runtime. Today I'd like to showcase the Agnostic display environment, which is a custom SDK that allows for simultaneous multi-view rendering between multiple displays. So light field displays and VR displays are our primary target since they both require multiple viewing. This would allow for a single render pipeline to be viewed by various displays. This is the Looking Glass display. Birds of a Feather 2021, we showcased that we ported Quake 2 RTX to, using our ADE, we were able to basically, oh, sorry about that. We were able to port it to allow for simultaneous rendering using the ADE, which allowed for the 3D environment to be visible from the first-person perspective of the user. So you can move your head around and the geometry in-game shifted left and right. Here's a quick overview of how the light field technology works. It allows 3D glasses-free rendering for multiple viewers. So depending on the angle that you're viewing the display, you'll see a different view of the same 3D object. Here is a quick demo of Quake 2 being rendered on the light field with my favorite feature, which is corner peeking by physically moving your head left and right. Probably not a feature that's going to be allowed in major esports events, but quite a fun one. We're happy to announce this year that the Agnostic display environment now has integration with OpenXR. So not only are we able to render to multiple viewing plane render displays like the light field or traditional 2D displays, but we're also now compliant with OpenXR. And here is a quick demo of that. So here is the mirror view from an Oculus Rift, which Steve is wearing. And we have a multiplayer session between this system and a light field display connected system over here. And you can see Steve is starting to shoot my character because I'm away from the keyboard. So here we're showcasing multiple multi-view renderers viewing the same rendered instance. And with that, I will hand things over to Steve.
So we did have a few challenges when it comes to OpenXR. Sadly, so all this is done using Vulcan. And one of the nice things about Vulcan is it gives you modern day technology capabilities such as real-time ray tracing. And that's kind of a requirement if you want to do anything along the lines of real-time light field displays, or be able to have thousands of views, which is required in order to have a lenticular light field display. And our technology utilizes that in order to also have VR work in games. So we have to work with Vulcan directly, and the OpenXR runtimes have varying degrees of support for Vulcan. Some of the runtimes will stop working if you turn on VK presentation. Some of them stop working if you utilize layers. Some of them stop working if you utilize callback function for your debugging. It's a bit of a challenge, but it's definitely doable. And Windows is the only one that has support for keyboard and mouse through context capture. That means that you actually have to, you have to do your keyboard input the old-fashioned way because there's no window to render in the operating system. So that is one of the next challenges with actually working with an older gaming system, gaming environment such as Quake 2 RTX. Poor support for Vulkan synchronization because presentation does not necessarily always exist on the runtimes. You can't rely on VK fence. And that's something that most of the older, say, Vulkan 1.0 applications would utilize before timeline semaphores. Timeline semaphores work great, though, so you have to actually port over to timeline semaphores first, make sure all that's good, and then you're able to easily work with OpenXR. As I said, poor support for validation layers. That's more Vulkan validation layers has that problem with OpenXR. However, OpenXR's validation layers work great on all of the runtimes we tested. And there's a few other things that are kind of core to Vulkan 1.0 that do not exist currently in some of the runtimes. Just that, okay. So stepping away from kind of the deep dive of working with Vulkan and OpenXR, one of the reasons and the main driving factor for wanting to utilize OpenXR, especially when working with light field display, is how do you do user input? Because mouse and keyboard are 2D by nature. And if you're going to deal with something that's a 3D display, where you don't have to have glasses, you don't have to have anything like that, the only real game in town is a user input designed for a 3D display, which is inherent to a VR environment, VR and AR environment. The nice thing about OpenXR is it does support Vulkan directly, which does give us the advanced rendering capabilities. The sad thing about it is it still is driven mostly by its support with OpenGL, which means that sometimes it will have some of the older supported context ideas versus the newer ones. So some of them are better tested than others. And if your game works in OpenGL, it'll definitely work with OpenXR. If it works with Vulkan, there's probably a little bit of work you have to do to get it to work sometimes, but it can work. So for future work, we are moving the ADE to complete integration with OpenXR in our runtime, which means that natively you'd be able to work with your OpenXR system to an application to have light field, n number of OpenXR headsets all render at the same time from a single context, even distributed through the cloud rendering system. All of it in ray tracing very easily, because that's actually the way it's built to work. The nice thing about our system is that because we're based specifically in ray tracing, there's zero cost towards adding an extra view. That means that if it costs X amount of CPU, GPU time to produce one frame for a single view, you're going to get X number of views for that same render cost. Implement support for additional types of controllers. So there we're talking about adding support for everything from the newer extensions in OpenXR, such as the hand tracking and be able to have customized SLAM and things like that through our system. Enhance UX through control modification. That one is more about being able to actually read and work with text dynamically, and the user interface with a light field display, which is actually something that's kind of an unknown, difficult thing in the industry for how to do that and actually see good text behave itself in a 3D environment. Improve game performance through platform-specific rendering. I mean, that's the same for everyone. And we are probably going to be looking at what else we could do to make this a better cleaned up environment, something that can potentially even be released. That's it. Any questions? There's a mic over here.
So what would you recommend the best way to get started in OpenXR is, right? Because there's different headsets to choose from. Obviously, like, you know, some come with peripherals, some without. You could get some secondhand. You could like try to use a simulator. I know Microsoft like has one, but you won't get the same like authentic experience like with OpenXR. So how would you recommend like going about it? Because like it can be very, very tricky, like the barrier to entry.
So I actually recommend that you sort of pick the right tool for the job. So it's hard for me to give this is the best winning headset of all time. In my personal opinion, it depends upon what you're going to be using it for. We have use cases with the military, for example, where they have use cases that need to have an AR and then VR subsystems. So we're talking about customized headsets with a waveguide to look through it. And all of that's supported through OpenXR just by creating new device drivers and work with it with the runtime. The advantage is you don't have to pick a winner. You don't have to pick any particular hardware. You just sort of write the OpenXR application itself, and it will work cross-platform. That's actually one of the best things about this entire system is that it doesn't matter what hardware you come with or what hardware you buy. It will work roughly the same way for each one of the hardware configurations.
Yeah, but I guess if you're like me and you're making a render from scratch, right? Mm-hmm. Like there needs to be some way to test it, to you know validate that everything's working the way you want. It seems like an emulator, like that's what I'm like was sort of trying to do. I wasn't just getting the results that I wanted to. I was just curious on your take on that.
Well, in that case, I would actually work with the Monado has, and actually most of the runtimes have their own emulation capabilities. The nice thing about Monado is that it works independent of most of the headsets. The Vive runtime Does work with other headsets as well. And the Oculus runtime, it works great most of the time with everything that we've run into. But headset-wise, you're pretty much open. If you're looking for something to just develop with, honestly, just pick whatever's the latest and greatest. You want to look mostly for, do you want to develop with PC in mind, desktop, or do you want to develop with Android backing it? Do you want to develop with HoloLens? So that would be a Windows running on the headset itself. It really depends upon your use case for where you want to get into it. But I would pick one and just start working with it.
Yeah, and there is a way to do it on Android. You mentioned, right?
Yes.
That's kind of cool. Okay.
Yes, you could absolutely do it manually. That's what we did here.
Okay.
This was Quake 2 RTX. That's the code that NVIDIA worked on to, I think it originally came from a Q2 Pro port of the Quake 2 code from Bethesda. So, I mean, we're talking about something that was released decades ago until NVIDIA took it on and modified it to work with ray tracing as a demonstration. There's nothing in that game that isn't also in AAA games today.
Right, gotcha.
Yeah, I was just hoping you could talk to haptics. I was excited to see that. Yeah, I was excited to see that that was scheduled coming up.
So my understanding of haptics is that it's a action system. So we're able to notify the controller that something has happened, and it will depend upon the hardware how it handles it. So some hardware will actually give you like a ability to buzz. Some hardware will give you the ability to actually feel more of a grip, that type of thing.
Yeah,
it all depends upon how the hardware did it.
Yeah, we're working with it on the Quest Pro, which is fantastic. That, like, amazing haptics, but yeah, our elation turned to disappointment when we jumped into OpenXR, unfortunately.
Yeah, the HTC, yeah, the new haptics are actually really cool, and I'm very excited for what's coming up with most of the run times with that.
Do we have any indication, like time frame?
I'm sorry?
Do we have any indication on timeline? I know it's a
I
barbed
can't speak
question.
to someone else's runtime,
All right.
unfortunately.
Thank you.
They don't consult me.
Hi, thank you for the talk. So I have a quick question, similarly related to haptics. So OpenXR mostly deals with vision, and I guess a little bit of haptics extensions as well. Looking towards the future, I guess, are we going to be touching all 5 senses? I know some devices have audio. Have Khronos ever decided a consideration of supporting extensions for audio?
So most of the time when you're working with spatial systems, the number one thing you're going to want to look at is some form of an HRTF audio rendering system. And by that, I mean that it's a head reference transform function, be able to actually place audio around the head in some location. If you haven't heard that, by the way, there's plenty of demos on YouTube that will show you being able to auditorially hear getting a haircut. You'll actually hear the razor go all the way around you. So spatial audio is something that is a extension, I believe, in OpenXR already. And there are other ways to work with audio directly if you wish to push it further.
Thank you very much. You talked about the looking glass and those 3D displays. Is there anything particular you need to keep in mind when you want your application to run on that kind of hardware? Because obviously it needs a lot of computing, and also it's a completely different medium, like when you say you can take a VR viewport and just distill it down to the desktop?
Yes, so the main thing, the way that that works, we'll see if I can't go back to that slide here. So this is a lenticular display, and that means it has some form of optics sitting on front of a display driver being a monitor, right? So you still have your regular pixels, and every time that there's an optic that is in front of that pixel, you could actually think of it the same way as having the lenses in a VR system. We have to distort that lens using barrel distortion and things like that, but all that goes away, thankfully, from OpenXR handling that for you. It just gives you the projection matrix and you're done. In this case, you have to worry about there being anywhere from 45 views if you just have left-right horizontal parallax, or you could have horizontal plus vertical parallax. In order to do that, you have to increase the number of views by a very large margin, up to thousands of views. And when I say thousands of views, I'm talking about this is why you can't work with it with OpenGL or with standard rasterization pipeline, because multi-view only supports up to 16 views on any graphics card I've ever seen. So in order to do that in real time, you have to move over towards ray tracing. And one of the things that we implement with that ray tracing is the ability to have any number of views at the same time. So in the exact same frame, you could render out those 45 views or 1,000 views or however many you need to have, and have that be defined for the actual display itself.
Okay, thank you.
Mm-hmm.
Going back to the devices that you were talking about for OpenGL, so I don't have a Microsoft HoloLens, but I do have a Windows MR headset. Mm-hmm. Does OpenGL support that for the Unity software? That's a great question for Unity and for the runtime developers. Okay. However, it would be my expectation that it does support it. Okay. Because OpenGL's standard rasterization pipeline, it is a deprecated API. Okay. However, that does not mean it doesn't work. And it works very well. It's very well supported in all the runtimes. Okay, thank you.
Coming back to the slide, so how far sort of abstracted is the fact that you need 2, 4, 8, or 100,000 views from the application? Does the application need to know that when it uses the OpenXR pipeline? Or is there an abstraction layer that sort of hides the fact how many views are needed? One of the nicer things about the setup in OpenXR is that it will define the form factor of the device you're working with. And that form factor will actually give you the view definition for each of the views. An extension that we are working on that's unique to the HoloChip runtime that we are going to be trying to push into OpenXR itself is to have n number of views instead of the current version, which only has support for up to 4, I believe. Is there any plans for support for non-coplanar multi-view displays, like a cave or a table or something like that? Yes, that is actually part of why the ADE exists and our runtime. We do have support for that. Okay. You could define a view to be literally anywhere. Thank you. Okay, well, thank you very much.
Okay, thank you, everyone. So we're going to take a quick break. By popular request, we're going to do a repeat of the Anari presentation at noon. So if you're interested in Anari, hang around for a few minutes and we'll cover that, and then we'll get on to the Gltf and Vulcan later in the afternoon. Thanks. You ready? Sure. All right, welcome everyone. So it's 12 o'clock, so we're at the next session here at the Khronos BOF at Siggraph 2023. And we're going to do a deep dive into the newly announced Anari rendering engine API. And we're very honored to have Bill Sherman here from NIST. So over to you, Bill.
All right, thank you, Neil. As Neil said, I'm from NIST, which is the U.S. National Institute of Standards and Technology, and I'm here on behalf of the Anari Working Group. I'm more of on the application side of Anari, whereas many of the members of the group are part of it's kind of the back-end development, and I'll talk a little bit more about that later. So this slide gives some examples of different ways, different rendering techniques you can apply to the same data set. So as you can tell, this is the same data set, but sometimes we have ambient occlusion, sometimes we have directional lighting with shadows, sometimes we have self-shadowing. And so depending on what your goal is, you may want some or different techniques to be applied to your data set, especially in scientific visualization, but also in VFX and things like that. So let me talk a little bit about the goals of Anari. So we are not officially launched as a 1.0 version. We expect that to happen in the near future, but we're anticipating that things are kind of solid for 1.0 right now, and that it'll be approved in Q3 of this year. So, but the goal really of Anari is to be the simplified application development layer, so that if you want to make a new application and you want to take advantage of advanced rendering techniques, ray tracing, path tracing, what have you, you don't have to learn or take someone else's library and write a specific interface to their library. You can write one interface and connect to a lot of different back-end renderers. So we want this application portability. That's kind of what this is all about, right? So on that first slide, we talked about visualization examples, and a lot of the examples you'll see today are from the visualization realm, but that was really just kind of where we started, and in the recent past, we've been moving on to other areas of rendering. So this is kind of the classic standards need, and you'll see a lot of Khronos APIs use the same thing, where we had at the beginning several different applications, which all, if they wanted to use a different renderer, had to write their own interface to that renderer's API. And so with Anari, we stick in a simplified API level in between, and now your application can select at runtime which rendering style or which rendering code you want to access. And so that's really the big win that we're going for here. So another way of looking at that in a more detailed level is that Anari sits just below the application layer and above all the kind of complex things that happen. If we go all the way down to the bottom, we have hardware, the CPU or GPUs, and then with modern GPUs, which 5 years or so ago introduced ray tracing capabilities right at the GPU level. And so a lot of acceleration APIs depend on that, or do some rasterization, making use of the GPUs. Several of them are listed here. But then on top of that layer, a lot of especially ray tracing applications have taken advantage of these new GPUs. So Intel has their Osprey, AMD has the Radeon Pro Render, and NVIDIA has VizRTX, and VizRTX 2 now. And so if you want to take advantage of any of those, Anari lets you link to them, and implementations of all those already exist. There we go. All right, so some more kind of diving down a little bit into the details. The specification is written for C99. That way it kind of has this broad application. It doesn't preclude us from moving on to kind of more new languages like C++, right? So there's a C++ implementation that already exists. It has wrappers, makes sure everything is type safe and what have you. Within the last year, we've added a Python binding, which is really still kind of at the prototype level, but it basically takes all the features of Python, especially the NumPy side of things. If you're doing more scientific work, have lots of data, you can use Python and Anari to link to these other backends. And then there's several example applications. If you download the basic Anari SDK, you'll get a tool called Anari Viewer, which just lets you try out different different test suites on different rendering applications. And then recently we've added a conformance test suite to test all the backends and make sure that they match the Anari API. And that's also based on Python. So there's several backend layers that exist. When you download the SDK, I'll talk a little bit more about this later, but there's one called Helide, which comes built in, and it's really just a test renderer so that you have something to go with once you download the SDK. But there are also other, from the specific vendors, you can download their specific backends to Anari. And so those are on separate repositories controlled by each vendor or whoever writes the backend. But along with the standard SDK, and I should actually, let me point out at this point that Anari itself is really just the specification, right? It's just a document that this is how the API is specified. But to get the community growing faster, we've already implemented the basic SDK for C, C++, Python, also several backends that are already going. So the SDK is not really officially what Anari is, but we provide that to get everybody joining the community and going more quickly. So one of the things that comes with this SDK that we've implemented are two extra backends. One's called the debug, one's called the trace. So the debug does things like, say, make sure that you've provided this right type when you specified an array of values, right? And so it'll print that out, and then it will pass through. There's a diagram that's coming later where you see that it'll pass through to the other libraries. And the trace one does kind of more advanced, more additional tracing of the debug. The Helide, I mentioned already, that's a sample implementation of the back end. So in addition to doing some rendering, the code is there. So if you want to write your own back end, you have this example code to work from. It's not the most advanced rendering system. It's there to be, kind of a clean code example for you to look at and build your own from there. So you can learn how to adopt your own to the SDK. And then I'll talk a little bit more about this later, but one of the things that we're adding to the SDK now is a third-party user who joined Anari, not as a member of the working group, but kind of as part of the community, and he implemented a remote rendering system that we can now provide with the Anari SDK. We'll talk more about that later. So one of the side benefits of Anari than having these backend libraries is that they can be connected in at runtime, right? They're just plugins. They're shared object libraries, DLLs on Windows, that can be connected at runtime. So you compile your C or C++ application, you link that with Anari all at compile time and loading time, linking time, and then when you run it, you can specify which of these backends you want it to run with. And so I think probably it's a little more flexible even if you're using the Python, because then the application doesn't even have a compile time, right? So here it is with that debug layer added in. So the debug later also gets added at runtime, and you can see it's a pass-through, right? So it's going to add some output to your console or to a window or what have you, and you can use that, as I said earlier, to make sure that your calls to the API are in the right order. You didn't try to create a scene, but you hadn't created the device yet, things like that. You have to make sure some of that stuff happens in the right order. So the debug layer checks that for you. Some of the backends will handle errors, right? And so this can be a problem if you're always testing with one backend and everything's working fine, but then you go to run on another backend and something's broken, because some of them are more forgiving than others. And I've discovered this a few times where I've written things like, oh, it's working great, try it with somebody else to see how that improves the rendering, and then you get a blank screen. So it's like, well, something went wrong. But no, the bug was in my code. I just didn't know it because I was using a forgiving backend. So I hesitate to call this a scene graph, but it's kind of this node-based, right, system of how the data is stored in memory. At the top, we have a frame, and the frame then has the world, which is where the geometry is going to reside, along with the lights. And then you have a renderer, which is a particular part of the back end. So actually, a back end can have more than one rendering style. You can do path tracing or ray tracing, and those can all be part of the same back end, and you can select those then at runtime which one you want to do. So you select the renderer. All renderers or all backends are required to have a renderer called default. So if you want, you can just select the default and you'll get that. And then you have the camera, of course, so you can choose which direction to render to. The world then has objects below it, including lights. We can render surfaces or volumes, and I'll I may have a slide that talks about it later, but I'll mention now that backends, to be conformant, do not actually have to do everything. So, for example, we can have different kinds of surfaces. We can have triangle mesh surfaces. We can have parametric spheres or cylinders. And a backend can say, well, I'm just going to do spheres, or I'm just going to do meshes, right? And there's a query system where your application can query the backend and say, are you going to provide me with the ability to render spheres, or should I convert all my meshes into spheres, right? Or just ignore spheres, however the application wants to handle it. So the API says, you know, there's the opportunity for triangles, there's the opportunity for spheres, but the back end actually gets to make the call as to whether whoever implemented it wants to go that far. Now, of course, if you don't implement very much, no one's going to use your back end unless it's something specific you're trying to accomplish. You can create objects and instance them, so that's kind of standard scene graph. But there are other aspects of scene graphs like switches or animated nodes that we don't handle. That what you would have to kind of do on your own. You can do some of that through the instancing node. So here's some of the applications. I mentioned earlier that we started with scientific visualization, so that's where we are here. VTK is kind of the low-level visualization rendering system, and that is written so that it's in the Kitware GitHub repo now. It is not part of what you would download right away. You would have to get a certain branch, but in a near future release of VTK, it'll be in the master pre-compiled branch. So VTK is used by both Visit and ParaView. So if you want to use Visit and have Anari in it, you have to get a special version of the VTK. But this is all just temporary, right, as we're releasing things now. But Visit has an implementation then based on VTK. ParaView also based on VTK. We're not quite releasing that yet. The interface isn't quite finished for that. So at kind of release time now, Visit works, VTK works, and also VMD works, the visualization of molecular dynamics tool from the University of Illinois. And so that one works, and that's one of the ones actually that wanted spheres and cylinders because, you know, as you're familiar with, a lot of times molecules are modeled that way, although this representation is more of a ray tracing of potential fields rather than that. But if you want to go back to ball and stick models, those are right there in the API. All right. So as I mentioned, though, scientific visualization was really just where we began. We've now been expanding into the modeling and FX areas. So we have a proof of concept version working in Blender right now that takes advantage of both our Python language binding for Anari, but also the fact that Blender uses Python in its add-on system. And so that the two combined lets us work with Anari right now in Blender. So that will actually work. There's another backend that I haven't mentioned that actually the backend renders to USD, right? And so once you have it in USD, you can then bring it to other things like Omniverse and manipulate things right there. So there's this link to the FX world and the metaverse world through that as well. Here's another example of where we've rendered a scene, the San Miguel scene using VizRTX. And so just a non-science one, but you can see you get a lot of the self-shadowing, the soft shadows from the harsh sunlight, but distant sunlight. So kind of a nice scene that we can render as well as the scientific visualization. So I want to talk a little bit about the timeline of Anari. We have kind of two tracks I'm going to talk about. So an exploratory committee for Anari was formed back in 2020. Based on the fact that, you know, a year or two earlier, a lot of advances had happened in the GPU hardware realm. And so there were a lot of new APIs coming out to take advantage of doing rendering or ray trace rendering on the GPU. And so the exploratory committee formed and worked on a specification, right? So that's, like I said before, that's our real product of Anari, is the specification itself. And so we had a provisional specification that came out almost 2 years ago. At the same time, in order to make sure that we're on the right path, we've been implementing the specification ourselves, and so we've had several iterations of that. Right now we're calling the implementation version 0.7. As soon as the final specification comes out, we're going to renumber that to 1.0. There will be, if there's any changes, they will be minor between the two. So if you download it now, you'll probably get 0.7.0, but you'll really be working with the equivalent of the 1.0 branch. And so the specification we're expecting to go to the Khronos board in the very near future, and we expect it to pass in Q3, depending on what feedback there was. Between the provisional and today, though, we released it to the public, so we got feedback from several groups. That's why we added some features like the spheres and the cylinders. Other things have happened. Some of the third-party stuff I'm going to talk about later happened because we released it. We did a little webinar, and so we had people interested in that. So, as I said, you can get it today. There's an Anari SDK, which is, again, not the official product, but exists and has all the samples, has the library, has the HELIDE open source example rendering library. And then, as I mentioned, you have to go to other people's GitHub repositories or wherever they have it to get the Radeon, the AMD Radeon Pro Render, or the Intel Osprey, or the NVIDIA RTX, Viz RTX, or the Omniverse implementation, the USD Omniverse implementation. And so these will all be conformant, officially conformant, once the spec is approved. All right, so one of a third-party examples, so Stefan Zellman from the University of Cologne came to our webinar from a year or so ago and was excited about Anari. So he had already written his own specialized render that did adaptive mesh refinement. He was writing that and had wanted to be able to compare it, right? So he's doing academic research. He wants to compare both the rendering quality and the time to render. And in order to compare that with, say, Osprey or Viz RTX, he decided that once he discovered Anari, he could write an Anari implementation, API implementation of his renderer. So he basically wrote his own back end. And now, at runtime, he can just switch which back end he uses. He can do timing analysis. He can kind of look at visual quality, however he analyzes that. And then he also, now that the VTK product was out, he could also compare using VTK of the same data. So this is really one example of where the big win comes from using Anari, right? So you don't have to write your renderer and then go and figure out how to get your same data into somebody else's renderer once you're using the Anari API. So there's a paper about that was published earlier this year. I mentioned at the beginning the ability to do distributed rendering. So Stefan is the same person who, when he was working on his back end, he wanted to be able to render on one big machine, but display it where he was working, at his office somewhere else. And so he went and made a new back end that sent the Anari commands to kind of a receiver, front end, I guess you'd call it maybe, receiving end, do the rendering there, and then send images back as compressed using JPEG Turbo or Snappy, so to get good feedback. And so that's going to come. We're actually going to include that in the Anari SDK that gets released. So that'll be one thing that the community has already contributed. And another user example is myself. So I mentioned at the beginning, I'm more on the user side of things rather than the rendering research side of things. And my area of work is doing virtual reality and specifically scientific visualization in virtual reality. So I've implemented both a cave style and a head-mounted display style implementation based on Anari. One of the kind of, holy grails of virtual reality has been to take ray tracing, make it real time, and put it into VR. And so in the past, there have been efforts to do that, some more successful than others, but now we've made it fairly easy to do. So for the cave, I use my free VR library, and we see that running in the upper right picture. There are some issues still, so you'll notice the rendering is all happening on the front screen there. We're still working on making things work better on multiple screens. And then the lower right one is on the Elixir library, which is an open source, open hardware platform that from the University of Illinois, a group that I've been working with. In the very near future, we'll do OpenXR. We just had the OpenXR session, so probably before the end of the year, we'll have an OpenXR implementation as well. But we're still working on things like the API specifies that you can have a regular camera, you can have a stereo camera, you can even have a 360 or cube map camera. But as I mentioned at the beginning, backends don't have to implement everything that's in the specification. You query to see if they do. So I don't know, I'm pretty sure none of our backends yet handle cube map cameras. I don't know whether any of them do stereo yet, so I don't think any of them do. So we still have to work on that. Right now I'd have to render the scene by changing the camera position and to get my stereo effect. But with a stereo camera, I can query the back end, say, hey, do you just provide a stereo camera? If you do, I'll do that. Oops. If you don't, I'll just have to render twice, right, and cut my frame rate. And so we also need to do the multi-threading, which I mentioned for the cave. So that's where we kind of the near future, things we're working on. In the slightly more distant future, things that are coming next is to integrate with more libraries, especially Khronos libraries like OpenCL. And so one of the things that if we're using OpenCL in an application now, the application has to kind of go out, do the OpenCL work, bring that data back, and then ship it back to Anari. We'd like to make that so we don't have to be shipping the data quite so much. So we want to integrate other libraries more seamlessly into Anari. Another area we're working on is to be able to do cluster rendering, right? So that we can send part of the scene to different CPUs or GPUs and have part of the scene rendered and then bring it all together at the end. And also distributed rendering. So we already actually have taken a step in that direction thanks to Stefan's work. So that's one of the things coming up. And then finally, we're looking at expanding how our materials work. So right now, we've taken the lead from Gltf and its physically based rendering, and we've integrated that as part of the standard. And I'll reiterate, not all backends necessarily handle that, right? You have to query to see if that comes in. But we know that people are doing other things with shaders and shader node graphs where they're going to want more flexibility in their material shading, material rendering. And so for that, we're actually looking for input from the community as to what's the kind of going method of doing that. What's the best method of doing that? And so we welcome new members to join our working group and give your input. You know, try things out, give input, show us how things work or don't work. I should mention that our working group right now is about 10 to 12 people arriving, attending meetings on a regular basis. We meet Wednesdays at 2 o'clock Eastern time, so 11 o'clock Pacific time. Is that right? No, it's 1 o'clock Eastern time, 10 o'clock Pacific time. And we have people from Europe as well. We don't have anybody from Asia attending on a regular basis, but we do have people from Europe attending, so a little later for them. And of the people attending those meetings, most of them work for the GPU manufacturers. I'm one of the few that show up that come from the application side, so if there's more people who are on the application side, we'd really welcome your input and encourage you to join. So I mentioned already that, you know, cameras, we already have a couple camera modes in the API. We'd like to see them in the back ends, of course. And we'd like to get a lot more for kind of visual FX people to participate so we can really make sure that we're heading down the right path when we add materials, properties, and things like that. We're going to, you know, further things we can do is add more languages. Like I mentioned, we recently added Python. So Rust, other languages, and then our debug and trace layers that I mentioned, there's still some room for improvement in those, so those will be improving over the next few months. So I just kind of said this, get involved, right? That last URL will get you the SDK. You can clone it from GitHub, compile it, it uses CMake, so build it from that. The docs, though, is what is really the product that we have, right, the specification, so you can also get that. And then we have an Anari page off the main Khronos page. And so that concludes the talk. If there's any questions, I'd be happy to take those. Looks like we got one coming. All right. Yes, sir.
Yeah, so when it comes to like the shader, like the pipeline, I know that there's like configurable stages. It can be quite complex. So how does Anari like handle like the different like pipeline configurations, I guess?
Right. So that's something we still have to work on. You can manipulate the world once you have it, and then you do a render, right? So you can continue to manipulate that. Right now, I feel like more of the burden would be on the application to make sure that that happens. But this is where, people with more expertise than at least I have on shading side of things would have to tell us what's the best way to put that in the API and make it happen.
Okay, because like a backend, like how do you implement a backend without like an actual like shader pipeline? They've got to work hand in hand.
Right.
Basically.
So I guess we'd have to come up with some sort of protocol, right, that lets you specify the shader pipeline and then ship that to the back end.
Okay, gotcha.
We took a lot of questions at the earlier session, and Neil has a new one.
So probably the closest comparison API out there is Hydra, which is part of the USD ecosystem. Do you want to compare and contrast the two?
Right, that's actually an area where I'm not so good, but we have a FAQ that our spec leader, our group leader has put together. So let me see, he has something on that. Yes. So I'm going to paraphrase. So Hydra is USD specific, right? So, it's basically taking source code data. I'm just going to read actually what he says. Siggraph source data into a form that the renderer can directly consume. And so the details differ quite a bit. Anari is basically the most similar to the API one could use to do a single render delegate. So he's saying, so the answer then is Anari isn't trying to do the data transformations, right? You have to handle that all in the API. So Anari has this very simple layer API. You provide it the geometry, the materials, the lights, the cameras, and the back end has to handle everything else, whereas I guess Hydra is going to do more data manipulation based on what the needs are of the renderer. Does that answer your question, Neil? Thankfully, Jeff provided me an answer to that. But.
Yeah, and I think obviously Anari is separate to the USD ecosystem.
Right. So Anari can render to USD, and then you can pass it on to the Hydra system from there.
Yeah. Can you go into more detail about like the scene graph? Because I'm really curious, like what's the best like scene graph structure if you're going to make a custom engine. I don't know if it can include like something like motion, like animation. I don't know if that's like part of Anari. So that's something I'm working on.
Yeah, very good question.
Yeah.
So one of the things you can do is take advantage of this instance node, right? So you can have your objects, whatever they are, and then instance them. You might have one copy of an object or multiple copies. With the instance node, you can give it a 4x4 matrix, and so you can put any copy of the object anywhere you want, scale it. So I don't have any videos here, but one of the things I've been playing with in my VR stuff is manipulating that. And so every frame, I can change the scale of an object or move it or twist it. If you want to do other things for scene graphs, like maybe have a switch where things turn on and off, or you have an animated object and you just kind of cycle through it, or you have level of detail. That's one of the things we're actually discussing right now is whether to put a switch on the instance where we can just turn it on and off, or, worst comes to worst, you could give a bad matrix, right, as your transformation matrix and make the object disappear because it can't be rendered.
Right.
So that's what we can do so far. That's a couple of scene graph kind of things that you can do using the instancing. Do you have any other scene graph things in mind?
Right, I guess. So on the back end with the instance, I'm guessing you're doing like instance draw calls.
Right.
Right. Like, I've never done that. Like, how important and how like memory efficient is doing like instancing versus like just bypassing it and just like doing straight up like draws, I guess.
Right. Yeah. So it's obviously memory more efficient memory-wise. I don't know that it's going to be more efficient rendering-wise necessarily, unless the back end kind of analyzes that, knows that it's going to do all these instancing, like the Performery library used to do. It used to put things in a certain reorder things in order to be more efficient. That's really a back-end job. So if a back-end wants to be more efficient and do those kind of things, then it can do that. If you just had a bunch of spheres or something, then you can just give that array of spheres and have a matrix for each one of those, or a location for each one of those. Does that answer your question?
I guess so. Like I was like curious, like what are the benefits of like going with instancing versus like without? I guess something like general.
Right. I feel like instancing makes it easier to manipulate objects that are basically rigid bodies. Right.
Okay.
If you have a mesh that's more deformable, then you're going to have to go down and edit things down in this geometry node of the tree.
Right.
And I have not tried that to see how well that works. I do know that just moving objects around as if they're rigid bodies or stretchable bodies, because you could scale them, works pretty well.
Okay.
All right, looks like we're good. Yep.
All right, thank you, Bill. And we're going to have a few minutes break, and at 1 we're going to start the deep dive into GLTF. So please hang around, and we'll start the afternoon with GLTF. Thanks.
I feel like I left out some things that I said the first time.
Okay, let's get going. Welcome, everyone. Thank you for making the trek down that very long corridor. This is the start of the Khronos BOF day in the afternoon on the Wednesday of Siggraph 2023. And watch out, because Gltf is in town. We have a 2-hour session where we have a number of speakers that are going to give us a deep dive into a number of different aspects on Gltf. And we're going to start out with Alexei from Meta, who's the chair of the 3D Formats Working Group. So over to Alexei.
Hi, everyone. And yes. Oh. So yeah, we'll do the short overview of the current Gltf state. Okay. Yeah. So Gltf is part of 3D Formats Working Group, and you can see on the slide what we're doing. In general, it's a Gltf spec itself, which includes PBR. And the new extensions, they're actively in development nowadays. Interactivity, composition, KTX, physics, geospatial tooling, and tutorials. Some of them will be covered later today really deep, so I will not touch them in my topic. So, oh, sorry, missed this. So what is Gltf? Gltf, it's a spec for file format, which intended to be in transmission effectively format to provide the information between authoring tooling and actual viewers on the different platforms. The goal for Gltf open standard actually just not innovate on pervasive deployment or, innovate on pervasive deployment of proven technology. That we are not inventing the wheel. We're just like taking the best from industry, distill it to the best representation, and provide this as the spec. And this is precise specification, and we provide the open source tooling for multiple vendors consistency as well. By Gltf, we enable cloud, desktop, and mobile development. So we pretty much platform agnostic. It's a pure file format. We don't mandate any runtime behavior for anything. We heavily optimize for runtime and use cases. So that means most of the data directly maps to the internal representation for GPU. And we want to be cooperative between the DCC tools and the authoring formats and this last mile format. As you can see on this image, basically that's how we think our spot for Gltf is. Also, last year we were approved as the ISO IEC JCC1 standard. Okay. So the goals of adoption. We picture Gltf as JPEG of 3D. That means we distill only necessary information to be effective for the final runtime viewers. Again, it's a completely platform agnostic and pervasive as much as possible. But we are not 3D format for the models anymore. We are format for 3D assets. That means it includes the other property, including audio, physics, and possible in the future something like anchoring, haptics, etc. We'll just describe the properties of the general 3D assets, virtual 3D assets. We picture our adoption as we have the Gltf core spec. That means each runtime should respect the core spec and implement all the features. And we have the extensions that you can extend your functionality for particular use cases. And on top of this, you can build your experiences. So this is a work in progress for us. Several extensions are already in the ratification process. Some of them really close to be ratified. And so basically that's the list that you can see what we are doing at this moment. KTX is another big direction for 3D formats working group. KTX, it's a hardware-independent compression format that allows you to compress texture information as much as efficient as possible, and then be able to transcode it to the final hardware texture format on flight. With this extension, you'll be able to reduce significantly memory impact for your assets, but still preserve hardware efficiency for the GPUs. One of the actively developing extension is a physics. We want to provide platform-agnostic way to describe the physical properties of the objects, be completely physics engine detail independent, and the current goal is provide two extensions, which one is will provide the collision information that can be used for different purposes, even outside the physics implementation. And the other one, it's an actual rigid body implementation that includes the motions, rigid bodies itself, joints, filters, etc. Oops. Another significant direction for us is geospatial. We signed the liaison with the Open Geospatial Consortium. We are working on the geospatial industry needs and finding the way to provide the way to extend the large data set support in Gltf. It includes several extensions that I listed before, as the GPU instancing and mesh compression. Includes point clouds as well, and we working on hierarchy OLOD extension. And this is slide basically our vision for Gltf tomorrow, how we picture it. Some of the extensions are already in progress. Some of them such as anchors and haptics, they planned for the future. The really important part of our collaboration with inside the Metaverse Standards Forum is be able to be interoperable with the USD format. And we spend a lot of effort to find the way how we can interchange the data between USD and Gltf to close the gaps between authoring tool and delivering format and be friendly for any different experience for the metaverse. We spend a lot of effort working on the education and the videos and tutorials. We implement several open source projects. We produce a lot of videos to educate how to use different formats, including Gltf, KTX, how to optimize your assets. Yeah, please take a look on our website and YouTube channel. And we definitely here to hear your ideas, what we are missing in Gltf and what you want to see in the future. And this is our short-term roadmap. Next incoming extensions, most likely the first spec for behaviors, that will cover it later today. Also audio and physics. Also we have PBR incoming, but Ed will cover this soon. Again, if you have any ideas what we have to put here, please let us know. And that's pretty much it. I have Dan Fried, who is the chair of 3D Commerce Working Group. He's next. I have no idea how it works. Honestly, it's just like that.
This button. Oh, that's quite low down. Hello, my name is Daniel Frith. I work at Avatar as Vice President of 3D, and I'm Chair of 3D Commerce and Vice Chair of 3D Formats. Today I'm going to take you a little bit through how to level up 3D commerce and where we are in regards to e-commerce and Gltf and everything. This button does not work. Okay. Right, okay. I'm just going to lean across here and press this button. Oh no, there we go. Right, sorry. So the Khronos ecosystem has different segmentations. There's multiple Khronos standards that are all relevant to developers with similar requirements. But today I'm going to focus on the pervasive 3D segment, which is where Gltf and 3D Commerce and WebGL and KTX all reside. And this is to do with like how Gltf is used in that section. Oh, where am I going? Spacebar. Thanks. So the Gltf ecosystem, just to give you a summary of what this is, we've got Gltf in the middle. There's a whole load of different types of experience that use Gltf as the core and support Gltf. Then you've got different commerce companies, like such as the ones at the bottom there. And we have lots of creation tools as well, which go with that. And then, of course, you can also download assets and discover Gltf files and PBRs and everything from other platforms like Sketchfab, TurboSquid, etc. So, but today, just down the bottom here is more where 3D Commerce resides, and I'm going to tell you a little bit about how 3D Commerce and Gltf work together. But before I do that, there should be a little video here that kind of gives you an overview of the kind of things we do. There is no audio, no. There was a bit of music. I can hum. So we have, obviously, Gltf and PBR are used a lot in virtual reality. And then, of course, a lot of e-commerce retail companies such as Target use 3D, well, Gltf and PBR. And then, of course, those assets are viewable in AR. If you take the watches here, done by Bremont, then, you know, IKEA, you've got, I don't know, the majority of the content in IKEA now is available in 3D, and Gltf is the primary format for that. We've got different planners that use Gltf and PBR. And then, of course, you know, this is the core of a lot of these companies and how they're working and how they're getting assets together to make them usable. Configuration and switching between different PBRs, different Gltf files. Bed configurator that we did at Avatar, and then there's different interactions as well, and Gerald's going to go through that a little bit with you later. And then, of course, you've got things like different underwear, but Ventana did this great thing here for Diesel where they could like customize and see it in AR as well, and install clothing there, and more AR and VR examples for you. Actually, I'm going to move on. So the point is that there's a hell of a lot of industry support for Gltf and 3D Commerce. A lot of companies already support Gltf, and Gltf is actually becoming stronger and stronger and more prevalent and very much pervasive in the e-commerce industry, where a lot of companies are basically relying on Gltf to be the standardized way of working. So just to take you through something on that video should be playing, but it's not. Okay. So for example, with Target, you can go on their website, you can click on a lot of their product, you can see 3D representations of those assets in there, and of course you can often see those in AR. And like IKEA, as I said before, I've been doing it for years, and then a lot of the assets there. And we've seen a huge amount of conversion and retainment on websites when people are using 3D as their way forward, because it gives customers a sense of, hey, I can move it around, look at the back, look at the sides. And it's a very important way of connecting in the current way, you know, and especially with the new demographic who are much more technical savvy. We take the word, oh, okay, these videos don't like playing today. And then, for example, you can get like a really high resolution, high definition on a lot of these assets. And Gltf is a really good way of like bringing out really nice shaders, different extensions. There's a PBR presentation by Ed in a moment, which he'll go through quite a lot of the different extensions we're doing in PBR. And the way e-commerce works and the way 3D Commerce works is that we're looking at the business needs and the use cases and how we meet customers and how we build experiences for customers. And then we're taking those findings to 3D formats and PBR and interactivity and saying, you know, hey, we really need this. And then the idea is that we then build an ecosystem with Gltf at the core and the center, but the business is going to need these assets in this way. If you take like the work with OpenUSD, for example, right now, you know, how does that implement? How do we work with that? How does Gltf fit into this ecosystem? So, but from 3D Commerce perspective, we've got a business need that we need to fulfill to convert more customers. So I mean, another example here is like bed configurators. There was a huge conversion rate here with Sleep Number, where suddenly customers be able to configure and actually put heat mapping on these beds. Made a huge difference to their traction, made a huge difference to their revenue, and actually it meant that some companies are seeing, actually, if I go to the next one here, oh, actually, no, I'll come to it in a second. But like with Ventana, this enabled Diesel to be able to represent their products in another way through AR, so you can actually see it in your space. I mean, it didn't have virtual try-on, but at least, you know, you're actually able to see the product and go and zoom in up close to it. And so one of the most important things about Gltf and PBR is that it's creating that consistency in that color so that you know that when you receive that product in real life, the physical to digital consistency is always there. So this is what I was going to come to. So the work Epigraph did with Ace Hardware, which I presented and went through the other day, they saw a 405% increase in revenue on a lot of their products when they were using 3D assets, and they saw a 500% increase in people staying online, which is pretty impressive. It would make a massive difference. And I think the thing to emphasize is that Ace Hardware as a company are fundamentally a hardware company, silly thing to say, but the point being is that they've not really been in the 3D space before. So suddenly to have 3D as their way of working hugely changed a lot of things, a lot of their customers, and it also meant they attached to a lot of different demographics. I haven't got the AR footage in here, but you can then put these toolboxes that they've done into your garage and adjust them. You can customize them, and you can actually see them in place. And then virtual try-on as well, where that Gltf files and, again, shaders and putting these different Nike trainers on. I think this was using Snaps Tech, and then putting these assets onto your feet. You know, it's really helping people connect and sort of say, I can see how this is going to work on me. This is my kind of product. You know, it makes a huge difference in that kind of physical to digital presence. And then I've got also here like footage of Wayfair's room planner. So this is an interesting case because obviously you've got a lot of multi-SKU items and it's all about resolution. You've got to keep the resolution up, but there's a lot of assets in that room and you can keep adding to it, and it's keeping it efficient. And this is where Gltf is really good because it's an efficient transmission format. So building these assets in Gltf and having a central core of assets of Gltf files means that Wayfair can then put these assets and lower resolution versions of into these planners. And then this was something that was done in IKEA a while back, and it was a VR experience where actually you could configure rooms and build a whole like VR experience and actually put places and change wallpaper and change different products, put pictures on and everything else. And again, that transmission speed of Gltf and the VR experience and actually being able to put multi-items together in there, the Gltf was the only way to go with PBR. So again, I've already mentioned this, but the importance of standardization is getting as close to the real thing as possible. And Gltf is a really good way of doing that. It's probably the best way of doing it because it's going to allow, we've seen an e-commerce conversion, online duration. Oh yeah, and I didn't really emphasize it, but Epigraph with Ace Hardware, they saw a massive reduction in returns because it meant that customers were getting exactly what they saw online. So when they were ordering it, testing it out in AR, and seeing it, moving it around, they had a massive reduction in returns, which is fantastic. And then, obviously, load time. You can't always guarantee that someone's got a decent device, and you can't always guarantee someone's got a decent bandwidth. So Gltf, and what we do is a really good way of transmitting information. It's very efficient because it's based on the JSON format, and it's like minimizing the size of 3D assets and the runtime processing, which is great. And then, of course, the use of standardized file formats is providing consistent experiences, like all the examples I've just shown you. It's very important that those photographs or those physical products look like that in real life when you get that digital version, even if it's in VR or MR or it's in a web browser or it's on your mobile browser. And then, of course, it's important to have, in regards to physics and scene composition and interactivity, when you compare that to original 2D image techniques, 3D is giving people that kind of really feeling of like something tactile. They can actually see it moving, they can see it interacting, you can actually do stuff with it. While a static image, you don't get that sense. It's really hard as well to get a sense of size and scale as well. And then one more thing was like, I've written here metaverse and wearable AR, because there is a new demographic coming. I've referred to it a couple of times, but my dad still can't get his head around AR, but my 9-year-old daughter can. So there's like a whole new demographic coming that understands technology, understands mobile, understands what these things mean. And as headsets become more available and they become more affordable and they become more accessible to everybody, 3D is going to become the way of communicating your product, full stop. And then just lastly on this part, there's the viewer certification program that we run in 3D Commerce, where if you've got your own engine and you get it certified by Khronos, we can test the GLTF files. There's a load of descriptions, specifications that help you do that. And the great thing about this is that we've seen companies who get the viewer certification program, they get actually other customers coming to them saying, hey, we know your engine's going to be guaranteed that the physical product's going to match the digital product, and they're going to get those really good experiences. So to a little bit about what's next, and under development and exploration, Patrick's going to take you through the skeletal facial work that we've been doing, which is really cool. I won't go into that too much detail. Patrick will do that. We've got asset creation guidelines. We need to continue the work we've been doing there already. There came up a question, I think it was yesterday or day before, about how do we create consistency of asset creation. So we need to continue the work we do there. And we've got scene composition. I mean, Alexi mentioned it earlier. We're now looking at how you build multi-SKU items in GLTF and bring multi-items in together. And obviously from a 3D commerce perspective, that's really important to us. How do we bring multiple items into a scene, configure them, but still keep it efficient? And also we want to bring interactivity and physics into that if we can as well. The viewer certification program, we continue to evolve that, we continue to develop that because of course things change. There's more, like I said, about headsets, that's becoming more readily available. And as we see that evolving, we need to make sure that the viewer certification program can attach to those other wearables as well. Interoperable tools and standards. We already developed things like the GLTF asset validator and the sample viewer, and there's lots of different tools that we develop where you can check your GLTF files, you can check the validity of how good they are. It really helps if you throw a GLTF file through those, because then you can evaluate how efficient they are, whether there's any problems, because there can often be bad scaling issues, for example, in a model, which you don't necessarily see. Tutorials, guides, and videos. We're doing more of those, which is great. We've got more coming towards the end of this year, and we'll be continuing that work we do there, where we're also going to get maybe one-on-one interviews or going to get companies to explain end-to-ends. We're going to get people who work in commerce and formats to actually do more tutorials and take you through a step-by-step guide on how to do things, like download a GLTF file or sign a PBR. Like Eric did some great presentations yesterday about iridescence, and it's those kind of things we're going to continue to do. We've been looking at generative AI in 3D and neural radiance fields and AI machine learning. It's still quite developmental, but it's something that is happening. It's something that's happening more and more. People are talking about AI and machine learning in 3D and how does that attach to what we do. It's still quite early, but it's something we're keeping a close eye on. And then lastly, industry involvement. So in 3D commerce, we'd really like to get more industries involved. We've got a lot of retail companies, a lot of companies involved in 3D commerce and Khronos, but we'd actually like to get more insights from apparel, automotive, architecture, gaming, because they're all using GLTF, but it would be really good for them to contribute to what we're doing in the 3D Formats Working Group and 3D Commerce. I think, oh yeah, so if you want to be involved, if you want to know more about what we do, here's some links, and you can have a look at that and then see more about what we do. And then now I'll hand it over to Patrick.
Thanks, Dan. As Dan mentioned, my name is Patrick Hadley. I'm on the AR product team at Snapchat. I'm also a chair in the skeletal and facial anchoring on the 3D commerce. We just want to do a quick introduction on some of the work we've been doing on body anchors, as well as virtual try-on in the Khronos group. So before Snapchat, I actually was working at Amazon back in the early days when they were just starting into the 3D space, and we tried to get some 3D models from other suppliers, other brands and partners, and it really was a challenge because we had our own material library, texture library. There was a lot of other challenges that was just there to make it interoperable, very challenging. PBR and GLTF really did change that. It made it very easy to kind of have interoperable products that are focused on furniture, so you can have a consistent, high-quality product each time, and then you had to just worry about the lighting environment and how you represented it. But really, a lot of GLTF so far has been focused on the product itself. And it makes sense because if you're going to place the product in the room, something like furniture, there's really just a few choices that you'd have. So if it's on the floor, you put it on the bottom center as the pivot point. If it's on the wall, you put it on the back center. On the ceiling, it's the top center. But as we move to more complex interactions, specifically with the human body, those don't always work. At Snap, we've been taking in 3D models of glasses, footwear, different stuff we have virtual try-on for. And if it's on the bottom center, some of them will be in the center of the object. There's really no standard right now. And what happens is people have to manually adjust the transforms to fit it onto the face. If you have different size glasses, you can't have a single transform. We tried to have single transforms. So there really was a problem in the industry of that interoperability for that 3D to human body interaction that we saw. We worked, one of them we announced earlier this year. It was with Amazon. We brought in 7,000 of their assets and worked a little bit on this same problem. So we took this to a Khronos 3D Commerce to solve this challenge for the industry and see what we could do to generate some standards for interoperability. If you look, a couple things, it's just like the placement. It doesn't look that bad with the glasses, but it definitely throws off. Like if you're trying to make a purchase, it's very an emotional purchase, so it doesn't necessarily look good. Or with the shoes, if it's not fitting correctly or if you have clipping on the sides. So our goal with the working group was to really develop a standard or a format, a framework that would be consistent as well as kind of an optimal best fit. It was easy to use for 3D artists and for people to understand, and it allows for automation, really no kind of manual touch required to bring in an asset and make it work for your system. I'm going to run through these pretty quickly, but there is, a shameless plug. We have our 1 hour session tomorrow. I think it's 11 to 12 over at the main building that goes deep into the body anchoring. But for example, for footwear, if you wanted to place it and have no clipping or minimal clipping and bring an occluder in, we defined 6 points, actually 7 points within the shoe. One would be on the kind of the sole heel for the placement, and then around we typically get a lot of clipping that happens around the ankle, especially if it's like a photogrammetry capture, and in the front on the sides of the shoe. So defining these as a new GLTF extension that has standard naming and standard points will allow anybody to take a shoe, kind of interchange it within different brands, different social platforms, and you would be able to place it kind of with confidence, automatable every time for a scaled number of assets. Like I said, I'm going to run through these pretty quick because I only have 10 minutes. The next one we focused on was eyewear. This one we actually had 3 points for the anchoring. One would be on the nose bridge. The other 2 would be on the top of the ears. The reason we don't have 3 on the shoe is because the planes, the X or the Y and Z planes kind of help with the orientation. But for eyewear, if it's flat, you could get the eyewear kind of pointing down lower at the bottom of your ear. So we wanted to have that positioning of the angle of the eyewear with the others. And then we saw some clipping in that other one around kind of the bottom of the cheek and the occluder. The next area that we wanted to focus in on was the wrist. We've had some watch try on and bracelet as well. They're similar idea here with one extra item. If you see in the green, we now have something called an attachment, which is a fixed attachment. But you have the anchoring, which is where the placement would be. Then you have a few points kind of for the fitting and the clipping, which would be around the edges. And then the idea would be if you wanted to do almost a true to size watch face, if you're purchasing a watch, you kind of care about how big the watch face is. You don't want to necessarily scale that up or down as you scale the rest of the 3D model. So we were actually recommending breaking out the face of the watch separate from the band and then having the attachment points so that you can scale the band to the user's wrist, but the watch face could stay the same. This would be kind of an optional add-on as a body, GLTF extension that could be used for use cases, or it could be, ignored if you didn't need to have the true to size face. And then similar for ring, again, you can be a size 10 ring, you can be a size 5 ring. You shouldn't scale the diamond up on the ring as you're scaling the product. It's kind of misleading to the shopper. So similar idea, you've got kind of one anchor for the placement, that would be in the center. You've got the collision around the sides to help with the positioning and the fitting. And then you've got that fixed attachment up at the setting at the top of the ring. I'm going to step away for a few minutes, but I'll be back for the Q&A. So if anybody has any questions around any of these, I went through them very quickly. Happy to answer. But what's the next steps? First off, we're going to actually propose this, as formal GLTF extensions in GitHub and have the review to get it ratified. We'll give updates, when that as that progresses, and then we'll also be looking at dev tools to help. For people that have 3D models that have already been built, how can you kind of automatically place these, like this would be an example with the shoe to help with the placement of these attachment and anchor points. And then we're not done with just these 4. This is, just the start, and we want to kind of continue to almost everything that could be within the body. Apparel would be a major one, so that's going to be one that we'll probably focus on next, but then we also have earrings, necklaces, and something like a purse. You can have a surface placement, but we would want to kind of look at how do you kind of have that same model be for a body try-on as well as that surface try-on. So that's it from me. I'm going to turn it over to Ed, I think is next. Thank you.
All right, thank you. So my name is Ed Mackey. I'm currently the chair of the PBR TSG group within Khronos. It's a group devoted to advancing and modernizing the state of PBR and GLTF, and I'm here with Henrik from Autodesk. He is an expert in Material X and several different PBR systems, and so we're going to explain how development is going in PBR. You may know we started with the release of GLTF 2.0 back in the year 2017. We started with a very simplistic, by today's standards, metal roughness workflow. We had ambient occlusion, we have a normal map, emission, that sort of thing. But pretty quickly it started to become apparent that, at least in that first publication in that year, we hadn't specified the math maybe completely precisely, and it was starting to look already dated by 2020. So in 2020, we formed the PBR TSG. It's a group that's split off from the main 3D formats working group with the mission of really nailing down and modernizing and maturing our definition of PBR. We were helped a lot by one of our members, Dassault Systems, and their enterprise PBR team. They essentially wrote a new mathematical definition of that core metallic roughness material model that we were using and made it much more specific. And we also released various extensions to that model that year, clear coat, sheen, and transmission. And then in the following year, we did a few more things. One of the things that's not shown on this slide is that back in 2017, we also had another extension, which was a specular glossy extension, but it was a whole different material model. It replaced the metallic roughness core workflow with something completely different, with diffuse and specular and glossy. So in 2021, we deprecated that, we archived that, and we introduced a new specular extension that integrated the specular channel as a new input into the existing core metallic roughness material. So now we don't have two separate PBR materials, now we just have the core metal roughness material, and we have these GLTF extensions that sort of add on to that single material. Some of the other interesting stuff we did that year was the index of refraction and volume. I'm going to try a live demo, if I may. We'll see how a live demo goes. This is our, oh yeah, can I, all right. We'll see how well optical mouse works on glass. Yeah, optical mouse is not going to work on glass. Oh, I'm not on the right one. I'll get it. Yeah, it was on the right monitor earlier. Sorry about that. There we go. All right, so this is the GLTF sample viewer. You may have seen this online. It is, that was not what I wanted to do. Let me just push that right back down. This is rendering in real time in WebGL. And this particular model is from Wayfair. Thanks, Eric, for contributing this sample model to us. The lid of this olive jar is using our transmissive volumetric glass material. And if you look particularly at these 3 olives right here, by the way, the olives are apparently sold separately from Wayfair. They don't come with this dish. But if you look at these 3 olives, the glass is sort of distorting them where the lip hits it. And then also, if you look even at the background, you can see this red column here is full of straight lines, but when the glass comes in front, you may see the red line distort. And if you've played with rendering engines before, you know this is not something that simple alpha blending is going to do for you. There's no ray tracing here, it's just WebGL. We're actually rendering, in this case, all the opaque objects to a texture, and then the transmissive object is doing a texture lookup into that opaque scene and is able to distort it like that. Let's see if I can get back to my presentation. So that's an approximation, right? That's not the way a path tracer would do it. That's an approximation that we have for a real-time rasterizer. Gltf does not tell you you need to use that particular approximation or any other approximation. Gltf just tells you what the material is made of. And if you want to path trace it for real, you can do that. If you want to run a wacky JavaScript approximation and get it done quick, you can do that too. I'm going to come back to that topic in just a minute, but first, let's finish out my timeline. Last year, we had a couple more extensions released. We had emissive strength that gives things cool glowing colors, which is fun, and we had iridescence. That's another Wayfair sample model there. It's a lamp with a very, very thin film layer on it that has sort of a rainbow shine to it. And that actually comes from the interference of light reflecting off the top and bottom of a layer that's so thin that it's as thin as the wavelength of the light. And it's creating those rainbow patterns, which is pretty cool. So this year, just 2 weeks ago, I think, we ratified our anisotropy extension. It's our newest PBR extension. It specifies for the first time that the roughness of a material in Gltf does not need to be the same in all directions. The roughness can be higher in a particular direction than another, and that changes the way the reflections work. So across the bottom row here, you see a sort of a brushed metal lamp, and you can create that brushed look even just with a simple base color and a normal map, but the reflections aren't right. The reflections are just sort of blobby. And what you really want for a brushed metal is you want the reflections to organize into those columns. And that's what this extension is doing for us. This is the parameterization. You know, the next PBR standard over can show you their own slide with their own parameterization of anisotropy, but what I would like you to understand more so than the details of this parameterization is the process by which we got here. We have a group within Khronos. We have these different members, and they were looking at all of our drafts, right? So we had Mike from Adobe. He's a developer on the Adobe Substance Stager team, and on his work machine he had like a dev build of Stager, and he was trying out the different drafts that we were proposing for this and seeing how well they worked in the Adobe product and showing us like sample renders from his dev build of the Adobe product. And at the same time, we had Emmett from Google was wanting this for his model viewer tag, and so he was prototyping it in 3JS and showing us how it looked in 3JS. And Gary from the Babylon team at Microsoft was showing us how this looked in Babylon. So we have these different needs. We have the real-time WebGL, make it run fast on a little battery-operated GPU type crowd wanting this to go quick. And we also have the real path tracers, you know, the Dassault Systems Enterprise PBR team, the Adobe Stager team who wanted like the perfect path traced, you know, beautifulness and not the quickie approximations. So, whoops, wrong button. So this is one of our available approximations for anisotropy. This is how 3JS and Babylon.js are currently doing it. And it's, they actually got it done without creating a performance hit by avoiding any extra texture lookups. Normally, if you want to blur in a particular direction, you need many more texture samples in your shader, and that hurts performance. We found after much experimenting that we could essentially just stretch the IBL and get a pretty good approximation. And in fact, if you look the top rows, it looks very similar to path trace renders that we have, where stretching is almost the same as blurring. The bottommost row here is with no anisotropy at all, so that row is the same too. But the second from bottom row, you can see where this approximation breaks down, especially on the sphere on the left side. You can see there's a building visible in the IBL in that environment image-based lighting that has been stretched instead of blurred in a particular direction. So some of the real-time frameworks decide that, okay, well, that one little spot there is broken, but I still need to render fast on a mobile phone or in a VR headset, so I'm going to accept that little bit of breakage on that one sphere and just go fast. And then we have other products like the path tracers that say, no, we're just rendering this perfect, and we're not going to use this approximation. So with Gltf, we don't tell you how to render. We tell you what the thing is made of, right? We pick our PBR parameters to tell you that if this Gltf asset were a real thing in the real world, this is what its physical properties would be. And if you need to render it quick, we may offer an optional side texture map like ambient occlusion or thickness that says if you're going quick and making these fast approximations, you can have this helper texture map, but you don't need to use that in a path tracer because you know what the real properties of this thing are, and you can decide, your rendering engine can decide for itself what rendering strategy it's going to take. Be it the long-winded, make it look absolutely perfect versus get it done quick. And that's all done with the same Gltf asset. And this is part of what sets our definition of PBR apart from some others, is that we are not saying, okay, well, the artist gave you a node graph with 1,000 nodes, and each of those nodes specifies some particular piece of math, and you need to follow all that math if you want this thing to render. We don't do that. We say, here's what the material is, and you get to decide how much approximations or not you're going to take on your way of rendering it there. Up next on our roadmap is subsurface scattering and diffuse transmission. This has been probably on the back burner for a while, but it's going to come to the foreground here pretty quickly. If you're an expert in this, please join Khronos and talk to us about it, because we'd love to have you on the calls. And yeah, with that, I'm going to hand it over to Henrik, and he's going to tell you about Material X and relationships with other PBR.
Thanks, Ed. Yeah, so as Ed mentioned, I'm from Autodesk. I've been involved in the Gltf PBR working group since we started about 4 years ago, and I'm also involved in some of the other material-related initiatives like Material X, Open PBR, Standard Surface, and so on. So one thing that comes up pretty frequently is, how does Gltf PBR relates to all these other things I hear about, like OSL, MDL, Material X, Open PBR, and so on. So I'm just going to quickly try to explain how it relates to some of these other initiatives. So hopefully it was clear from Ed's description, but the Gltf PBR model is an Uber shader model. So it's based on the same principles as some of these other common Uber shaders, like Adobe Standard Material, Autodesk Standard Surface, Blender Principle, Dassault Enterprise PBR, USD Preview Surface, and a few others. And that's a different approach compared to, let's say, the shading languages like in OSL or MDL, where you can basically create your own shading model from small building blocks. Whereas in the Uber shader case, you have a fixed material model. And there are several advantages with that. It's much more artist-friendly and intuitive to use. And as Dan explained earlier, that's really a key to get adoption for across multiple different industries in creating materials. And it turns out that it's expressive enough for the vast majority of materials that you will need in practice, so you don't have to go to the length of creating your own specialized shading model. And it also, like Ed described, makes it very portable. You can scale from like high-end offline to various real-time targets, and since you have a full understanding of the complete shading model, you can make informed approximations. Whereas if you just get an arbitrary, shading graph of various different nodes, it's hard to reason about and make good calls in how you would approximate that for a real-time environment. And if you want to know more about how these different shading models compare to each other and what parameters map and how they might differ in between the different Uber shaders, Ben Houston has an excellent spreadsheet that kind of breaks down all the common models, and you can scan the QR code there. So yeah, that's a highly recommended resource. So one question we got early on when we started this work is like, why? Okay, there are a few popular PBR Uber shaders out there. Why wouldn't we just adopt one of those for the GLTF work? But they weren't widely supported across different vendors, different tools, and especially real-time engines. There was like no consensus in how to implement some of these effects that you saw earlier, in a practical way. Because again, going back to the earlier talks, the consistency that a product looks the same in all the different viewers and different browsers, different engines is really key for some use cases. So we did go with this incremental approach through various extensions. And while the extensions themselves are based on physical properties and not tied to any particular implementation, we needed to make sure that it is practical to implement it today in real-time engines. So for each extension, we have multiple different real-time engines supporting it before we ratify an extension. And the way we tackle that in the timeline that Ed described earlier was, which extensions would, or which phenomena of materials would provide a lot of value and also are mature. There is a common understanding on how to parameterize them and how to implement them in both real-time and offline renderers. So that's why we started with clear coat and those effects that were would bring a lot of value, but also relatively straightforward to agree on the parameterization and implementation. Whereas subsurface scattering is still on the backlog because there's more discussion needed before we can kind of nail that down. But I should say that all these other popular PBR models were used as a basis when we defined these extensions. So if you author assets in any of these common models, they very easily map to GLTF PBR. So you can easily publish them for downstream workflows, and vice versa. If you have an asset in GLTF, you could map it to these models if you have other workflows where you need to do more editing or flexible workflows. So another popular open standard around materials is Material X, but there's a significant difference here. Material X is not specifying a PBR model in itself. It's this flexible graph-based system to describe both patterns, so texturing or parameters, and also a way to express various different PBR shading models. So on the left-hand side here, you see like a pattern graph, which consists of image nodes and procedural math nodes that drive the input parameters to your shading model, like base color, roughness, IOR, and so on. And that graph could be just one node, like one image texture, but it could also be image texture plus some scale, or it could be arbitrarily procedural networks. And then the second piece is this PBR graph, which can express any shading model, such as the GLTF PBR1 or standard surface or the newly announced open PBR1. And the final component is this optional shader generation framework that allows you to take these graphs and turn it into shader code that you can execute in your engine. And that out of the box supports the common languages like GLSL, OSL, MDL, metal shading language, and so on. So, can I go back? Yeah, so if you look at the middle part here, the PBR graph, we have that for GLTF PBR. So in the last year, I think this was work from Dassault, from Tobias. So there is a full Material X graph for GLTF PBR, which allows you to use this material model in other tools and other downstream workflows, renderers that support Material X, or material editors that support Material X. You can open the PBR model, and you can, if you choose to, modify it or extend it. And one thing we're looking at right now is to see if we can take some of Material X's procedural capabilities and adopt those for GLTF. And apart from adding some additional flexibility in just procedural texturing in general, it would also bring some benefits with transmission size, because you can express higher resolution of patterns and textures with a smaller footprint, which will help with both transmission and potentially also rendering on low capability devices. But this will still just be for the procedural aspect, so that will plug into the GLTF PBR model and be compatible with everything we've showed here so far. But this is still early work, and one fallback you could have if your engine doesn't support interpretation of the procedurals, you can imagine baking that to a texture atlas for your texture inputs, or material inputs rather. So yeah, some work happening in the GLTF PBR working group right now on Material X. So yeah, if you're interested in this work, please come join us. So that was it from the PBR side of things. Over to interactivity.
Hello, my name is Joel Guillemard. I work for Adobe. I'm a software engineer, and for the past years I've been involved in various interactivity components. So today I'm going to present the work of the interactivity group at Khronos for bringing interactivity to GLTF. So before starting to talk about the specification, let's just recap exactly what we mean about interactivity. We have seen previously in this presentation, thanks to Dan, many very good examples in 3D commerce, and I'm going to start this presentation with a very simple example. A typical use case of interactivity on the web, for example, on a commerce website, is trying to sell you a coffee machine. How am I supposed to? So what you see here is a coffee machine, right, where there is a model button where you can change from one model to another. There is also a color button where you really want to pick the color you want for the coffee machine. And so that's really that interactivity. It's something that where your content dynamically reacts to your user input. That's something that makes your content more compelling, and that's something that makes your content brings your content to life. Next slide. To click outside. Nope. No, this one is done. Okay, here we are. So, GLTF is a file format that can describe many things, like a node, mesh, materials, and so on. But it's mostly today about representing a static scene, right? There's no internal rules that can represent the logic of your interactivity. Until now, interactivity was kind of custom made, and it was up to every application importing a GLTF to write this interactivity logic. And for this reason, your interactive content was not portable. Your interactive content was only working in your application. Okay. So what we are proposing today is a new extension that, on the left, what you see is exactly this. No, is only the GLTF as you can export today. Just a bunch of static objects, the coffee machine, the buttons, and the only thing you can do if you import this, for example, in a web viewer, you can just orbit around the camera, and that's it. as soon as you adopt this interactivity building block, you're going to be able to do exactly what I just shown in the previous slide, a fully compelling, interactive, rich experience. So this new GLTF extension, it's all about providing a blueprint for, it goes from, I would say, smart assets, just like a door, a simple door, where when you click on it, it's either open or close. Or it can be even more, it can be bigger than this, like developing little games or a full-fledged 3D commerce experience. So when we started this work of figuring out exactly how we could encode such interactivity logic in GLTF, we looked at exactly what people do these days for doing that. So I would say on the left side, it's the hardcore old school way, you write code. So on purpose, I chose an example on the bottom left corner of this slide that is pure C++, that is just a snippet of code that just says, I'm waiting the user to press the space bar. When it happens, I'm continuously rotating the object by 30 degrees every second. Okay, so it's scary and it's for a good reason, because it's for engineers, it's C++, it requires some kind of skills. And so it requires some skills, and you obviously have some portability issues. By writing this kind of code, you're not sure it's gonna run anywhere. So in the early 2000s, a new kind of programming emerged and became very popular these days until now. It's what we call visual programming. So I don't know if you have kids, but I always mention this example. For example, MIT Scratch is a very nice way for kids to learn how to program. And instead of writing line of code where you are struggling with resolving compile errors, syntax errors, you are given a set of building blocks, like Lego blocks, that you would assemble, and then you would graphically create your execution flow and so on. So it's much easier to learn. We can just target a much wider audience, not only engineers, but also technical artists or artists. There's no syntax to learn. You don't have any compilation error. It's more portable, because by design, the level of abstraction is much higher than writing raw C++ code. And it's more secure, because you can only do what you are allowed to do thanks to the atomic building blocks you are using. So as an example, in the bottom right, this is the exact same code that you see on the left in C++, but expressed in visual programming, made with the Unity visual scripting module. So you will see it's like a set of blocks that you would assemble and link together. So as I told you, visual programming is a vast topic. There are various ways of doing that. We focused on the node-based graph approach, which is a comprehensive. It offers a comprehensive set of building blocks where you can define your custom variables graphically, you can read them, you can write to them. You can also query the world state. I have a node in my Siggraph, I want to get the translation of it. And also, something super important to understand is you can you can define carefully your execution flow with a branching condition, like the if-else in regular programming. And that is the thing that is very popular these days, that you can find in such tools like Unity, called visual scripting, or Unreal in the blueprints, Omniverse with the OmniGraph, you name it. So I'm talking about this node-based graph design because it's exactly what we decided to pick for the interactivity extension for GLTF. So because this kind of approach is the good trade-off between accessibility and power. It's accessible enough not to be a niche for technical people. It embraces more people. More people are likely to adopt such a technology. It's extensible because we provide a bunch of standard building blocks. We call that the nodes but it's gonna be up to you to define your own node to really adapt this thing to your needs. And it's compatible with visual editing. So to be careful, we are only providing specification on how things could be made. But it's a solid foundation for third-party vendors or developers to build their own visual editor, respecting the rules that we set for this extension. So that's the only technical slide, don't be afraid. It's just to give you a very concrete example of what visual programming is. So this example is all about enumerating some numbers between 1 to 5, so 1, 2, 3, 4, 5, okay? And it's gonna, for every numbers, we're gonna send an event. An event is just like a message, or think a print. That's the same principle. That's gonna say odd or even depending on the value. So 1 is even, 2 is, no, 1 is odd, 2 is even, you see? I can be wrong too. So you see the various color coding on this graph. It represents the categories of this node. So you have like a node is defined by its type. For example, the first one you see on the left, the blue one, the life cycle on start, is going to be activated. So the action corresponding to it is going to be run at the very beginning. You run the experience, and you see this little black links between the nodes. Okay, you have two kinds of links. The one with an arrow tip are what we call the flow links. That's the thing that's gonna define your flow of execution. So, for example, here on the on start, I'm starting my for loop, okay, to iterate through 1 to 5, with two outputs, two flow output, loop body, the one that's gonna be executed for every value from 1 to 5. And then the flow branch is a if, think if, right? And we are doing some computation, the modulo of 2 to just figure out if it's odd or even. And depending on that, we're gonna just, at the very far right, send one event called odd or even. And at the very end, so when it's done, you see the other output socket in the for loop done. We are activating a flow delay that is just pausing the graph for a while, for 2 seconds. We're gonna then display done. So that's just a rough example of how you would design your logic. So now, what can't you do and why? We are aware that there are some limitations, just first of all because that's the first version of this extension, but also because at the core of our consideration we have these 3 keywords: security, portability, and ease of implementation. Okay, so because of security, we don't want to the people implementing this spec to create some buffer overflow or whatever by often due by dynamic allocation. So that's why there's no dynamic allocation or object instantiation. That means that basically, if you want to show some objects that are not present at the beginning of the experience, they are there, but they are just hidden. We just need to trigger the property visible. There's no network access, there's no file system access, and there's no multi-user. So that's the only very beginning of this promising extension, and because by design it's extensible, we hope that in the future it's going to be more complete. No, it's up to you.
Thank you, Gerard. And I'm not auditioning for Airplane. So we'll talk about composite scenes. This is new work that Khronos is doing. Pretty much just started this project, even though the initial idea to us came from Adobe about 1.5 years ago. They brought the idea that included interactivity and composite scenes, where you take multiple objects and include them into one scene. This is something that Dan talked about as a need for 3D commerce. And it turns out the need for 3D commerce started developing just about the same time that Adobe brought their potential solution of it. And their solution was based on their work that they originally did as part of Arrow. So those familiar with the Adobe product suites will recognize the Arrow. And if you really understand what's going on and understand Arrow, you may see the connection there. So there's several different types of composition. There's a traditional LOD, in other words, as you get closer to the object from your viewing camera, you get more detail. And that sort of drives the whole concepts of what these are doing, but there's variations on that. There's time-based. In other words, when some object appears just at the beginning of a whole sequence, particularly an animated sequence, and doesn't show up again, that's something that you can then unload right after it's done appearing, and you can save your memory. Alternatively, there's the equivalent where it doesn't appear till towards the end, and you don't want to load it up front, delaying everything else from starting. So you load it, you start everything, and then you load it as you go. There's also environment-based, and I'll get to that one in a little bit more detail. Streaming of large models or progressive loading, that's something that becomes very important when you have very large models, and we'll talk about that, particularly in a geospatial case for that coming up. Smart loading is an interesting concept, and this is where you load the material that you need to see dependent upon what the user's device and the user's network connection speed is. So if somebody's working on a desktop in a highly hardwired connection area, then you can pretty much load everything in full maximal detail starting from the beginning. But if they have a low capacity device, low capability device, like a phone on a very slow network, you don't want to load everything. You want to load only the most important stuff. So there's a detection there, communication between the client, in other words, the user's device, and the server as to what to send down the wire. And then, of course, you could always change or delete objects as seen. That's sort of the basis of room planning. So the geospatial case here is where you load in a very low resolution piece when you're far from the object. And it's divided up into hierarchical level of detail. Sometimes it's a quad tree, sometimes it's an octree, depending upon the particular application. And as you approach one section there, you load more and more details. Other pieces that either are further apart or so far away that they're not in the view frustum get dropped out of memory, or just pushed off to the side, so depending upon what sort of level of responsiveness you want in your application. Sometimes there are things that you don't want to show everybody, or you can't show everybody, or you shouldn't show everybody. For example, in this room, behind, above the ceilings, there's all sorts of HVAC and electrical plumbing lines. We in the building as a user of this room don't care, don't want to see it, probably even should not see it. But if you're doing maintenance, you need to know about that. And it's not so much in a big hotel room, but when you're getting into industrial facilities, it becomes much more of an issue, making sure that the pipes are carrying the right things, or that you're not about to open a pipe that's carrying high pressure steam. In the last case I'm going to show with pictures is the room planner. This is where you select several different objects, even potentially from different suppliers, and you integrate them into one room, either in a virtual sense like this video shows, or more common, as many apps now do, is a virtual augmented sense, where you say, okay, here's my living room, I want the couch here and the table here, and it puts those there. Advanced cases will actually learn to remove existing objects if that's something you want to remove, eliminate from the scene or from your room in the future. So the work to date, and this was started really in May and represents about 1 month of work and then additional analysis of the results. It was a demo that we did for AWE. The contractor on this one was UX3D based in Germany. They took their existing sample viewer application, which Ed showed much earlier, and extended it to support multiple scenes, multiple objects. This was done at the time. The file format was known as GLXF, and we don't talk about much about that anymore, so we're trying to go to the composition format, which is GLTF-C. But in this particular demo, you'll see the GLXF, so don't worry about that. Eventually, we want to get to the point where we include interactivity, but we don't have that for now. I have a video, but it's on the other screen, so give me a moment, please. This is the starting point of the application, the demo application. You can select the other scene. This is the 3 objects comprised here. Then to illustrate that, we manually edit the GLXF file here by adding in the additional asset and additional node, which will show up here. There's the new asset, which will be glass hurricane candle, and the additional node gets stuck into here, similar to the lamp node, just like right down there, and it ends up putting it onto the scene. And once we reload, so it's there. I know this is not really high-tech and really cool, but it was important for us to be able to establish that we could actually do this, and it worked well. This represented less than a month's worth of work, starting from scratch on the application as the extension to Sample Viewer. And this is available online if you ever want to try the results and push things out. By the way, all these slides will be available online, and most of these have embedded links in places so you can track them out. Timeline for getting them online will be shortly after Siggraph. So next up is we have work to do on the specification, defining it better, how it works in just the straight composition form. We have several different types of composition to include, and exactly which ones we start with is still yet to be determined. 3D Commerce, headed by Dan, is setting up the use cases and the priorities, and that will be pushed forward for this particular project. We'll continue on the prototype development. UX3D is supporting this work. Their job is to create the prototypes as we need to see them, work out the use cases, find out where there's holes or inconsistencies. So now I'm switching hats, and this is the tooling section. I am chair of this, and it's technically a TSG, but we don't, that's kind of too much detail. So the tooling mission is to support GLTF through outreach and education and developing and supporting the community. We create projects and execute them in a number of different situations, and in particular for these 5 bullets listed here. The biggest one here is that we've accomplished recently has been education areas. The members of the tooling group are listed over there on the left. This is mostly the people who have been very present over the last few months. The contractors listed on the right are those who have been key to developing various aspects of these projects. A number of these works have been presented at other Khronos BOFs earlier in the week. And a list of the project collections is here. This is not the list of the individual projects because it doesn't make much sense. But generally speaking, we have focused a lot on making sure that the software that we do produce is maintained, and that's seen in the Blender support and the GLTF sample viewer support. But we're also continuing to develop new projects, some of which are extensions, like the sample viewer that we used for the composition, and also the sample viewer was used as the base for the GLTF compressor. Other projects create brand new software, such as the Asset Auditor. The projects tend to fall into these 4 categories. And I built this before really testing it out on this particular display. So it leads to a little bit of awkward situations clicking here. In the content creation section, many of these projects show up in multiple categories. So you'll see the same icon reference there. We'll cover the details of these projects in a little bit. The first one there, always going around top left and clockwise, is the tutorials project. We'll go have a quick video that condenses the tutorials by a factor of 30 or so. Sample model repo, the compressor, and asset auditor, plus Blender. We continually not only just maintain the Blender plugin, but we continually advance it. The latest Blender plugin supports everything, all the extensions that Khronos has developed or ratified, except anisotropy and iridescence. Those two came out after the software was started for that latest release. They will be included in the release later this year. So the pipeline and distribution, this is the place where once the content is created, organizations need to optimize the content for better distribution, handle multiple different platforms, getting it out to the users, making sure that things work at the user end. There's a number of tools here that assist in that category. Going across the top again, the model repo, KTX tools. These allow very detailed choices of KTX compression. They run both pipeline methods, where you can run them from the command line and just process all your entire asset library, or as the experimental side, more for the Gltf compressor, which is the next line. I'm sorry, that's scene composition. A big item today that we were talking about this week is Khronos has released an RFP for Gltf on iOS. This is to support the display of Gltf models on iOS using both virtual mode, in other words, straight on the screen, and also in augmented mode where you use the device's camera. So the RFP is available. It's a public RFP. It's a relatively small project. We're looking for lots of submissions on that RFP. The deadlines for submission is later this month. Blender support, always supporting Blender. Metadata, especially for commerce cases, allows you to connect up what is displayed to the user back to information on the screen, or carries, let's say, non-modeled information such as packing sizes, finished size that's not necessarily apparent from the model, extensions or things like that. More compressor, sample viewer, and asset auditor. Education, again, a lot of the things, the tutorials show up here again. And the new one, the new icon, new image on here is the ecosystem, or also Project Explorer. This was released last week. It is the web version of the Project Explorer, which runs under GitHub. This is a much easier one to use. It makes it easier for people to add in new models or new references to do that. And we'll take a look at that in more detail a little bit. Not? Oh. The last category is the futures. These are things primarily needed by Khronos, but sometimes also working for the futures of the community. Composition is the big one here. But we're also looking at metadata advances and starting to categorize metadata in a manner that can be easily shared amongst different contractors, so providing a specification for that. So I want to run the tutorial video. These are videos available on YouTube. And this is a very shortened version, a shortened Reader Digest version of the videos. There are 5 videos. The first 2 are essentially the same ones, but with different lengths depending upon your application. Then we go through 3 extensions, Clear Code here. And all these use Blender as an example, and they show you how to create that extension, how to use that extension within Blender. Transmission. And there's also, with each video, a little bit of an education portion, exactly why you would want to use that particular extension or that effect. And of course, how it looks before and after and multiple points along the path, from initial version where you just have the model to the final version where you're using all the feature of the video. And finally, the volume extension, which Ed referenced in the olive dish. And this has a lot more education component to it. And must point out that these models were, for the most part, all done by Eric from Wayfair. Thank you, Eric. Except for Suzanne. And there's, during the video, it's not just this quickly catch it as it goes by. This is running 2 to 4 times faster than the video, and there is narration that goes with the explanations here. The video projects are continuing. We have a new set of videos coming out, or actually being produced for 3D Commerce. They will involve not quite so much technical detail of how you do things, but of more of the issues involved with creating, dealing with 3D models in commerce. And there'll be additional sets of technical videos coming out for the new extensions and some other technical topics. So we have, Khronos had the GLTF sample model repo that has been revised and upgraded. It's now called Sample Assets. And this is the homepage. It's all on GitHub, meaning everything here is public. We did a thorough license categorization of this so that clearly identified the licenses involved with each model. For the most part, these are all CC BY. Occasionally, they are CC 0, which also means public domain. They include a lot more means for easily accessing the model, so you don't have to download the model to show it. All these models have links in them directly to show them in Sample Viewer. Let's see, we talked about the RFP. If anybody has any questions on the RFP, come see me, myself or anytime, and we'll have contact information. It is available. Go to khronos.org, and it's under developers. Yes. Sometimes you get too lost in the details. RFP means request for proposal. So it's to ask people to write proposals for how they would solve this problem within the schedule and the budget listed here. Project Explorer, here's the quick version, but this is now on the web. It's ecosystem, ecosystem.khronos.org. You can add in your own projects here, anything that contributes to the general knowledge of GLTF or how it's used, or perhaps even commercial projects or open source projects are all equally welcome. The add project is up in the top right, and once a project is in here, you can update it. All this is curated, so just because you submit or add an update to it is not going to immediately appear on the website. So we're not worried about spam at the moment. And we talked about all these. So this is a text version of the future's work coming up. Composition is very high on that list, and so are the tutorials and other videos. And always, as indicated many times, support for Blender. So if we have Blender users out here, know that you will always be kept within 6 months or so of the current and most latest releases of whatever's in GLTF. That's my contact, in case anybody needs it. And now we go to the Q&A. Thank you. Okay, if you have any questions, please use the mic on the floor so we can pick it up. It's right over here.
Thanks so far. A question about interactions. So it's great that they're inside of the GLTF and everything, but maybe I want to, depending on the situation, build my own GUI like on a web page. So do you have a proposal, or is there some guide plan for engines how to implement an interface to query what interactions are possible and to make it possible to have external buttons or something to trigger them?
Yeah, so you can define custom events. It's defined by name. So you need to make sure that you don't, there's no name clashing. So that could be your company name slash the ID you want for the event. And you can both receive from the graph or send from the graph. So every event can store some payload. So again, it's GLTF, so it's all about JSON. And so that's a nice mechanism to bridge the graph with the web page. Now the thing is, I didn't mention here because it was a shortened version. Is the example I just showed was just a simple for loop that was just printing in the. Or it was most of the time if you want to deal with interaction, you want to address the scene graph, getting the position of a particular node and so on. And so how do we solve this issue is basically GLTF being a JSON, it's a tree, it's a data object model that you can address with a JSON path. So that's why also this extension relies on the ratification of another GLTF extension, the KHR animation path that is well, I will not go into detail on this one, but basically it's something where if you want to get a translation, I would say, of the node number 7, because in GLTF, every object is an array, and then you identify an object by its index. That would be something like /node/6/translation. Because if it happens, you open this GLTF inside a code editor, you will notice that all the nodes are stored inside a node entry in the JSON. And so it's going to be up to every runtime that has its own game engine, I would say, that may not share this organization of the scene graph, to provide some adapter to map that to your own data structure.
Okay,
Maybe
thank you.
I went beyond the question.
I have a follow-up to the same question. So the flow graphs, the nodes that are used in the flow graphs, are they part of the standard, the extension? Are they so let's say you have a for loop or an if loop. Are they?
Yeah. All the things that you could expect from I would basic flow. So if we talk C or procedural programming, for loop, while. We don't say if, because we try to reuse the same convention used in Unreal and all these tools that say a branch. So for example, a branch, you have one input value socket that is the Boolean, the condition that could be that could come from a previous node, and you have two outputs when it's true and when it's false. So you can, by doing that, you can do something you would do by doing a if something else. And there are various ways. I mean, everything you may find something missing just because we don't want to bring too many atomic blocks at once. And our mantra, I would say, with each, we won't define in the standard a block that you could implement yourself by reusing more atomic components.
Thank you.
My name is Johannes Beer. I worked on a couple of original proposals I had. We worked on this extension proposal like 3-4 years ago, and the idea was to compose extension, and we included the composability directly into Gltf and not add yet another format. So with the GLC file that you have right now to do composes, you have a different format. And the links to other assets is not in Gltf or GLB directly.
I didn't quite catch the question. Is it? Are you wondering, are the leaf nodes forced to be GLTF?
No. Why did you create yet another format and did not use GLB or GLTF for the links? You could add. What we proposed is that you add it directly in the node graph inside of a GLB or GLTF, and that would be much more efficient. So if you have large composition, for example, you could use a binary compression of GLB, and with the external file, you cannot use the benefits of ASCII and binary compression.
We needed to handle the situation where the resources could come from multiple different locations. And
yeah, but also with links inside of a GLB, you could, or from a GLTF, links to.
In addition to the GLTF-C, which I talked about, there will be a GLTF-B, so a binary version, which will support rolling everything into one file, much like GLB does currently.
Okay, so it gets even more complicated. Now you need 4 variants.
No, at that point, though, we are not, this concept has been decided as a concept. We haven't even started on how to write that up as a specification.
I might, it works. Okay, I might maybe add to this. So idea for GLTF-C actually to open. Does it work? Oh, okay, sorry. Yeah. So idea actually is bring even more flexibility. GLTF unfortunately doesn't serve this because GLTF it's pretty much established spec, and you cannot avoid add more information into it because you have to respect the spec. GLTF-C in some sense is way more lighter and allows you to use any different resources reusage. So it's up to you how you'll share the cache or something else. So we want to keep this core for GLTF-C as lean as possible and introduce additional extensions that you can put any kind of possible combinations that you want. So we just want to open more flexibility by default.
Well, then, okay, but the argument goes in both directions. You can also say just build simple GLB or GLTF files that just contain links, and then you would have the same.
Unfortunately, that's impossible because GLTF, again, it's established. You cannot just create empty GLTF that contains only links. It will be not conformant to GLTF spec.
Yeah.
And then, again, we have GLTF-BC, right? So even I get lost. Yeah, we have the binary representation. That will be actually compatible. It will be next version for GLB. So that will be unified between GLB and composition binary representation. The more details are incoming.
Okay, good. I just look in the spec.
Thank you, Johannes. Any other questions?
Yeah, someone's coming.
Yeah, someone's coming. Great.
Hi. So kind of piggybacking off of the last question, in one of the files that you showed today, there's in the GLTF spec, there's the assets panel, or the list of assets, and those had external links in them already. I was just wondering, what is the current use of that? Because it seems like it might already provide some of this like functionality of allowing links for loading of external resources and doing scene comp in GLTF as it is now.
But that was exactly example of this new GLTF-C file, actually.
Yeah, but aren't assets also in GLTF right now?
No, the GLTF might have the reference for the buffer views or textures, but it's not like generic. You cannot embed another GLTF inside GLTF.
Okay. Okay, so just to be clear, the assets, like nodes, materials, meshes, there isn't an assets category as well in the GLTF spec as it stands now? That, yeah.
Yeah, it doesn't. That's pretty much GLTF-C. So only one requirement for GLTF-C is just listen the nodes. That's it, nothing else. That's why it's different from GLTF, because GLTF requires more information.
Okay.
Hey guys, good to see everyone. It's Patrick. I have yet another composition question, but it's just a vocab question, maybe a comment and question. So one, look, I'm a big believer in the external references. We actually had it on the roadmap about 10 years ago. We just had to cut features for 1.0. My concern is with USD doing composition in the VFX world and all that means for the layering and just that big complex world. I'm afraid there could be some confusion if GLTF also uses the term composition for this. So just any kind of insights on the rationale for the naming and if we'd be open to other naming.
Maybe I provide some and then someone else will continue. So for us, that was like a battle between, we have like many names like experience and then scene description, something like this. But then we figured out we have so much different use cases that basically the composition is the best word describing this. Because that can be just exactly the situation that will not create the new scene graph or something. Like literally you have like an asset that use like two different textures and we want to be optimal for the browser performance, for example, for effective cache. And that's exactly the file that the composition happens. That's the only one single point, but we know actually for your asset, you will get those variances. And that's how we picture the composition. But it's my technical point of view. I'll pass over to Leonard, if you want to add.
No, the caching, also the user decision controlling what goes in there. So this is along the same lines as USD composition, but it is fundamentally different because it supports the last minute, last mile choices of what goes to compose a scene, like you would do in a room planner, especially if you are a generic room planner which can pull assets from multiple different vendors. Now, your comment about the name composition, I think it's taken. I'm not sure how well we can, what other suitable terms there might be out there. If somebody has a suggestion that seems really great, we'd love to hear it. But really soon we're going to have to start locking things in.
Got it. Okay, so I hear maybe it's a name in progress, and we'd be open to input from the community. Is that what I'm hearing?
We kind of decided, but if you have strong opinions, probably we can decide something else.
So just my concern is, as we work for more USD, GLTF interoperability and collaboration, that if the USD community hears that GLTF is adding composition, that immediate reaction that they would have would probably not be positive.
That's why we call it GLTF composition. It's not just composition.
Okay. All right. Well, I'll try to help facilitate some alternative names. Thanks,
Thank you, Patrick.
Thank you, Patrick.
Just call it a bunch of stuff.
Yeah, you're a best.
Would that be BOS? In which case, we might as well call it BOSS and just call it the BOSS format.
Any more questions? Oh, here we go.
So continuing this talk on GLTF-C, I'm more interested on this GLTF-B that we're bringing up. How is that generally supposed to be working? Are those references supposed to be baked in? How is that working with LODs? Yada, yada, yada.
Yeah, okay, so we probably we cannot provide much details, but in general idea is we have find some flows in GLB format that we want to fix. And it's no easy way because it's out of wild, so many GLBs. And we kind of thought that's probably a great idea actually to bring those two together. In this case, that will be unified loader, a lot of runtime, nice things. And this format will basically support new GLB with those tweaks and then GLTF-C as well in binary form. That's pretty much it, what I can say today.
Cool, thank you.
And that will not prevent external links, particularly when you need it to make a composited scene work. So, last chance for questions.
Anyone else?
So, conclude this session. The next session is for Vulcan, and it starts in about 30 minutes at 10 after 3. You're welcome to stay for that. You're also welcome to come and see the Roddenberry collection presentation by Otoy, which we'll talk about ITMF and GLTF and how they put everything together to make that work. That will be in room 513, so you have to trek back to the West Hall. And concluding here, starting at 6 p.m. tonight, is the Khronos Network reception, sponsored by Lunargy and Cesium. Oh, we have a new sponsor, Epic. Also. Oh, and of course there is food because it runs 6 to 8 or something like that. 9. So there is food. There'll be lots of talk. Come meet. You can directly talk to the people responsible for working on GLTF, Vulcan, Anari, OpenXR.
Yes, that's beer.
3D Commerce. Talk to Neil. Any last questions?
Thank you, everybody.
Okay.
Thank you.
Thank you for your attendance.
Apologize for that interesting technical interruption, kind of a blast from the past. It used to be that every meeting started out with 15 minutes of that, but I haven't seen it happen for so long I'd forgotten, so apologies. So are we starting the clock now? Okay. So, hi. My name's Tom Olson. I work for ARM. I'm chair of the Vulcan Working Group. Today's talk, I'm the kickoff talk of our 3 hours of Vulcan sessions. I'm going to start with a very quick level set on Vulcan. I'm going to spend half my time talking about what's new in Vulcan, various topics, particularly over the past year. And then I'm going to spend the rest of my time talking about what's next for Vulcan. So if you didn't know, in which case, what are you doing here? But whatever. So Vulcan is an API for graphics and compute on GPUs. It's based on OpenGL and OpenGLES, distantly descended, and it's cross-platform. Our goal is to make it available everywhere. Today it supports devices ranging from embedded and mobile up to desktops and servers with a single API. Vulkan prioritizes performance over almost everything else, certainly including ease of use. It does that because that's what its core constituency, AAA game developers, asked for. And their needs were primary in the design. A result of this philosophy is that Vulkan makes the programmer responsible for a ton of stuff that the API used to do for you in the old days. That includes object and memory management, synchronization, thread management, and even error checking. It demands a lot of the programmer, but it gives you in return the opportunity, though not a guarantee, of the best possible performance. Since launch in 2016, Vulkan has been widely adopted. There were implementations available from all of the mainstream GPU vendors except Apple. At the platform, they are a mainstream GPU vendor. At the platform level, it's available on Windows, Linux, Android, several game platforms, including Switch and Steambox. And although it is not officially supported on Apple, you can write Vulkan applications that run on Apple using the Molten VK shim layer. And finally, of course, tons of middleware. All the big game engines have Vulkan paths. Vulkan is used for all sorts of performance-sensitive applications, games, obviously, both desktop and mobile, but it's also used in applications as diverse as video editing and effects, various kinds of artist tools, real-time event visualization and control, and scientific visualization. Basically, any graphics application that has a real-time element and/or needs to make maximally efficient use of CPU and GPU and/or needs to run cross-platform can potentially benefit from using Vulkan. Historically, we started thinking about a successor to Vulkan, to OpenGL in 2012, but we didn't really start working on it seriously until 2014. We announced that effort here, kind of, at Siggraph 2014, and then shipped version 1.0 at the beginning of 2016. It succeeded beyond our wildest dreams, and we've been working like crazy ever since to keep up. Our methodology is we develop all new functionality as extensions, and when the time comes to release a new core spec, we promote the extensions that we agree are appropriate into that. And we've done that every 2 years since 2016. In 2022, along with Vulkan 1.3, we also introduced a profile system and the beginnings of a formal roadmap. That activity is now central to how we plan to move forward, so I'll say more about it at the end of my talk. So enough history. What's new? As I said, Vulkan is not supported on Apple, but it has been available on Apple platforms for quite a while. You use it by linking your application with the Molten VK library from Brenwell Group, which translates your Vulkan calls into Metal. What's new this year is that Molten VK is now caught up to Vulkan 1.2, only one version behind. It's still a subset, so it's not a conformant implementation, but it's a very well-defined and well-tested subset. It's relatively easy, using tools provided in the SDK, to write applications which stay within that subset and will run fine on Mac. The performance of the Molten VK shim library is also extraordinarily good. And as a result, tons of apps are using it, including big commercially important applications like Autodesk Fusion 360, Dota 2 in the game space, and a ton of other games, and a lot of very interesting middleware. In the Android space, I don't have current numbers. These are from January. But in January, Vulcan was on 85% of active devices visiting the Play Store. I would guess that it's above 90% now, based on the curve, which, as you can see, is pretty linear. We're approaching the point where, in my view, maintaining a separate path for non-Vulcan devices is beginning to be a questionable value proposition. So that's exciting. Functionality. As usual, kind of the bread and butter of working in the Khronos, in the Vulcan working group, is adding new features to the API through extension. This is what we've done in the past year. I tried to categorize them in terms of the rough area of functionality, but I caution that these are my categories. If I say something's experimental, there might be other people in the working group who disagree with me, but this is the best I can do. I'm not going to obviously try to talk about all of these, but I want to highlight 3 of the subgroups within this space. First of all, Vulcan Video. This was originally released more than a year ago as a set of 7 provisional extensions. Provisional meaning they're not final and you aren't supposed to put them in production code. The decode side of the stack has now gone final and been released, and it's starting to see serious adoption. It's used in FFmpeg, the latest version, and therefore it's being used in some of the applications that use it, such as the MPV media player. There's work ongoing to use it in GStreamer, although that's still in pull requests. Several Mesa drivers, including ANV and RADV, are close to having shipping implementations. And the TSG is now working, now focusing on getting the encode side together and on adding more codecs like VP9. Tile-based optimizations. So back in OpenGLES, we had a number of extensions that exposed the ability of tile-based GPUs to read from the frame buffer in a fragment shader and see values written by previous fragment shader invocations at the same pixel without generating a ton of memory traffic, or any indeed, and without causing huge pipeline bubbles. This is very useful for things like deferred shading. Vulcan had a subpass mechanism, subpass dependency mechanism, which was supposed to give you the same functionality, but it turned out to be hard to use. Developers didn't like it and found it just generally awkward. So a year ago, we released an extension called Rasterization Order Attachment Access, which gives you the equivalent of GLES frame buffer fetch. It's basically comparable functionality, but significantly easier to use if you're willing to have your code actually admit that that's what it's trying to do. A problem with that extension is that it built on subpasses, which meant that you could not use it with dynamic rendering, which is our latest preferred formulation for writing render loops. So this year, we've released a new extension. Whoops, sorry. How do I back up? There we go. We have a new extension, Shader Tile Image. It's basically the same functionality, but it works with dynamic rendering. So that means that when this is fully adopted, which will be a while, I don't believe it's shipping anywhere yet, but when it is available, you'll be able to move to dynamic rendering completely and get rid of subpass dependencies and multiple subpasses entirely. At the same time, you'll still get the memory bandwidth benefits on tiled architectures. Finally, one of Vulcan developers' least favorite experiences, Siggraph, you have to have an explosion somewhere, is getting device lost, which typically means the GPU hit a memory fault and the driver is now dead, and you can no longer talk to it. These errors are very hard to debug because state is completely lost. You have basically no visibility into what happened. A few years ago, we set out to create a family of extensions to help with this problem. That was a special effort led by Ralph Potter of Samsung. We've now released 2 extensions that we hope will help from that effort. EXT device fault lets you, after a device lost, you can now talk to the driver a little bit. You can ask it what went wrong. What you get back will be implementation dependent, but it might be something like, I tried to do a storage buffer write at this address and I died. So once you have that, well, you know more than you did. And if device address binding report is also supported, that gives you tools for tracking how regions of address space are bound to Vulcan objects. So you might be able to find out that the address that device fault told you you faulted on was bound to a particular buffer object, but that buffer object had been freed, in which case you're doing a classic access after deletion. No wonder you got in trouble. That's a best case, but these are tools that we hope will help. We have other things in mind. We're working on a progress marker type extension, which you may be familiar with. We don't have those yet. These extensions are, I believe, also not supported anywhere yet, but support is coming. Our DevRel effort is led by Marty Johnson, who used to run DevRel at AMD and is now doing it part-time for Vulcan, as well as helping me with working group project management. He works with Tim Lewis in Khronos' marketing department, and they, together with Steve Winston of Holochip, are leading several efforts to improve our documentation and our developer outreach. One of those projects is Vulcanize 2023. We've done full-day developer events in the past, but this was taking it to the next level. This was a 3-day conference in Munich, Germany. Open call for papers, 180 people attending. And about half of the program were presentations from outside Khronos, a mix of academia and industry. People who were there said it was terrific and that we should do it again, so we're going to try. Currently planning, I think I can say, should be February 24 in the Bay Area. All a little TBD, but that's where we are, and the call for papers should be out in a couple of weeks. Khronos provides a lot of documentation and developer information about Vulcan, but it's kind of scattered all over the place and hard to navigate. We have a project to try to bring it together, present it through a common user interface with cross-link capability and searchability. That is work in progress. We're not there yet, but there is a proof of concept prototype. Sorry, I don't have a nice QR code. I just have a URL. But if you search for it, Vulcan Documentation Project Demo, I think you'll be able to find it. We would love feedback on this. Do you think this is a good idea? We're currently saying, okay, what's next? We have a proof of concept. How do we make this complete? And we would love feedback and suggestions. Another project we'd like feedback on is procedural valid usage statements. If you used Vulcan, you know the spec is littered with blocks of text like this. These are valid usage statements that tell you all the things your app has to do to use the API correctly. If you break those rules, undefined behavior, anything can go wrong. Those rules are currently written in English, which is not good. It's a manual process. Translating it into validation layer software is a manual process, and because it's English, it may be ambiguous. So Shabazz Yousefi of Google had this idea, what about if we write these in code instead of in English? He's done, again, a proof of concept, which is, I believe, not exposed on the web, but we've been looking at it. This is not a good example because this valid usage statement is very sensible, but they get a lot worse. And sometimes code is significantly easier to read. It also, because it's code, you can imagine doing all sorts of interesting machine-readable things like auto-generation, CI checking, etc. We don't know if we're going to do this for real. We've basically come to a decision point. We're now looking for feedback. Is this something you'd like to see us put resources into? So again, there is a proposal on the Vulcan docs, which is the specification repo, and it includes the Python language and the sort of the interface to it. If you have time and interest, take a look, give us feedback. We'd love to have that. SDK, well, I'm not going to say hardly anything about the SDK because Karen runs the team that builds it, and she's going to do a better job than I would. But I did want to brag about one thing. The Windows SDK is up to 35,000 downloads a week. That just blows my mind. But Karen will cover the rest. One more thing in terms of what's new is actually not new, profiles. We introduced these at the beginning of 2022 along with Vulcan 1.3 as part of an attempt to deal with the fragmentation problem in Vulcan, or to give you tools to manage it. I talked about them then, but we haven't said anything since, and I feel like when I introduced them, I didn't really make the case for how awesome they actually are. So I'm going to try again to convince you that profiles are awesome. So hopefully you know, Vulcan defines a huge number of optional features. Extensions are optional by definition, of course, but even within a core spec or within an extension, there are features, capabilities, format features, all kinds of things which may or may not be supported. So when your app starts up, it has to query the core version, the extensions, and a huge long list of Boolean flags that tell you what features are really supported. Then you have to query numeric properties like how many render targets can I have, how big can they be, what pixel formats can I use, which ones can I render to, all kinds of things which are not, you know, the answer to those questions is not in the spec, it's in your implementation. Then your application has to decide what to do with that information. This is a huge pain, and it makes writing portable applications hard. Unfortunately, we can't fix that problem. It has to be this way. Vulcan runs on devices that will fit in a wristwatch. It runs on devices that fit in 4-card SLI AFR systems where each GPU has its own power supply and everything in between. And you cannot logically expect them all to support the same feature set. So optional functionality in core specs is just a fact of life. Fortunately, it's not quite as bad as I make it sound. It's not the case that every GPU supports a different, completely random collection of extensions and features. There are islands of coherence within markets. Mobile devices tend to have similar functionality. Things that support DX12 obviously have similar functionality. What we need is a way to make those regularities explicit. Enter profiles. So what's a profile? A profile is a formal specification of minimum capabilities across a family of conformant Vulkan implementations. It defines a subset of the space of possible implementations that supports at least a particular core version, a particular set of extensions, at least a particular set of features, etc. Implementations in that subset may support more than the profile calls for, but they may not support less and call themselves conformant to the profile. Oops. Profiles depend on a core spec, but they are not part of the spec. The spec doesn't know that profiles exist. We define tools for working with them, but they're in the SDK, not in the API. Whether a profile is supported depends only on the API version number and the extensions, features, and limits and formats exposed by the implementation, which means that you can write a new profile that describes old devices. Profiles are specified using a JSON schema. Here's a picture of one of the Android baseline profiles. So they're human readable, but they're really meant to be read by machines. This enables all kinds of interesting code gen and magic, as Karen will talk about in her presentation. Profiles are a simple idea when you think about it, and they seem kind of obvious, so it would be easy to miss how awesome they are, as I did. Here's why I think they're awesome. First, if you've got a profile that meets your needs, it's like having your own personal Vulkan core spec. It supports all the features you need. It supports all your favorite extensions. It isn't on all devices, but no core version other than 1.0 is on all devices, so that's not really a loss. As long as you code to use only the features that are required in the profile and target devices the profile covers, it's just as good as a core spec. Actually, it's better. It's better because, think about it, if we released Vulcan 1.4 today and it had all your favorite features and all your favorite extensions in it, you still couldn't use it because it wouldn't be on any devices. New core specs take time to work out into the market. Profiles describe existing stuff or potentially existing stuff. And so, you know, if there are devices out there that support the profile that you like, even if the profile has just been released, you can start using it immediately. Another way it's better is that you can start using it with little or no change to your existing code. If you want to target a new core spec, you have to go through and change all the names, remove the suffixes from the promoted extensions. But you're not going to do that, are you? Because you wouldn't be able to run on old versions of Vulcan, and you wouldn't, and besides, there are no devices out there in the market that use the new core version. So to use a new profile, all you have to do, and this is optional, is add a query saying, is this profile supported? And then if so, create me a device that supports this profile. And you've written this many lines of code, and you've got a device that has all the features enabled. And you can enable other features. We have backdoors. Again, Karen will talk about that. So that's awesome. To make it concrete, suppose you're writing an Android game. You're probably going to target devices as much as 4 years old, with a dozen GPUs from 4 different GPU vendors and a handful of handset OEMs. So you have a fragmentation problem. Now suppose Google says, here's a profile, target this, and you will be able to run on 90% of the devices that hit the Play Store in the last month. Seems like a win. And they've already done it. Android Baseline 2021, in January, 87% of devices, certainly at 90% now. Android Baseline 2022 is lower. I think it's at 80% of devices in January, but you know, progressing. So if you confine yourself to using the profile, you're not using every feature that all the devices support, but that's really hard to do. Your job will certainly be easier, and this is certainly a great place to start. 5 minutes? Okay. What's next? This is going to be 5 minutes. Let's talk about the future. When we released Vulcan 1.3, we set some ground rules for the future. We continue to release extensions as we always have, but we now have 2 different kinds of major releases. Core specs, what they've always been, are meant to be supported on all new devices going forward, and also to be backported to any device that can get a driver update that isn't at end of life. That means that core specs typically won't require new hardware features. They provide what we call quality of life enhancements, things that make the programming model better, but don't require new hardware. For example, synchronization 2, pipeline creation feedback, dynamic rendering, and no optional features in new core specs. That is, no new optional features. We can't get rid of the old ones. The other thing we'll release, the other spec we'll publish, is profiles. These describe the functionality you can expect in implementations aimed at specific market segments. And that's where you'll find requirements for new hardware features. Along with core and profile specs, we plan to maintain a formal roadmap. We're trying to accomplish 2 goals with this. One is to reduce fragmentation within a market segment. So in the short term, what we'll do is capture what's common to the market segment, but by publishing the spec, and it will be visible to GPU vendors long before it's published, we can encourage them to work toward a more coherent ecosystem and a larger common feature set. The other thing we want to do is enable ourselves to take a more coherent approach to long-term spec development. Develop specs like the crash debug, device loss debug, things that I talked about, families of specs that work coherently together to solve larger problems. In this new world, the working group is thinking about market segments. So you might ask, what market segment is your roadmap targeting? We call it immersive graphics, which I write in sneer quotes because it's so horrible. But what it means to me is, or it means to us, is mid to high-end devices, smartphone, laptop, console, desktop, which I translate to devices aimed at the consumer that support an active third-party software market for games and media applications. We could do other things. We have not currently decided to do that. So here's what we plan to deliver in the new flow. We started in January 2022 with Vulcan 1.3. That's where we adopted this new philosophy. Along with that, we released Roadmap 2022 as a profile, capturing functionality that we expect to see in immersive graphics devices starting in 2022. The criteria and the commitment we make is that every vendor within Khronos who targets the immersive graphics market has said we'll have a device, at least one device, that supports this profile in the market by the end of 2022-ish. Also, we agree that eventually these features will be universally supported in the immersive graphics market. At the start of 2024, we're now talking really about the future, we'll release the next roadmap node, Roadmap 24. This will again be a profile using the same criteria, making the same commitment, just moving everything forward 2 years in time. We don't plan to release a Vulcan 1.4 at the same time. We looked at the set of features that we could plausibly require in it that would be supportable, and it just didn't add up to a compelling product. Given the amount of work that it takes to absorb a new core version into the ecosystem, we agreed that it's better to wait. We certainly will do a Vulcan 1.4. It's a question of when we have enough pure quality of life features to justify pushing it out. Future roadmap profiles will follow on our usual 2-year cadence. I should say this is the plan, and we'll be watching closely and listening to you all for your feedback. If this turns out not to work well, we'll change it, but this is the plan. As I said, 2-year tick. I have just a little bit more to say. As part of our roadmap development process, we're trying to extend our planning horizon further into the future. We used to just finish Vulcan 1.2 and then start working on 1.3, and finish it and then start working on 1.4. Not good enough. We're trying to look as much as 5 years or more out into the future. So, Roadmap 2024, basically done and dusted. Content is frozen. I'm not going to tell you what's in it, but I will around the end of the year. So right now, as far as 24 is concerned, we're just doing packaging and support and dotting the I's and crossing the T's. But work on 2026 is well underway. We can't write Roadmap 2026 as a profile today because it's going to need extensions that we haven't written yet. So we're thinking in terms of problems that need to be solved, needs that need to be addressed. So we're defining it now in those terms. We'll use that information to guide our spec development process and the extensions that we write, prioritize the work that we do over the next year and a half, and then we'll eventually build a 2026 roadmap profile from that. I hope we'll be able to talk about our plans for Roadmap 2026 at the same time that we release the 2024 profile. Working group hasn't signed off on that yet, but that is the hope. And we're starting to sketch Roadmap 2028, which is about as far ahead as we can sanely think about. Our view that far out is hazy, but we are putting things into that bucket. Part of the reason we're doing this is that that's how far you have to go in order to have a prayer of influencing future hardware generations. And we want to be able to do that. Again, partly just to reduce fragmentation, and partly because we think we have ideas. We think we can accelerate the progress of the technology by doing that. Given that the goals of Roadmap 2026 are being defined now, this is a great time to communicate with us what you want to see from Vulcan as far out as 2028, but particularly 2026. You can do that by raising an issue at the spec repo. Don't be shy. It's just an issue. and we will look at everything. And that's probably the best way. It's long-lived, people can comment, etc. We do have a Discord channel that we monitor, and we still monitor Khronos Dev Slack if any of you are on that. And of course, you can talk to us at events like this. If you want to talk to me here or at the reception, you can't miss this shirt. I will be easy to find. I guarantee there will not be another person there wearing one like it. That's all I have. Thank you. Do we have question time or not? So, am I live? Yes. So while Neil and Karen get Karen's slides visible, if you have questions, I'm happy to take them.
Hi, I'm Alexei from Meta. I have actually 2 questions, 1 suggestion probably. So the question number 1, do you have any influence on Google with their profiles? And maybe any kind of recommendations that you can give them out for the Android devices? What exactly they need to support for profiles?
So it isn't for me to speak for Google about their process, so I'm being a little careful here. Google does, of course, talk, actually, Trevor can take that. Trevor can speak for Google if he's willing. Yeah.
Okay.
I will say Google is a very active member of the working group, and they're not shy about telling us what they think we need and vice versa.
Happy to hear your question. Context, I'm Trevor Black. I work on the Android part of Google, specifically representative for the Vulcan working group. I am somewhat responsible for the Android baseline profile, so I'm happy to hear any suggestions or comments you have.
Yeah, so basically the question is, well, we definitely want to make our life easier. And Android, to be honest, it's probably the biggest pain in the ass in general. And yeah, we just want to make sure, do you have like any ideas how you want to, design the profiles? Are you going to change like every year or whatever? I mean, we definitely care about the coverage on one sense, and then we don't want to lose the features. I mean, what's your kind of rough idea how you want to drive this?
Sure, so if I were to repeat the question, it's kind of what's our plans, how do we want to evolve this moving forward?
Yeah, how you want to evolve this and maintain.
So as said in these slides by Tom here, we released a 2021 profile and a 2022 profile. We do not intend to release a 2023 profile. If you have an idea of the cadence you'd like to see, please tell me now or afterwards. We are slightly cautious at releasing something every year because we want to establish a stable platform for everyone to develop on so that every year or every 6 months, what have you, a developer doesn't have to go, oh crap, there's more extensions and features that I need to worry about. So if you have a cadence you'd like to see us be at, we'd be happy to hear that. We will not be doing one this year. Moving forward, we're going to continue doing this. It's something we desperately believe is needed in the platform. It's why we're really pushing on this. So we have all the tools, we have all the analytics, and we're just trying to figure out at what cadence we're doing this at, and if there's any features or extensions that you think are really important for you and your platform, we'd also love that feedback, because we can then go to Tom and associated IHVs and say, hey, we know for a fact that Meta cares about this. So it's a little more open-ended than that, but does that make sense?
Yeah, absolutely. Thank you. And second one, this docs generation code actually looks pretty much awesome. I wonder if you can train ChatGPT basically to do the checks for us.
We should train ChatGPT to write the spec. That would be even better.
Oh, yeah, then we can collaborate, I think. Yeah, thank you.
Right. Do we have time for another question, or how are we? Neil, I'm depending on you to enforce. Okay.
Sure. I'm Vipul from Autodesk. This could be a little too specific of a question, so please let me know. In case of device lost extension, I suppose you're giving some context to what operation has caused the device to lose. Does that tie in with some debug marker support so I can actually figure out what buffer that I've annotated actually, caused the crash, for example?
So unfortunately, we talked when we were designing these, can we standardize the response you get. So really all you get from device fault is a query saying, give me the crash info. And you get a structure of records which have text fields in them and numeric fields. And what is in those is completely up to the vendor. You know, we just could not find a sensible way to, you know, to make it more standard than that. And of course, it's not at all intended for runtime decision making by the application. It's really just to give the developer a clue about what they should be looking at. Yeah, there are many problems with these extensions. For example, conformance testing them. You can only test this code after a device lost, which we don't have a reliable way of generating. So, although we can try. We should talk more offline.
Sure, that was valuable. Thank you.
Sure. Sorry, Karen.
Okay. So, hi everybody, I'm Karen Gavam, and I'm CEO and Engineering Director at Linergy. And so in this presentation, I'm going to be going over all the features in the SDK, not just new ones. I will be highlighting anything that's new. I did provide a QR code. I will be going over material quickly. You can follow that link and view the presentation at your leisure or at your pace. I thought I would take a moment to clarify or make it clear who is Linergy. I do get questions about this periodically. So we're not Khronos owned. We are an independent software consultancy. We are Khronos members. And we provide Vulcan ecosystem components. We've been doing it since 2015, thanks to generous sponsorship from Valve and Google that enables all the engineering work that goes behind these tools. We develop and maintain the loader, validation layers, the profiles toolset, which you'll hear more about, emulation layers that you'll find in the extension layer repository, graphics reconstruct, and more items that I haven't listed. And then we package this all up, integrated and compatible in an SDK that we deliver about every 2 months, 8 to 10 weeks apart. So I'm going to start out a little bit, just some highlights. We do surveys every year to the ecosystem users of the tools. The last one we did was in February 2023. And so a few highlights and themes that we heard from that survey. Developers are voicing needs for more development and maintenance of the shader tool chain, specifically GLSlang and DXC, DXC being the Microsoft DirectX shader compiler. It is interesting that the population of DXC users per their survey is about 20%, and 60+% of users are actually using the GLSlang workflow. GLSlang does have an HLSL front end, but only up to shader model 5. Validation layers are invaluable. I get lots of feedback about how developers could not live without the validation layers. That said, they still want us to give them more, increase the coverage of what we can actually validate while improving the performance. Error messages can really be verbose. And also, once they get error messages, it's not trivial at times for application developers to actually debug their application. What did they do wrong? There's a very strong interest in Molten VK and moving that forward more quickly. And if you're not familiar, Molten VK, Tom mentioned it, it's a Vulcan on Metal implementation. If you're interested in more detail on the survey, there is a lot more. I put a full link here. Of course, here you can't find that if you Google it, but I did give you the QR code so you could follow the link. So the Vulcan SDK, you can get it from vulcan.linergy.com. On the upper left, you'll see a SDK link. We deliver this in close coordination with the Vulcan Working Group. Once you get to our download page, you'll see that there's versions for Windows, Linux, and Mac. And for Linux, we have 2 different versions. We have a tarball that's basically a big zip of all the repositories. Everything is pre-built. And then we also do Ubuntu packages for the Ubuntu 20 and 22 currently. We keep those up to date as Ubuntu releases come out. Downloads are healthy. As Tom mentioned, his graph must have been old because we're at 38K a week about right now for the Windows SDK. The Linux SDK, the numbers you're seeing here are only for the tarball. I don't have accurate ways to get counts of the Ubuntu packages and how many are being downloaded. But I would say that from a Linux front, we're at least at about 5,000 a week. Mac SDK is really interesting. About a year ago, there was a big jump, and it's running at about 5,000 a week now. We're speculating what caused that jump. We think it's probably related to Apple's announcements, their architecture, good performance that their architecture is providing. They did gain some market share. But then maybe it could just be because we just do such a wonderful job on the Mac SDK and people are realizing it. So we're not really sure. Okay. So why use the SDK? It's created to make things easy and convenient for developers. You don't have to. You can go try to build it all yourself. Go knock yourself out. But we knock ourselves out, making it easy for the developers. The installation process is easy and fast. The pre-built tools are installed in correct system locations ready to use. We vet the content. We make sure it's compatible so that it integrates well. There's a ready-to-use version of the Vulcan configurator. There's SDK release notes and documentation. And we also have a license registry. Some corporations are very particular about what are they pulling inside the walls of their company. This license registry will detail every single open source license that's included in that SDK. So I wanted to dedicate an entire slide to the Vulcan configurator included in the SDK. This is really a helpful and valuable tool. We do give it priority at LunarG. We continue to enhance it. So it's a GUI application, and it really simplifies your experience with layer enablement and configuration. There are multiple preset configurations that you can use, and you can define your own custom ones as well. We recently added the capability for you to select your physical device. The next major release, this is kind of a preview. We're not exactly sure when this is going to come out, but we're going to add better controlling of the layers in terms of you could have multiple versions of a layer. Like what if you wanted 3 different versions of the validation layers to see what's going on? You'll be able to switch through those different versions and run your application. We'll provide full ordering control of the layers, including implicit layers. We're going to improve the UI with a tab-based redesign. And we'll have more diagnostics information. A lot of the diagnostics, it's driven by the Vulcan loader information. And there's a link here at Munich, Vulcanize 2023. Christoph Riccio, who is the author of this, did a tutorial there, and I've linked to the video and his presentation. So moving on, validation layers. That is, of course, the most popular tool in the SDK and the most essential. There are several different types of validation as well. There's GPU-assisted validation, validation that is occurring on the GPU at runtime. There's best practices, where you may not be violating usage of the spec, but we can detect behaviors that might not be the best way to use the API, and you'll get warning messages to that effect. And we have best practices for NVIDIA, ARM, Imagination, and AMD at this point. There's synchronization validation. Vulcan synchronization can be tricky to get correct in your application. This will validate whether or not you're using synchronization correctly. And there's a debug printf, which I just call, it's like a printf inside a shader. Helps you debug your shaders as well. Of course, the very, very simple and common layers of API dump. API dump, I think, was the first layer that we ever wrote, and it's just an ASCII output of all your API calls that you've made. Vulcan info shows you GPU device properties, etc. We also include 2 emulation layers currently, synchronization 2. You can use this emulation layer if you're running on hardware that doesn't support the synchronization 2. And just recently added as of May is an emulation layer for the shader object extension. So as you saw in the ecosystem survey, people say, give me more and make it faster. And those are somewhat a little bit in conflict if you're adding more things happening with every API call. But there is a lot of opportunity where we can performance tune. And we have a dedicated resource in LunarG who's actively profiling and tuning. Right now, our focus is on improving descriptor index validation performance. It's a CPU-side implementation today, and terrible performance and correctness problems for applications with lots of descriptor indices. So we're moving that into the GPU at runtime, and we're also refactoring it to better scale for 1 million plus descriptor arrays. This is a pretty complicated and lengthy refactor that's in progress. We're estimating it will be done sometime in Q3. I mentioned a couple performance improvements. We've done many that have been done in the past. I just chose a few that showed the magnitude of performance that we can achieve by some of the things we've done. For example, the fine-grained locking. We used to do big locks around everything, but now many, many smaller locks really helps with performance overall. So this graph is with Doom Eternal. Doom Eternal does a really good job of exasperating those areas that can get very bad in performance. But since 2021, we've been measuring the performance of it, running with validation layers, and we've had improvements up to around 150% in the performance. More to come. We're expecting a pretty big jump once we get the descriptor index performance tuning refactored to run in the GPU. So synchronization validation. So synchronization, we know, is identifying, access conflicts due to incorrect synchronization operations. And we can do it within a single buffer. We can do it within and between queue submissions and across multiple queues. The implementations are complete. There are some limitations, such as timeline semaphore. We have not yet implemented synchronization validation for that. It's very difficult and a very big project. We're currently focused instead on let's fix any community found issues so far with the synchronization validation, and let's tune it a bit performance-wise. It can also be pretty intense in performance, have some impacts on your application. So John Zuloff at LunarG is the architect and author of the synchronization validation. He's also really good at writing tutorials, and he's done several birds of a feather presentations in the past, and I added links to these, and I noticed that there are hundreds of views on these. They are really good tutorials if you're trying to understand the synchronization validation and the errors that you're getting and how you debug them. Even more tools in the SDK. So we added Vulc about a year ago, very popular Vulcan entry point meta-loader. We added Sasha's hardware capabilities viewer from gpuinfo.org. That's part of the SDK as of last October, with the option to auto-launch, so we can get more database entries into his database. The more, the better. We also support the Vulcan portability solution in the SDK. Portability enables consistent use of layered implementations of Vulcan functionality over Metal and other APIs. So there's support in the loader, the enumeration extension to give you portable conformant devices if you want them, and the portability subset extension. And we also have some profiles in the SDK for developing if you're trying to develop to the Vulcan portability solution. Okay, the Mac OS SDK. So something that's new is that we have a loader for iOS running. We don't have it packaged and delivered in an SDK yet. We're not exactly sure. There's quite a few things we have to think about when it comes to productizing this. But what this will enable now is you can run layers, such as the validation layers, natively on your iOS device with your application once we have this loader shipped to you. We also, in the next SDK, that as soon as I get back home after this show, we will work on getting released. It's going to now have all Mac SDK components support both Apple Silicon and Intel architectures, so no longer will you need the Rosetta emulation environment. And we have some good resources here. Again, we've written a white paper of how to develop Vulcan in an Apple environment. We did presentations at the Munich 2023 Vulcanize, and also we did a BOF here. Richard Wright did it on, again, developing in Apple environments. He did it in conjunction with Bill Hollings of Brenwell, and this QR code will take you to that presentation and a video. We actually did a video version of this that Richard's probably editing right now and will be up very soon. Graphics Reconstruct. This tool, Lunargy has invested in heavily for several years now, and it is high priority, and we continue to invest in it. There is a lot of interest from many hardware vendors in usage of this tool that have come to us asking for help to get some of the features in that they would like to have as well. So we're finding that it's very popular and quite important. It will enable you to capture Vulcan API calls in a file, in a binary format, and then you can replay them at a later time. Runs on Linux, Windows, and Android, all platforms treated with equal priority, that it works well. It's API agnostic. Today, it supports Vulcan and Direct3D 12 so far. You should take that as a hint of, yes, more APIs can come. It was architected with that purpose. Typical use cases, silicon development, we work with hardware vendors. They will use these captures to run the workflows on their simulators or do performance analysis or regression testing and bug reporting between partners. It's very common today that we will get issues on the validation layer GitHub that we cannot recreate. The user says, I can't give you my application, or I don't know how to tell you how to recreate it. We tell them, please go create a graphics reconstruct capture. They do so. Now we have a way to reproduce their issue and find out where the bug is. And Brad Grantham of Lunargy, he did a Siggraph BOF actually on Monday, and the QR code that you're seeing here will take you to his presentation, and he will have a video up of that presentation sometime next week. As well as he did a presentation focused more on the internals of graphics reconstruct at the Munich Vulcanize, and so I put a link to that here as well. All right, Vulcan profiles. So Tom, thank you for covering a lot of the information. It might make it easier for me to fly through some of this. But as Tom said, this will be essential for Roadmap 2024. So if you haven't been paying attention to profiles, it's time to do so. I believe we have a good tool set. So let me talk a little bit about how profiles could be used. So the roadmap profiles you've seen from Tom. So we have in the SDK today, the 2022 roadmap profile is included. And there will be a 2024 roadmap coming out at the end of the year, which will end up in the SDK as well. We have a concept we call platform profiles, and it's a way you can express Vulcan support on different platforms. So in the SDK, we have a desktop platform 2022, which is based really on Vulcan 1.1, and a 2023 was Vulcan 1.2, as well as we've worked closely with Android and put both of their Android baseline profiles in the SDK as well. Device profiles, like what if you want a profile for just a single device? So we worked with Sasha for his hardware capability viewer, and you can go choose a device and he'll give you a profile for it in using the JSON schema in the correct format for you. There's another term we call engine profiles, where you could express the requirements of the rendering code path. This profile would help prevent an application from requiring unavailable features on devices, such that make sure they are not using features that are not supported by the rendering code path. So in the SDK, the tool set that we include starts out with, we have the profile schema, and it's just a JSON data format. It's not rocket science. It's how you communicate the Vulcan capabilities. And there needs to be a schema for each Vulcan API revision. So with every header update, we are also updating the schemas, and we're pushing up to the Khronos group, Khronos schemas repository. there's a layer called the profiles layer, and it allows you, in essence, to downgrade your developer system to the capabilities of what's defined by the profile that you give that you're opening up. There is also a header-only C++ library for profiles so that you can use it inside of your Vulcan application. It will check to make sure the device supports the profile, and then it will do a VK device instance creation for you with all the features and extensions enabled. We saved you many, many, many lines of code by doing that. And what was added about a year ago was a JSON file generation tool where you can take multiple profiles and combine them together, and you can do a union or an intersection. So this is a tool that's only been out for about a year now. There are links in this slide set. If you grab the QR code, really good tutorials on how to use the profiles tool set. Christophe Riccio has done these tutorials. He is the author of the profiles tool set at Linergy. Okay, in the SDK, we also include the shader tool chains. So these are offline executables and API libraries for SpearV tools. If you want to validate SpearV, optimize it, the assembler, disassembler is there. If you want to go from GLSL to SpearV, you can do it with the GLSlang SpearV generator. If you want to go from HLSL to SpearV, you can use the GLSlang SpearV generator. That's up to shader model 5 plus a little bit more. And you could use the Microsoft DirectX shader compiler to go from HLS to SpearV. We include Shader C, which is basically a wrapper for GLSlang and SpearV tools for better integration into build tools. We include SpearV Cross, which will take shaders, SpearV shaders, and you can view them in HLSL Metal or GLSL. We have SpearV Reflect, which provides a C, C++ reflection API for SpearV shader bytecode. And I put a plug in here pretty quick, or at the last minute. I didn't realize this happened. This happened several years ago. Spencer Frick, who's at Linergy, created a really handy tool to visualize your SpearV and donated it to Khronos, and this is a link where you can find that visualizer. It's a very useful tool, and I'm going to make sure it's included in the SDK documentation as well. So again, the link to today's presentation, if you realize that I went faster than what you could keep up with, or if you want to get some of those links. And there will be a networking session after this Vulcan session. We will have a demo table there. Brad Grantham, who's the technical lead for Graphics Reconstruct at Linergy, he will be demonstrating Graphics Reconstruct for you and showing how you can expect an application's graphics commands using it. And then Richard Wright, our Mac OS enthusiast inside Linergy, he'll show you Vulcan validation on Apple devices, and he'll also demonstrate Vulcan Configurator for you. And with that, I think I'm all done.
One question.
Oh, question, yeah. Any questions? If there are none, that means I was really clear.
The perfect presentation.
Perfect.
So, hello everyone. In this section, my colleague Bernhard and I will talk about, not about the future of Vulkan, but about the future users of Vulkan. Teaching Vulkan is a delicate process, and mastering Vulkan requires a blend of theoretical understanding as well as a lot of hands-on experience. And we will show you how we do this in an academic context, but we also had a Vulkan course at this year's Vulkanized. So at our university, we teach 4 different computer graphic lectures. We have 2 undergraduate lectures and 2 graduate lectures. The order of the images is the same order as the courses are listed here, while the first or the middle the courses shown in the middle here let the student decide the graphics API that he wants to use by himself. The first and the last one here constrain this to in the beginning OpenGL, but now we also have this in Vulkan. So in this talk, I will mostly talk about this, or only talk about these 2 courses, one from an undergraduate perspective and one from a graduate perspective. It's important to differentiate these because you have to use different methods to teach this to a different audience for Vulkan. So how did we transition to Vulkan? We had multiple options to do this. We could have just created another new course, but here the question is, should we enforce this to every student, or should this be an optional course? And also this would maybe change the curriculum also that we teach. Or we do Vulkan teaching only in a graduate course. So the undergraduates will still use maybe OpenGL, and in the graduate courses we would switch to Vulkan or change everything to Vulkan straight away from the beginning. We kind of went with the last approach, but we choose to slowly integrate Vulkan into our teaching. So this is minimal, this is least invasive curriculum-wise and also beneficial for students. Maybe not every student wants to go the Vulkan route. But at the same time, with a lot of work, maybe we can bring this to a status where even for people that just want to taste a bit of computer graphics can also use the Vulkan route. So for the undergraduate course called Introduction to Computer Graphics, we decided to do a dual track mode where students can decide if they want to do OpenGL or Vulkan, and this exists since 2021. For the graduate course, which is called Algorithms for Real-Time Rendering, we started out with a 50-50 tactic, where some of the tasks were in OpenGL and others were in Vulkan. Mainly, for instance, the ray tracing parts of this course were done with Vulkan. And since 2022, this is only Vulkan, so the graduate course is completely shifted to Vulkan. So there are different requirements needed for a different audience, and we differentiate here with beginners and advanced. Often beginners have never seen a graphics API before and just start out with our course, and they require concrete guidance, while advanced users want to explore this a bit on their own, and we can provide them just a vague guidance. Of course, for beginners, it should not be too overwhelming, and Vulkan can be overwhelming if you throw everything at them at once. And at the same time, for advanced students, you don't want to make it too boring. And an important aspect when teaching Vulkan is the abstraction. For beginners, it's important to start out with a high abstraction and then remove parts by parts, like an onion, for instance, and remove more of the underlying ways how Vulkan functions. And for beginners, it's important to also get the concepts and the patterns and how everything is a bit connected without giving them too much low details. And for advanced users, it's important to give them useful, or at least in an academic course, it's important to give them useful abstractions so they don't waste too much time on implementing everything themselves. And the insights, of course, for an advanced student is to get low-level details on the one hand for Vulkan, but at the same time, we also want to implement state-of-the-art graphics algorithms. And we developed 2 different frameworks for this case. For the beginners, we have Vulkan Launchpad, which we also applied during the Vulkanized course, which is basically a very high-level abstraction layer. And AutoVK is more at the level of, for instance, Vulcan HPP, like the C++ headers. And yeah, so let's start out with the introductory course here. This is often the first contact with a graphics API. It's maybe not the first contact in our university with rasterization because we have some computer vision courses before, but until this point, they mostly never have used a graphics API. We have about 150 students per year, and the task, we have basically 5 assignments. And you can see the images here from left to right. It's assignment 1 till 5. They learn how to draw some simple shapes, translate them, move them around, create different pipelines, as you can see here, that do back-face culling or front-face culling and so on, and all these variations. And they do basic shading. And the final assignment is then do some texturing. The thing is, the original OpenGL assignments were around 1,200 lines of code. And as some of you know, drawing a triangle in Vulkan is already 700 lines of code. So we needed to add some help or some abstractions to that so that we can keep this in check. And maybe this is even a good thing that we have this comparison between our OpenGL course and the Vulkan implementation, because it allows us to keep track of the required work. So let's take a closer look at task 1. In this task, the goal is to open a window and do some basic setup. Basic Vulkan setup, so they need to choose the device and activate, like I display here, need to initialize the instance, create a device, pick a physical device, create a logical device for that with extensions enabled, and pick a queue, and then call the framework, and then basically the framework takes over. The framework does the rest. So this is a code snippet. So everything above the VKL init framework is done by the student using the C API of Vulkan. They create all these handles, and then they pass this to this function. And also the while loop below is also written by the students. They can use GLFV is used for creating the window and doing the input handling. And then they use these predefined functions that are often in the task description or so, and create this render loop. And the good thing is students can already see the result and get a dopamine release. And I think that's a good way of giving them a first impression of Vulkan. And then you can always strip down things and go into more detail for these sections. For instance, we can replace the init framework part or the loop itself, or we can just replace the VKL draw T-pod here and replace it with the actual command calls that they need to do. And through this way, we can keep the implementation overhead in check, and students can still understand the fundamental components and how they are connected. So a bit of statistics here. This is from 2021 and 2022. The number of Vulkan users increased in 2022 and 2023. Here we have about 15% of all students using, 15% of all registered students chose the Vulkan route. Now it's around 25%. Even though we told them that the Vulkan route or Vulkan path will probably be a bit more effort. At the same time, the grades for the Vulkan students was better. So maybe that's because we got only motivated students for the path, for the Vulkan path. Yeah, maybe that's the reason. So at the same time, Vulkan students finished all the tasks faster than the OpenGL peers. Maybe we created a too good abstraction for this, but based on the survey, they were quite happy with what they learned. Now let's go to the advanced lecture that we offer. Here the topics are quite broad, like we teach state-of-the-art algorithms for real-time rendering, like hardware deceleration, view frustum culling, physical-based shading, temporal anti-aliasing, and also real-time ray tracing. We also provide some framework that does the scene loading, window input handling, and also abstract some parts of Vulkan a bit so that it's more easier for the students to go along. So we try to provide convenience function without hiding functionality. And I just give a small example here because I don't think that we need more of these examples. So here you can create a pipeline just by using this variadic function, and you insert the shader path or where your shaders are located, and you can specify the winding order and the vertex inputs and specify some bindings. So here another statistics about the number of students over the years. The algorithms for real-time rendering is only offered every 2 years, so that's why it's missing in some of these plots. As you can see, maybe I need to clear this. The real-time rendering is the project-based lecture where students need to develop a game and choose their API independently. So even before we started doing Vulkan at our university, there were already some students trying Vulkan during these courses. And then 2021, we started to offer this Vulkan path. And as you can see, 1 year later, we doubled the number of Vulkan students. And the same with the computer graphics exercises is the same like the real-time rendering exercise is also like a project-based lecture where students can choose their API independently, and they also started to using Vulkan there. And yeah. So I just want to throw this question out there. So what is the future path that we should take when teaching Vulkan? I don't really want to get into this rabbit hole, and I'm not even sure if it's already time to ask this, but we kind of going in a classic and modern Vulkan direction split. For instance, render paths and frame paths are mostly replaced by dynamic rendering. Pipelines now kind of get in this direction of shader objects. Descriptor sets are often used as with the descriptor buffer extensions, or why use buffer attachments at all and maybe just use buffer references for bindless rendering. Maybe the interface part is a bit far-fetched because that's a personal preference, and you can always use the C header for modern features. But for me, at least, it's not really clear what we should really teach going forward. In our introductory course, we just use Vulkan 1.0 and the C headers, but maybe some of these parts could be replaced with more modern features. So, and that already concludes my part. I want to talk about want to summarize the resources that I used. Maybe some of you know the awesome lecture series that Johannes Untergutenberger did, which you can find on YouTube. On the right, you can see some of our tools that we use. For instance, the Vulkan Launchpad. If you're an educator, then maybe you can make good use of that and create your own tasks for whatever audience you want. And all of this is basically based on an educational paper by Johannes Untergutenberger, Bernhard Kerbel, and Micha Wimmer. And speaking of Bernhard Kerbel, he will be the next presenter now. So thanks all.
Oh my God, give me just 1 second, I need to fix this. Okay. Where's the mouse? Okay. So, okay. Thank you for your patience. Here we go. Okay, Lucas, thank you for very first, nice first part. So, Lucas was talking about maybe taking some different approaches and deciding between modern, classic Vulkan. And this is, again, something that we tried here with a different approach with Vulkan for Compute. Again, this was kind of a know your audience challenge. And I'm gonna describe what we did differently here for a different type of audience. So, first of all, why would you want to look into Compute? First of all, it's definitely on the educational side, because if you do compute, you have to analyze all these different capabilities that you have. You need to be aware of, if you want to do efficient compute, you need to know what kind of hardware resources your classical GPU has, how you can exploit them, so you can really take the time to drill down into the individual components and make sense of the individual parts of your hardware. And of course, once you understand them, you can use your GPU not only as something that makes pretty images, but basically as a general purpose side processor that helps your CPU with nice parallelizable tasks. And once you have enabled and unlock these features, basically both in your mind and the API, you can then start from this and really focus on the performance aspect. And compute basically gives you a few simplifications in Vulkan. It's faster to set up, it's somewhat less verbose, which we will see in a second, and you can make it even less verbose if you do a few tricks. And so with these things in mind, hopefully what's coming up now is a healthy mix of suggestions and tools and experiences, and maybe some motivation to start teaching Vulkan or integrating Vulkan as a way to teach compute. So another reason that is not on this slide here, but is definitely important, is that compute is not only valuable for doing things like number crunching or computing your machine learning outputs, but it's becoming more and more important in graphics applications as well. So we see more and more applications that make very heavy use of compute, whether it is for simulation, whether it is for neural rendering, or whether it is for actual classical rasterization, but with a twist, so-called software rasterization, which also more and more attracts attention from compute. So the first part of why one would argue that compute is easier to teach or might be a nicer way to make Vulkan approachable for students is that if you compare the stages of the graphics pipeline and the compute pipeline, it's actually pretty obvious. So you only have that one stage that you need to care about, right? So that's a very nice visualization of how this could be differentiated in terms of complexity between the two paths. But we will see a little bit more about this. So what they basically do is targeting a specific audience, which in this case, or for this type of course, is not strictly university level, but also includes an audience that is a University of Applied Science level. They basically get a set of 13 tasks, where the first 12 are explicitly guided, and they are kind of laid out in a way that is more like a puzzle structure. So this is somewhat inspired by I don't know if you're aware of these challenges, like for instance, advent of code. And you can basically translate these kind of setups also into Vulkan, right? Where if you do your synchronization correct and you do your buffer copies correct and maybe you wrote your shader correct, you get a nice little message at the end of the day, and otherwise you get some gobbledygook that makes no sense, right? And these assignments basically try to go that way and progressively up the ante until you get something that is really interesting and also visually pleasing. Because you can make things that are visually pleasing without ever setting up a graphics pipeline. It's super easy to compute something that is interesting visually, then write it out maybe to an image, and then you have, again, that dopamine release, but with even fewer lines of code. So, where can you find these exercises if you're interested in them? They have been now alpha tested by the HPG audience this year. So they are available under this link. Unfortunately, I also don't have a QR code, but I hope that this one is somewhat easy to remember. Consisting of these 12 hands-on programming exercises. So this is now in beta. If you want to do something to it, if you want to make suggestions, please feel free to reach out. And also if you have ideas for introducing new sub-projects, maybe ease the learning curve a little bit more, that would be great. So for teaching compute, what is the rationale here, what we tried to do? So we took a path here where we said we don't want to do any abstractions, and that's feasible because compute is much less verbose. So we don't have any support for the students in terms of framework. They get to write real code from the get-go that you would use in the industry as well. But we use the available tools that are there that make things more convenient, right? So there's no framework structure there, but we basically nudge them towards using tools that are meaningful. And this aligns also with the demands of the different audiences we have. Again, so this would be, for instance, the setup for making a simple device. And this is the C-style API of Vulkan. Especially for us, we said we want to be modular, we want to reach a broad audience, university or University of Applied Sciences. Especially for the latter audience, you don't want to try and teach them a C API. They will not take kindly to this, especially if C is not in their applied curriculum. So the first switch or the first takeaway for making things easier would be to don't try to teach C API, and here you have basically Vulkan HPP that comes to the rescue. So you have those C++ style extensions, including constructors, RAII wrappers, and very clear and unambiguous namespaces that help shorten your code and reduce the risk of errors. So the same code that we saw before for setting up your first device, with Vulkan HPP, if you've never seen it in action, is much more compact and is much friendlier to a student, especially if they are used to using those standard containers of the standard library, and Vulkan HPP allows them to integrate them with things they might be much more used to. So only using Vulkan HPP, let's see what we need to do in order to get your first Vulkan compute equivalent of Hello World, right? You know all the steps already. You have to go through all of these that are listed here. You have to provide your GLSL or whatever other shader code that compiles to SPIR-V. You have to make your instance, your device, set up a compute pipeline, then record a command buffer, and then make a submission, and in the end, finally synchronize. So what does this look like? Well, how fast can you do it if you use Vulkan HPP? Well, you can do this in basically the equivalent of a check card. So here, basically this includes the entire code that would be needed to write your first Hello World programming compute. And you have very clear distinguishing setup of what you need to do here. Here's the basic Vulkan setup, including the instance and the device and the queue. That's all in there without any frameworks. That's just Vulkan HPP doing its job. You have even the shader code in here for good measure. So that is the shader code, shader module, compiling the shader code, then combining it with a pipeline. And then lastly, you have the setup of your command pool, the recording, and lastly also the dispatch. And then in the very end, you have the wooden mallet of synchronization that is a device wait idle, right? So, and if you run all of this, what you get is the equivalent of a Hello World, but parallel, right? So already you have unlocked the power of your GPU. You have not printed Hello World once, but 8 times, so great. This is maybe not entirely user safe on its own. So you would, of course, have to, if you're doing this properly, make sure you have your extensions, you have validation layers enabled. So how can we make it so that this becomes actually proper? That is in making sure that we have our validation layers and our extensions enabled with the help of another tool. That is my second takeaway, and that is be brave and make sure that you can appreciate VK-config and that the students can appreciate the ease of use and the usefulness of VK-config, as we've heard before. So you can set up your individual environments with the VK-config with just a few clicks, and it can completely replace your validation layer setup. And at Vulcanized 2023, I had a nice talk with its creator who basically said, yes, that was the wider vision, or that was the greater vision for this project. And a nice little addition is that also the VK-config creator allows you to very easily enable or disable the printf functionality without ever touching your code. So another example that I want to look into, or another step for making things more compact and making it easier for students to grasp is, this is one of the tasks that you need to do as part of the exercises that I have in this suite. And that's like a decently sized wall of code. And all you're pretty much doing here is setting up your uniform buffer, right? So Vulcan HPP on its own will not help you there. What will help you there is something that also comes with the SDK, and that is the Vulcan memory allocator. So unfortunately, at this juncture, Vulcan memory allocator pretty much, as it is being maintained, only has a C-style API. There are some C++ versions out there, but I'll come back to this later. Another part, at some point during the teaching of the Vulcan Compute API to students, you will need to convey to them what it means to exploit the collaboration within the GPU, because that is the main reason of why you would want to have them switch to compute so they can make computations efficiently. And making GPU compute efficient means to exploit the collaboration that you have between the different layers of the execution hierarchy, right? So for instance, in the very simple case of a reduction, where you have your arrays of values and want to compute a sum value, a simple way to exploit the collaboration techniques that you have available on the GPU is to use the shared memory that you have on each individual compute unit inside your device. And of course, a very simple way to do this would be to first tell your students what is an atomic operation, then tell them that there's something like shared memory, and then let them try an experiment and how they could give them a basic idea how they could basically combine values first into shared memory and then into global and get some savings. And they might come up with something like this. So in theory, this should be a more efficient solution to the problem of the reduction of values to a single value. But unfortunately, as many of you can tell from looking and without thinking too much, this is wrong, right? And so this first example that many students come up with, or this first solution that many students come up with, basically brings you to the necessity of making sure that you need to tell them properly about multi-threading and memory. And this is an issue because it doesn't really come up that often, or there is hardly ever a curriculum that looks at this in depth and basically really drills down into a C++ 11 style memory model and what it implies, right? So the memory consistency is key whenever you exchange information between threads. And in theory, students know this, but the experience that they have is usually in most cases on a multi-threaded x86 architecture, which by default will be using sequentially consistent operations. So that is mostly what they are familiar with. And on the GPU, the default operations that you have for atomics would be relaxed, which is the nightmare of anybody who is coming from the CPU and doing multi-threaded programming, and this is basically the default behavior. So if you're approaching this, at some point you will have to give them a basic overview, a basic introduction on synchronization, because probably nobody else has done it before to the degree that they will need to have it. So basically making sure that they are aware of what memory fences are, how does release and acquire semantics make sense, things like out of thin air values, luckily you can skip them because the Vulcan memory model doesn't allow them, so that's already great. And what's also important to remember is that synchronization, at first might look tough, but it really isn't if you have performance to spare. So if it makes sense to maybe not prioritize performance early on when you're teaching students, you might use those very slow, very expensive synchronization primitives, and then later at some point come to the less expensive ones and introduce them gradually. And another thing that I would like to maybe incentivize or maybe give the idea is to maybe pursue synchronization as a challenge of gamification, because I think it can be put into the form of individual puzzles where you start out with a code that does something, follows some instructions, computes some results, combines them together, copies them together, and at the end you get a value that at first is wrong. But as you keep adding more and more synchronization primitives, you basically end up eventually with the correct results. And this could hopefully also be supported by something like the validation layers for synchronization or the emulation layers, as we've seen just before. But I have no clear way, or I have no clear roadmap for making this, although to me, honestly, this sounds like it would be quite fun. What are some open challenges that we have? So as I just mentioned, Vulcan has a complete C++11-like memory consistently model, both for shared and global memory. But right now, there's currently no standardized forward progress guarantees. So what does that mean? That means that many of the algorithms that you would want to do with a C++11-like memory consistency model, right now you can't do them because in addition to that, you would also need forward progress guarantee, which is not yet there, but is in the future actually of the specification, which I was basically told in some internal chats or some private chats at the last Vulcanize conference. So it is very likely that actually as some future part of the specification, we will also have forward progress guarantee. So that's great. It supports a wide range of cutting edge and vendor-specific features, but for instance, some of the popular ones that you might know, for instance from CUDA, they are not there yet or might probably never make it in there. So, but this is again, as we heard before, this is often influenced by the demand and by vendor policies. So we will see as demand rises, maybe at some point we will have also for these somewhat interesting extensions, we will have additional functionality inside Vulkan. Third point, I already mentioned this before, it would be very nice to have a solution for the Vulkan memory allocator that is compatible with Vulkan HPP, so that you don't have to break these coding paradigms and can keep the RAII behavior. There are unofficial GitHub projects that are trying to do this, but those are unofficial, and the support for future versions and for future functionality is kind of vague, so I personally don't recommend at this point integrating this into a teaching experience. And the last point is that basically with Vulkan, there's a very steep challenge of keeping up with the nice SDK environments of other compute APIs, which give you a very extensive set of features. And we know that Vulkan can do the same jobs with the same performance or even better. We saw this, for instance, at the last Vulcanize conference, where we saw the presentation of VKFFT, which, by the reports of the author, breaks even and can do basically similar, has a similar efficiency as the CU FFT libraries on the same hardware, and in some cases can even surpass it. But of course, other APIs have these functionalities and have maybe a more extensive set of these functionalities and libraries. So this is really something that is a question of, can the community find the time to add that support also to Vulkan and make contributions also to Vulkan in this kind of, in this form. And yeah, this brings me to the conclusion of my teaching experience for compute. Thank you so much for listening to me. Thank you also to the contributors to this course, anybody who's been involved in this, at TU Graz, TU Wien, and FH Salzburg. Of course, thanks to Siggraph and to the organizers who did a lovely job bringing us all together here and establishing a nice network for communications. So thank you.
Just wanted to say that thanks to me, we are behind schedule, and we were supposed to have a break now, but we're at the end of it, and we don't want to cut off the afternoon speakers or make you late for the reception. So if I was you, I would stand up right now and do some little number like, I mean, don't be shy, because otherwise you'll be sorry. So we're going into, okay. All right, so I'm sorry, my brain is completely fried, so I can't introduce you. But Henrik, pleased to meet you.
Pleased to meet you. I'll go first. But
All right.
He'll set it. Is his board version. Yeah, I think we're set up. Yeah, so we'll all run off the same laptop here, so I think we're good to go. So we have 4 speakers from Autodesk. My name is Henrik, so I'll go first. Before we start, I got to show this slide. We will be making some forward-looking statements. Plans might change, so please don't make any purchasing decisions based on what we share here today. So I'm going to start with kind of like a high-level overview where Vulcan fits into our pipeline and yeah, what type of use cases we're trying to solve here. And then I have 3 colleagues here that will go more into the details in how we specifically use Vulcan for different parts of our graphics stack and products. So you probably are somewhat familiar with Autodesk, but we make software for people who design and make things. And that's for AEC, architecture, engineering, and construction. It's for product design and manufacturing, and it's for media and entertainment. And obviously here at Siggraph, we tend to highlight a lot of the work we're doing in media and entertainment. But AEC and product design and manufacturing are our biggest industries where we have most of our products and most of our customers. And obviously all these industries have need for high performance cross-platform graphics. So across these products, we have a need for a wide range of capabilities ranging from 2D drawings, more simple types of 3D scenes, typical kind of 3D modeling workflows where you might have some simple shading just to be able to read surfaces and so on, but you typically don't have any texturing or advanced lighting or things like that might actually be in the way for your particular workflow. And then we also need to support realistic rendering where you want realistic materials, lights, shadows, reflection, glow illumination, and so on. So most of our products need to support all these different styles of graphics. So it's a pretty broad range that we need to cover with our graphic stack. So I'm specifically talking about our viewport graphics here. There's other workflows around graphics as well. But most of our main products are on a common graphic stack. Flame that Jasmine is going to talk about later is one exception. It uses a separate stack. But most of our major products are on the same graphic stack. And that's currently undergoing major modernization, I would say. So the objectives here is to make sure that we fully leverage the current generation of APIs, including, of course, Vulcan, that we are using open standards and open source as much as possible. These are just a few examples, USD and Hydra specifically, Material X, Open PBR, Open Color.io, and others. And we also have an intent to decouple our applications from the graphics stack as much as possible. Because if there's one thing we know about graphics, is that it's evolving quickly. We have new hardware capabilities, new APIs, new algorithms and techniques, and we want to be able to quickly adopt those and integrate them into our products with minimal effort. And all of this needs to be available on desktop, mobile, and web. So for desktop, that is Windows, Linux, Mac, mobile, Android, iOS, iPadOS, and web, obviously all the major browsers. So if we look at all these things, modern APIs based on open standards, decoupled architecture across all the various different platforms, that led us to the decision to base our viewport strategy around Hydra. So Hydra is this open source library. If you were here for the Anari talk earlier, it's kind of the same principle. We just started working on Hydra before the Anari project started, but the principle is the same. So it's a way to decouple how the applications describe the scene data to the graphic system from the implementation of the graphic system itself. So on the front end, we have something called a scene index, which is the way that an application, whether it's a desktop, mobile, web application, describes the scene data to Hydra. So that kind of represents the multiple different heads of a Hydra. And on the other side, you have something called a render delegate, which there are several different render delegates, many external, non-Autodesk, but there are three main ones that we are looking at internally. So the first one is Storm, which is the rasterizer that comes with a USD distribution. And that's kind of handling most of the type of graphics that I described earlier. Basically, for our viewport needs, it's probably about 99%. It's all the 2D, all the 3D, all the modeling workflows, and so on. When it comes to realistic rendering, where you typically want to have something that is ray tracing based or path tracing based, we have Aurora, which Mauricio is going to cover in a minute, which is a real-time path tracer, kind of a game-like experience, but with full global illumination, reflections, and all of that. And then we also have the Arnold renderer, which is our production renderer. So that's specifically used for like high-end VFX film type of workflows, which is a bit different. It's also not using Vulcan, so we will not talk more about that today. But both Storm and Hydra use another abstraction layer within the Hydra stack, which is called HGI, Hydra Graphics Interface. And that is the low-level API that abstracts the underlying APIs like Vulcan, Metal, DX12, and WebGPU. So what we will cover here today is Storm and Aurora and how they both use Vulcan through HGI. And again, this is something that we are incrementally rolling out for several of our main products, not including Flame, though, so keep that in mind when we go into Jasmine's talk. But This was just to kind of frame the next two speakers' talks to understand where Vulcan and Storm and Aurora fit into our stack. So with that, I'll hand over to Mauricio.
Thank you, Henrik. Okay, so as Henrik mentioned, I'm Mauricio from Autodesk. 5 years ago, quick story, I was at the WebGL BOF to talk about 3D retail space planning, and such is the technical diversity of the Khronos group that I'm here to talk about something quite different. So, and that is Vulcan Ray Tracing in Aurora, which is our open source real-time path tracer. Now, much of the work I'm showing here was done by my co-conspirator Gareth, who could not be here today. So once again, we have a safe harbor statement, so please don't bet your life savings on what I'm about to say here. Okay, so my part is going to be a series of questions, starting with what is Aurora, in case you don't know. The first thing I want to mention is that Aurora is open source and free as in beer. In fact, everything that Henrik talked, I don't know if you said it, but everything that Henrik talked about in that last slide, all the stuff that we're doing is all going out into the open, right? And it's open source, including Aurora. So besides that important thing, which we'll get to again later, it's also these things. I will touch on most of these in the next few minutes, so I'm not going to, you can use your eyeballs and read them. The last point in italics there is important. We developed Aurora for rapid design iteration, not final frame rendering. So it's more for powering an application viewport and less for rendering a movie. If you want the final frames, that's what we have Arnold for. Please go check that out. Anyway, so let me show you, or attempt to show you, Aurora in action. So this is Aurora running in our demo app with this telescope model that we made available for the open source release. So we released it in open source in November, I think it was November, and we released this model with it as well. So if you want, go take it, use it in OBJ or USD format. So the demo app sets a frame performance target, in this case to render as many samples per pixel as possible in like 33 milliseconds, and then we apply denoising. So a lower-end GPU still runs smoothly, but may have like more temporal artifacts or noise until you let it sit idle. So here I'm animating the background. I think I stopped it there. But yeah, the environment light was animated, which shows that the shading is fully dynamic. Nothing is baked. So, path tracing, all the benefits of path tracing are here. And again, as you're watching this, the goal is rapid design iteration, not final frames. A product designer in the middle of dragging a slider for a material property is more interested in responsiveness than a perfect final result. Hopefully that makes sense. We think we've struck a good balance here. So, next question. Where is Aurora used? So, Aurora is already shipping an Autodesk Inventor as the new GPU ray tracing feature. So this, on the right side there, is a screenshot of a 3D printer model in the Inventor viewport. We're also exploring the use of Aurora in other products, but I can't speak on behalf of those product teams here. Of course, since it is open source, anyone else can use it too. So all we ask is that you let us know if you do use it, because we're curious to hear about it. Before I move on, I want to show what Aurora looks like inside the Inventor UI. And so basically all you have to do is click that little ray tracing button up there to get going. You load your model, you sort of switch to this sort of realistic mode, click ray tracing, and off it goes. So that's how it works in Inventor. It's designed for engineers, not artists, so simple is good. Okay. So that list on the first slide mentioned that Aurora uses hardware ray tracing. So in case you don't know what that means, and I don't think we've covered it yet in this BOF, let's answer that question. So what is hardware ray tracing? So basically it's graphics API support for ray tracing operations. What's kind of funny is that it may or may not be backed by actual dedicated hardware. So some older GPUs support hardware ray tracing without actually having the dedicated hardware, but that's because it's hidden behind, compute shaders or something. Obviously that will be slower. Dedicated hardware is a good thing if you can get it. So it was introduced with DirectX ray tracing, or DXR, at GDC 2018. And the hardware, that dedicated hardware, I should say, from NVIDIA followed shortly after in the Turing architecture, or basically once they started calling everything RTX, that's what they were referring to. They're referring to this ray tracing hardware. So this is how Jensen of NVIDIA introduced this I think it was in Vancouver at Siggraph 2018. He sort of held up a GPU and had it reflect the light and say, oh, look, ray tracing in real time, right? So it was super corny, and I loved it. So this is now widely supported. It's not just NVIDIA, but NVIDIA, AMD, and Intel all have support for hardware ray tracing through these APIs. Even in integrated GPUs, and I really want to spend just a moment on this one, starting with this AMD Radeon 680M. So this here is a die shot of a Ryzen 6000 series processor, which has an 8-core CPU, which if you look closely, you can see the 8 cores sitting there, and a GPU that supports hardware ray tracing right there on the die, right, the little tiny little die. So this little laptop, the one I'm using right now, supports hardware ray tracing. So my point is, it's here to stay. It's not some kind of flash in the pan feature that's going to get yanked by the vendors. Oh, nobody's using this, so this is going to go away. We are stuck with it, or rather, we are the beneficiaries of hardware ray tracing now and forever, as far as I'm concerned. So just keep that in mind. So when you do have dedicated hardware, it normally handles two things: BVH traversal and triangle intersection. And then the API introduces a few new things. They are acceleration structures, ray tracing shaders, special shaders like ray generation shaders or closest hit shaders, shader binding tables, and special commands to sort of invoke all of this stuff. So you'll notice this is the Vulcan BOF, and I haven't said anything about Vulcan yet. So let's fix that right now. What about Vulcan? So Aurora development started with DXR support for Inventor on Windows, right? So we only needed it for Windows at the time, or at least that was the thinking. But as we got to this open source release, we thought, well, we want Linux support for other Autodesk products that happen to run on Linux as well. So we want cross-platform. Vulcan is the answer. So Vulcan it is. Ray tracing support in Vulcan was finalized in, I think I got this right, December 2020, which is great. And it's conceptually very similar to DirectX ray tracing, so once you know one, you kind of know the other. But it's also just as verbose. Earlier we heard, some like 700 lines to draw a triangle or something. With Vulcan, Vulcan ray tracing is also verbose, just like DirectX ray tracing. So, APIs, toolkits to sort of abstract that are great and much appreciated. So this is a blog post that I highly recommend if you want to know more about Vulcan ray tracing, and it includes this. I am not going to go through this, don't worry. Really nice diagram from the blog post, which is clearly more than I can do here. However, you are in luck. The last presentation in this BOF will be about debugging Vulcan ray tracing, so that'll be in about 30 minutes. So we are going to hear more about Vulcan ray tracing. You may ask yourself, how does Aurora support Vulcan ray tracing? So we are using, this is the key bit, we're using HDI instead of a direct integration. And the reason for this is it makes it easier for the Hydra render delegate that we have. So Aurora includes a Hydra render delegate. So Henrik just briefly mentioned what the HDI is. Let me just make sure you got this. OpenUSD includes something called Hydra. Allows you to mix and match scene data and renderers. Mix and match scene data and renderers. Hydra includes HGI, Hydra Graphics Interface. It is lowercase gi, I don't know why. So HGI is an abstraction layer over graphics backends. So OpenGL, Metal, and Vulcan. It's intended for, again, for use by Hydra render delegates. That's the real idea there. But it can be used independently, and that's kind of what we're doing. Now, I will say the HGI Vulcan support, in case you've been following it, is incomplete. It doesn't do everything yet. It's not really usable for now. But see the next talk right after me. We're going to talk a little bit more about that. So this is not the last you've heard from HGI. Now, for our purposes, for Aurora, we didn't actually need all of Vulcan. We just need enough for ray tracing, right? So what we decided to do was extend the HGI API and the Vulcan backend as it exists today to support ray tracing. So that means adding, this may seem familiar, acceleration structures, ray tracing shaders, shader binding tables, special commands. Okay, so that's what we added. Let me dig in a little bit in that. So what did we actually put in there? So these are some of the types and enumerators that we added to HGI to support ray tracing. Okay, these, if you're familiar with Vulcan ray tracing, these closely correspond to concepts in Vulcan ray tracing, then if you look at those names. So it ends up being a fairly thin wrapper, at least right now. Like Aurora, this extension is also open source, and you can find the code in this branch of our USD, Autodesk USD fork. So it's not in the OpenUSD official yet. It's relatively new. Hopefully it'll eventually get there, but that's where you can find both the additions to the HGI API and the implementation of that API in the Vulcan backend. It's sort of two things in one. One of the main challenges that you have to deal with when you address multiple graphics APIs is this one. What about shader languages? Bane of our existence. So we needed both HLSL for DXR and GLSL for Vulcan. We don't want to maintain two copies. I've been there, I've done that, it's no fun. Although you could do that, I guess. And we don't want, so what we need is shader language translation, right? We'd like the computer to do the job for us. Isn't that nice? And we heard a little bit about all the different ways that you can, all the tooling for shader language translation. But here's the catch. We need support for ray tracing concepts like, there's a trace ray function, right? And a lot of those tools haven't caught up to Vulcan ray tracing. So what to do? Slang to the rescue. So Slang is an API or a toolkit from NVIDIA. It originally started, I think, at Carnegie Mellon and as a paper, and you can go learn all about it. But their tagline, the important thing is their tagline is making it easier to work with shaders, and that's what we found. The code then in Aurora is written in Slang, which is basically HLSL with some extensions. That's basically what Slang is today. And then at runtime, the Slang transpiler will convert from GLSL, convert to GLSL, I should say, when the Vulcan backend is used. So this was basically, in my opinion, a seamless integration, except for a few minor if-defs. So you go look at the code, you'll see a few if-defs, but that we may address later. But overall, it's basically the same code for both targets, right? We aren't using the advanced language features that Slang has, but they are compelling. If you do want to know more about Slang, you should check out Falcor from NVIDIA, where this is where a lot of their path tracing research code goes, and it uses Slang extensively. So I highly recommend you check that out if you want to know more about Slang. So now I want to show you how all these pieces fit together, sort of to begin to wrap up. So we have a typical rendering API upon which we built the Hydra render delegate, which is called HD Aurora. That's the convention. And then we have the demo app that I showed you earlier, the video, is called Plasma. So we have the two implementations I mentioned, which are DirectX and HGI. And when the HGI implementation, you sort of choose one or the other at a time, right? When you choose the HGI implementation, especially if you're running on Linux, you have to, we use the HGI API, which that dashed line there, and the Vulcan backend, which has our ray tracing extension. So in the future, there might be other HGI backends that support ray tracing using that same interface. So the idea is that we want to stabilize on the interface. We may make some changes to it or whatever, and then there could be future backends. You can think of some probably off the top of your head, like DXR. We could actually just bring that DirectX implementation in there, for example. But anyway, that's for the future. Speaking of the future, what are the next steps for us? First of all, we need to address some known gaps between DXR and Vulcan and Linux and Windows. It's mostly around like windowing and interop. So we need to, one thing that we need to do, and it's kind of an interesting thing, we need to refactor our integrator to be iterative instead of recursive. So our path tracing integrator is actually recursive. But it needs to be iterative. Why? So it's a good thing that should help performance, but it also addresses an interesting limitation with some Vulcan drivers where they don't support multi-level recursion, right? Since it's not mandated by the spec. What's interesting is the same vendor supports recursion on DXR, but not on Vulcan. I don't know why. If anybody knows why, come talk to me. I'm kind of curious. But in any case, it's something we want to do anyway. We want to have it be iterative instead of recursive. And so that'll give us broader compatibility. That'll be Vulcan support on more GPUs. So that video I showed has denoising. We don't have that in the public repo yet because it's an old version and we need to update to the latest that NVIDIA provides. It's called NRD, real-time denoisers, NVIDIA real-time denoisers. The good news is Vulcan is supported by NRD, so if you want to use it in your project, go ahead. It's good for us because we're going to use that Vulcan support when we turn that back on in the public repo. So upscaling with AMD FSR is another thing that we have in mind, and Vulcan is supported there too. How convenient. And Material X support for Vulcan is not working yet. So if you have the DXR version, you can sort of use Material X materials, and it'll run it through Material X, and you get the expected result. But not yet on Vulcan, so that's something you have to fix. And then while we're in there mucking about with Material X, maybe we'll integrate Open PBR, which is, you should go look it up. It is sort of a successor to Autodesk Standard Surface and the Adobe, I think it's called Standard Material. Okay, yeah. So those things are being merged and made open, so go look it up. It's actually very cool. That was just recently announced. So we may, we probably will put that in Aurora, I guess. So yeah. Let's see here. Last but not least, as I mentioned at the very beginning, Aurora is open source. So if you want to help with any of these things, or there's something you're interested in that you don't see on this list, you can contribute. The repository link is right there, along with an email address if you want to contact us directly. So that's all from me. Now I'm going to turn it over to Vipul, who's going to tell you more about how we are having fun with Vulcan at Autodesk. Thank you.
Hi everybody, I'm Vipul Kapoor and I work as a graphics engineer for the platform team at Autodesk. I'll be talking about how we're using Vulcan as a cross-platform strategy for viewing large AEC models. That is our safe harbor statement. In this session, I'll talk about what AEC models are and how they define our technical problem statement. Also, I'll talk about what our cross-platform strategy is and how it aims to meet our rendering challenges and demands at Autodesk. After that, I'll talk about where we currently are in our process of using Vulcan on this journey and a little on how we got here. And finally, on community and collaboration. AEC stands for Architecture, Engineering, and Construction. And so the design data, so AEC models are design data for building infrastructure and construction projects. This data format is optimized for design, and it's sharing between different engineering teams and different perspectives. So this is unlike game development models where it is authored by taking some rendering optimization strategies into perspective, like LODs and vertex overdraw and stuff like that. For some perspective, they include both 3D and 2D information. The 3D information is the three-dimensional representation of what the design data is itself. And the 2D data adds more context to that 3D data, like overlaps, overlays, and blueprints. And they're again represented as line styles in different formats. So they add to the overall vertex count in the scene. Some perspective on the asset statistics, the sizes of these files can go somewhere between a couple of gigabytes to hundreds of gigabytes, depending upon the industry they come from. The polygon count can again go up to 1 billion. The mesh count can go up to a couple of millions. And what this directly translates from a technical standpoint is significantly high draw call count, immense input assembly and vertex shader pressure, and definitely VMM consumption. And this is what really translates to be our technical problem statement. Now, in the interest of time, I'll focus on what our strategy for solving this technical problem is, and less on how we might intend to solve loading of large AEC models. So we are using OpenUSD and Hydrographics interface as a cross-platform strategy, and we aim to equip OpenUSD with all the tools and techniques and solutions that we need that meet our rendering and visualization demands at Autodesk, including our technical problem statement with loading large AEC models. So we are using HGI Vulcan for Windows, Linux, and Android because, one, Vulcan gives us that cross-platform support that we need, that we have demand for. And two, we see value in leveraging greater control we get from these explicit APIs, like Vulcan, and make use of that CPU and GPU access that we get. We're using HGI Metal for Mac OS and iOS, and HGI Web GPU for web-based platforms, HGI DirectX 12 for Windows, explicit Windows platforms. Both HGI Web GPU and HGI DirectX 12 have come from internal contributions and efforts at Autodesk and are currently in the process of getting merged into OpenUSD. Now, quickly talking about where we are in this journey of using Vulcan. Well, the current implementation, like Mauricio pointed out, the current implementation of HGI Vulcan on OpenUSD is neither complete nor stable, so we at Autodesk prioritize this and have completed the HGI Vulcan feature path for USD's base material pipeline, barring some caveats. We have disabled features like instancing, blending, join direct MSA to get here because they are currently broken. However, these are our known gaps, and we intend to resolve them immediately in our upcoming iterations. We have stabilized the Vulcan backend using industry standard tools and techniques, which I'll be quickly talking about in the next coming slide. Also, the current implementation of HGI Vulcan in OpenUSD uses OpenGL for presentation due to its simplicity. However, we see value in having a Vulcan-based swap chain management, composition layer, and a presentation infrastructure for the sake of stability and performance reasons. So it is currently owned by the application, this swap chain presentation and management layer, but we hope that in future, this layer finds its way back into OpenUSD in some form. We currently have both the proposal and the implementation PRs of this effort in review to get merged into OpenUSD, and those are the links. So please feel free to go have a look at them and show some love. Leave your comments and reviews on that PR so we can follow up to progressing on this. The screenshot you're seeing to the right of that is basically a kitchen scene model rendered on OpenUSD with HGI Vulcan as a backend on Windows 10, running on an AMD CPU and an NVIDIA RTX discrete GPU. We see value in quickly progressing on Linux and Android as well. So we were able to successfully port this effort to Linux without any explicit platform changes. However, for Android, we successfully compiled all the subcomponents needed that USD has, and also addressed any challenges we had around packaging issues and the Android security implementations. So we have provided the specifics of that porting process in our proposal that is currently in review for OpenUSD's merge, and that is a link that we have provided. Also, the implementation PR for both these efforts for OpenUSD's merge will be coming in soon. That is implementation PRs for Linux and Android. And we are internally tracking them in terms of days. So once we go back from Siggraph, this is one of the first things that we'll be working towards completing and documenting and pushing out. The screenshots that you're seeing on the right has been captured on an Ubuntu 22.04 operating system running on a AMD CPU and NVIDIA RTX GPU. And the screenshot to the right of that is being captured on a Galaxy Tab S8 Plus running on an Android 13 operating system. A little bit on debugging and tools. A good part of this journey was debugging for stability, and fortunately we were not flying blind. We relied on the Vulkan debug and validation layer for correct API usage across Windows, Linux, and Android. And shout out to OpenUSD for providing the debug marker infrastructure so all our GPU resources were annotated. Now what that means is when we were using tools like RenderDoc and NVIDIA's Insight Graphics, these applications seamlessly hooked into our OpenUSD Stack Plus sandbox application and give plenty of perspective on the GPU side of things. We then relied on the debug markers that we saw on these traces for more context, and then went around resolving our GPU issues on the C++ side of things. Also, shout out to LunarG for the Vulkan device simulation layer, among other layers as well. We intend to support a wide range of devices across different platforms, and we look forward to using this layer in simplifying our testing process. Finally, a little bit on community and collaboration. I'm very happy to be here and share this progress with all of you. This is also an opportunity for me to reach out for collaboration and contribution from the open source communities we have here, both from OpenUSD and the Khronos Vulkan group. So please do take time out of your schedule and show us more love and follow up to these PRs with us. I hope we're able to continue this conversation outside of Siggraph as well. So you can reach us at the Autodesk Graphics Platform team, which is at agp@usd.com. And also, you can have OpenUSD, Hydra, and Vulkan specific implementation questions and conversations on aousd.org. Please feel free to participate there. We do keep an eye out for our queries. Thank you. This is a capture on Windows operating system running the USD stack with Hydra, Vulkan on Hydra. And this is what we have on Android of the same implementation of the other port.
Thank you.
Hi everyone, my name is Jasmin Roy. I'm a software development manager at Autodesk in the Flame team. First of all, I want to thank Tim Lewis, Marty Johnson, and Lizzie Hardson for reaching out to us and giving us this great opportunity today to talk about one of the biggest undertakings in the Flame history, which was to port Flame from legacy OpenGL to Vulcan. So super excited to be here. And I also want to send a shout out to the Flame team, which are currently looking from Montreal, and especially the 4 main contributors in this project, which are Jasmin Frenette, Samuel Falardeau, Bernie Sma, and Fabrice Lefebvre. Safe harbor statement. So I will be giving some insights at the end of this project. So obviously plans can change. Presentation agenda. So I'll be giving a quick overview of Flame. So I'm not sure everyone here knows what Flame is all about. Then I'll be talking about the project conversion strategies that we used, some technical challenges that we had and solutions, and finally the project outcome. So what is Flame? Hopefully the video is going to work. Awesome. So Flame is a timeline-based visual effects and finishing solution. It has a proprietary 3D engine that is used mainly for real-time and visual effects. It is used in commercials, TV episodics, and features. It has a very powerful machine learning engine which is used to assist artists in creative tasks. And I'm really proud to say that Flame is used around the world by high-end studios and artists that rely on its performance, its rendering quality, and its feature set. And also, although this video shows some capabilities in Flame, you need to understand that the feature set in Flame is huge. So we have very complex workflows, we have multiple components, and we connect with third parties like Substance and OpenFX. So that being said, our code base is very big, and it's been relying on legacy OpenGL for over a decade now. So you can appreciate the fact that porting a software like this to a more modern graphics API can be really challenging. So on that note, talking about challenges, so obviously a huge feature set. Flame is also supported on Linux and the Mac platform, so Intel and Apple Silicon, so we have to keep that in mind. When we started the project, we knew this was going to be a multi-year project. So obviously you have to plan accordingly. And finally, one of the biggest challenges we had was memory management. So obviously in Vulcan, we all have to, we're responsible for the memory manager, right? So this was something new for us coming from a legacy OpenGL. And so we've been tweaking our memory manager for multiple years until the very end of our project. So I won't be talking about memory management today because it would take about 500 slides, but some strategies I can talk about. Molten VK. So I can safely say that Molten VK was key to success to this project. For us, it was unacceptable to have to maintain 2 graphics API implementations at the same time, so Metal and Vulcan. So knowing that there was a solution for Vulcan on the Mac was key for us. We knew there was a risk because we weren't certain about the overhead of Molten VK. But it turned out in the end that we've seen up to 50% speed increases on the Mac. So it's safe to say that it was a great solution. And also the feature set for Molten VK, I mean, we've never had any issues with features missing whatsoever, so that was great for us. Also abstraction layers, so I'll be talking about this in a few slides. Master branch, so if you're working on multi-year projects, obviously, if you can avoid branching out, that is also very important. And finally, iterative and automation-driven approach. So what I mean by that is, thanks to the Vulcan interrupt extensions, we were able to use interrupt with OpenGL and Vulcan and convert components by components. So for example, in this processing pipeline, we could take AI tools and convert them to Vulcan and still have like mainly OpenGL modules and processing nodes inside Flame, and it would all work correctly. And the advantage of that is that we were able to take advantage of our 20,000 plus daily automation tests that we run from day one, right? So that was perfect for our project. So a first technical challenge that I can talk about today, Matchbox. So what is Matchbox? Matchbox is a feature in Flame that allows artists to create their own creative tools by writing their own shaders. The problem with Matchbox is that it's been around for a very long time, and artists have been writing legacy GLSL code, right? So we can't go from legacy GLSL to SpearV right away. So what we did is we created our own runtime shader converter, pretty simple. So basically cleans up the shader, it packages all the uniforms together, fixes the keywords, and then we're able to compile this using GLSlang to SpearV. Another technical challenge, so we all know that writing Vulcan code can be quite more difficult than OpenGL, so like we mentioned before. So what we did to streamline the whole conversion process is create an abstraction layer, which basically contain multiple tools to help developers try to accelerate the conversion process. So the advantage of doing this is that we were able to distribute the work between multiple developers throughout the years, right? So we could have developers join the team temporarily for a few months just to help out with some components. And it was easy for them to learn Vulcan, first of all, because we had this abstraction and these tools. So for example, one of these tools that we created is the shader configurator. So it basically uses shader reflection. So if you want to set a uniform by name, it was super easy. So basically the configurator will find the correct offset in the buffer to set the uniform value for you. So this really reduces the amount of lines of code you need at the end. And finally, another technical challenge we had, the fact that in this project we had so many components in Flame that we had to convert to Vulcan. So we wanted to concentrate on the more critical aspects of Flame, right? Everything that affects render quality, performance. And we didn't want to waste too much time with UI overlays and diagnostic tools. So what we did is an OpenGL translation layer. So we created this wrapper around the OpenGL API, which basically tracks the whole state. So when these tools need to render or draw, it basically translates and commits all of the state into actual Vulkan pipelines and commands. Obviously, you cannot optimize that much when you use this, but so you use these things only for the non-critical components, and that's exactly what we did, and we concentrate on a really critical stuff. So unfortunately, I cannot show any benchmarks today for so many reasons. I would have loved to. But I can safely say that we run hundreds of performance benchmarks every single day. And we've seen performance gains across the board on Linux, on Mac Intel, on Apple Silicon. And I can share with you some artist testimonials which have installed our latest version of Flame, which is Flame 2024 Update 1, which contains Vulkan. And some of our clients are seeing up to 50% faster rendering times on the Mac through Molten VK. So the project outcome, so basically performance improvements, obviously, better memory management and stability due to, and thanks to Vulkan for giving us all this control on memory management, and obviously successful Flame 2024 Update 1 in the end. So although we're seeing performance gains today with current configurations, we do believe Flame is at a performance point of inflection right now where we're seeing all of these new CPUs, GPU capabilities coming up, and we feel it's all coming together with our Flame conversion that we've done, and it's going to give our Flame artists just a better performance experience in the end. But there is so much more we need to do, and this is where I'm really excited, because with Vulkan, there's many things that we couldn't really do in the past with legacy OpenGL. So, for example, I'm talking about Vulkan subpasses, which is something we didn't really have the time to use, but definitely we can use this. Multi-threaded processing pipeline, a lot harder with legacy OpenGL. With Vulkan, I do believe it's going to be a lot easier. Multi-GPU support, And lastly, moving all of our OpenCL to CUDA and CUDA to Vulcan Compute, which would be pretty easy. So that's pretty much it. Thank you.
Yeah, we will be around later for questions. In the interest of time, we're going to turn it, that's all from Autodesk. We're going to turn it over to Hai, who's going to talk about the promised basic ray trace debugging in Vulcan. I want to know about this.
Yeah. You might be disappointed because you're too advanced. I actually started my career supporting Flame in visual effects, so it's very fitting that I follow a Flame talk. Okay. So in the interest of time, I'm going to skip a section of this. It's a wall of text anyway. You can download the slides and read it. But unfortunately, it's an important section. Hopefully, I can do like a web version of it at some point. So a little bit about me. My name is Hai. I am a graphics lead for XR at Google. I previously worked on Stadia. I contribute to DXC and Spirit Reflect. And like many of you, I love computer graphics, and thank you for being here. And I know I'm the barrier between you and beer, so I'll try to make this quick. Okay, so a bit of background about this talk. I don't remember when I started doing GPU ray tracing, but I got really bored one day, and I had a lot of free time, so I just started mooking around with the Vulcan API and Directory 12. And the first thing I wrote was I wanted to see the coordinate system to prove to myself like how ray generation would work. And I wanted to see some consistency between Vulcan and D312, and voila, it's the same thing. Anyway, I went from this to this in about 2 months, and had a lot of help along the way. And it was during my evenings and weekends and holidays, because what else you can do with your spare time but write graphics code? And so there was a lot of debugging involved, and I want to share some of the things I learned along the way to help me solve some of these problems, because debugging ray tracing is hard. Okay. So this is what we're going to talk really quickly about today. The target audience for this talk is anybody who's new to Vulcan ray tracing, and this talk primarily focuses on the API side. We'll get a little bit into debugging pixels, and the assumption is that you're somewhat familiar with the Vulcan ray tracing concepts. Thank you, Autodesk, for talking about some of that, because I wouldn't have time to. Mainly acceleration structure, shaders, and pipelines. Also going to assume that you're familiar with Vulcan descriptors and resources. And the focus of the API that we're going to look into is VKCMD trace rays. Unfortunately, we don't have time to go into things like BLAS and TLAS debugging. I do have some comments about that. Like normal graphics, we can categorize ray tracing debugging into 2 areas. The first one is debugging the API, and obviously the second one is debugging rendered pixels. And while each one of these has they're vastly different, but you kind of approach them the same way from a basic level. So you might be wondering some of these things. For what tools can I use? Show me what's happening in the API, or my app. What's the pipeline shader configuration? Can I do with my shaders? What are some useful tidbits for me to keep in mind while I'm debugging like rendered pixels? Can I examine the pixel values? Can I see how Vulcan interpreted my scene? And can I graphics printf, because when you lack all other tools, there's always printf. Okay, so this is, sorry. So first up, we'll look at what tool can I use. The unfortunate news is that RenderDoc does not support Vulcan ray tracing. So if you try to launch an app with it, you'll probably, it'll just fail. I don't know if or when their ray tracing support is coming, but there is a tool that works, and it's Insight Graphics. So the next few examples are going to use Insight, so this might look like an ad for NVIDIA Insight, but it's not. It's maybe a little bit of a tutorial. Definitely not a sponsored talk by NVIDIA that was on Sunday at the expo, if you missed that. So Insight was the only debugging tool that I found that worked for me, and hopefully after this little tutorial, it can help you if you're running into problems with Vulcan ray tracing. Okay, so this is the, this is the, The insight screenshots over the next few slides are going to be a capture of this scene. And if you're not familiar with this, this is a sphere flake by one of the OGs of computer graphics, Eric Haynes, who might be wandering around. I'm not sure if he's here. But a little bit about the scene. There is one regen shader, two mist shaders, two shaders in the hit group, and three resources that it touches, acceleration structure, output image, and buffers. Max recursion is set to 5, and there's 66,000 something odd spheres. And pretty much when I was learning ray tracing, every scene had, or every example I saw had sphere flake, so I thought I'd include it to show everybody else. Okay, so if you haven't seen Insight Graphics, here's what it looks like. It looks pretty much like any other graphics debugger. There's a bunch of different components on here. There's a timeline, events viewer, API inspector, and an object browser and a resource viewer that will pop up when you start drilling down on the details. So let's take a close look at some of these. So this is where debugging generally starts. You look at the events list or the events timeline, and you start drilling down on whatever Vulcan command you're interested in, right? So in our case, we want to look at event 17, since it's the call to VK CMD trace race. So if you don't remember what that looks like from the API side, here's what it looks like. You know, one of the beautiful things about debuggers is that it helps you consolidate a lot of the calls into a small piece of information that you can look at. But you know, for VKMD trace arrays, the things that you pass to it are the SBTs and the image and width and height, and hopefully you set the right pipeline and the right resources before that in the descriptors. So from the debugger perspective, this is what it looks like. You see the values that are passed into the parameter, you can inspect them. You know, so if you need to check your stride and size for the SBTs, here's where you can do it. Also, you can make sure that the device address isn't null for the buffers that you're passing in for the SBTs. If you're getting that dreaded black screen, it's also another place you can look, because if you have like incorrectly configured SBTs, that might be a result. Also, I believe that the validation layer should catch any egregious errors that you make with this level, at this level of the API. There are parts that it can't, and we'll talk a little bit about that. So moving into the API inspector, and this is where the good stuff is. Here we can see the pipelines, the SBTs, the descriptors for the resources, and this pipeline that we're looking at is a GLSL based pipeline, so all the entry points are main. But what's nice here is that you can see what ray tracing groups are referencing which shaders. So if you need to find, if you need to figure out if like your pipeline was misconfigured or not, this is a great place to see it. It's a little bit easier than looking through the code. I've actually gotten a few things wrong before, and Insight definitely helped me find it. So the descriptor layout foldout shows you the resources that are used by the pipeline. I do wish that it also listed the actual names of the variables that are from the shader using reflection. The other thing that I think is missing is I wish max recursion depth was also visible from here, but it's not. But it's not a big deal. You can get to it by just clicking on the pipeline. It's just a matter of convenience. So this is a HLSL version of a pipeline. Hopefully the screenshots are not too blurry. Apologize. Not a whole lot of room on these slides. So it's pretty much the same thing as the GLSL version, but you get more descriptive entry point names. It's a little bit more helpful if you're trying to track down exactly which shader you're looking for. So the thing about was when I was taking a screenshot, I actually found an error or a bug in one of our samples. And this one it was descriptor binding 12. It has combined image sampler and descriptor types. And that's actually wrong, because while you can do combined image sampler in HLSL with Vulcan, it's actually really not easy. And in our samples, we definitely don't use it. So thanks to Insight, we actually found and fixed this while we were making these slides. So diving into the first shader stage for the pipeline, the shader stage, like most of these shader stage tabs will contain like the shader module, the resources. This stage does not use any shader records, so we don't have any of that here. We'll look at that in just a bit. And you can actually view the source code to the shader by clicking on the address for the shader module, and we'll cover that a little bit too. But here's, you can click on the image view, the output image, and you can see the results of the VKCMD trace race calls. The other thing is that for the Vulcan version, there is the absence of the acceleration structure. I'm not quite sure where that is. It's definitely in the D312 mode. Next stage, and here this is the mesh shaders, and this is, since it's a really sample example, it only shows the shader modules, and we just have our two lonely mesh shaders here. And lastly, this is a hit shader group, and we finally have some access to the shader records. And the purpose of the sample the purpose of the SphereFlake sample was to actually show a resource passed via the shader records, which is the buffer for for SphereFlake. And here you can click on the address for the buffer and see the resources, or see the actual data. But for some reason in the version of Insight that I'm using, it interprets the size as 64 bytes, which is the size of the buffer address. And so you just end up seeing like the first two elements. So before moving on, one of the things that would be really useful to see in these panels, if NVIDIA is listening, is that the shader entry points. Like the first, if it's like one or two shaders, you could probably figure out which one you're looking at, but you start having like 6 or 7, a little bit harder to track. Okay. So I mentioned earlier that you can click on the shader modules and look at the source code. So when you do that, you get your choice of SphereV or GLSL. I couldn't get the HLSL cross-compile to work. That might have been my shader. Anyway, regardless of what the original source is based off, if you can look at the GLSL, you can probably figure out which shader you're looking at and maybe even spot like whatever bug you're looking for. Obviously, if it's like the wrong shader, you're going to get wrong results. So this is a pretty cool feature that I kind of found by mistake. So like other graphics debuggers, you can edit and compile and promote the shaders. Promote is the Insight lingo for rebuilding the pipeline so that you can use your newly edited and compiled shaders. And in this small example, I just changed the background color from the blue gradient that it normally has to this yellow. And this worked right away. I didn't have to relaunch my program. I just had to like move the scrubber back and forth. And so this is really useful if you are, if you want to make a quick change to your shader to test like some debugging. Okay, so let's talk a quick bit about debugging rendered pixels. So when you start debugging pixels, you've crossed over into shader territory, which means that there's going to be some math involved. And there's some basic things that you want to keep in mind when you're debugging. Turn on the validation layers, obviously, but one of the things about debugging graphics is that like when you are in the thick of it and your brain begins to get a little mushy, you might start questioning like, what coordinate system am I in? Like, is the math I'm doing correct? So it's pretty helpful to just note some of the conventions that you're using, particularly in ray tracing, since like the coordinate systems are whatever you choose. So the other thing to keep in mind if you're doing recursive ray tracing is that the only vendor that currently supports recursive ray tracing is NVIDIA. I found this out the hard way. I should have just looked at the properties. But, and also, lastly, just remember that this is real-time ray tracing. You can add like whatever debug UI you want to make it easier. Like you get instant feedback. It's kind of weird because with ray tracing we associate with having to wait for results, but we don't. It's real time. Okay. So going back to the questions, can I examine my pixel values? Yes, Insight has a graphical viewer that lets you very easily examine your pixel values. And you can also do isolate channels. So you can examine the pixel values as float or hex integer. I couldn't find a setting to change it to decimal integer, so if you're interested in that, you might have to do some quick math between hex and decimal. There's also a memory viewer, and here you can select between an address or index for the axis, but I'm not positive. I'm sure there's a good use for this, but I think for me it would have been easier if these were pixel coordinates so I can find the pixel I'm looking at a little bit easier. But you can do some quick math if you have your image dimensions and figure out like what the index is. But keep your calculator handy if you're going to do that. And lastly, if you don't have access to Insight and you can add the debug UI using IMGUI. Brad was nice enough to just take one of our samples and add a really quick UI using IMGUI to do this. It lets you lets you examine the pixel values because graphics debugging, you might want to write something fun and fancy to the frame buffer so you can debug it. So one of the things that one of the things that you might want to know is can Vulcan show me how it interpreted the scene that I handed it to while I'm ray tracing? And before we go on to that, I went to the NVIDIA talk on Sunday and I saw the pro version of Insight, and so I know this is possible in Vulcan, but it is not possible in the version of Insight that you download as a consumer. But it's unfortunate because this is really useful to have, and here's a screenshot of the D3D12 acceleration structure viewer. So this is immensely helpful if you want to debug geometry and procedurals, geometry that's the triangles or procedurals. One of the hardest things is sometimes you question if you configure your geometry correctly. And a tool like this can, if you misconfigured it, probably just end up scrambled or you might get a crash. But anyway, if you don't have a visual acceleration structure viewer, you can always graphics printf. In our case, it's ray tracing printf. And so the very, very fundamental version of this is just coloring one color for your hits and a different color for your misses. Here's a very simple shader or two simple shaders, one for closest hit and one for miss, and one of them just colors it red, and one incorrectly colors it as black. It should be red. My apologies, I'll fix that. So if you need to see some separation in the geometry with a graphics printf, then you can just do something like write out the barycentric coordinates, or you can use world hit position or object ID or primitive ID or instance ID. Those take a little bit more math because you start writing those values out, it's going to probably overload some of the values. But anyways, printf, it's there. You can if you have access, if you have your geometry data pumped in, you can always write geometry data as well. So normals, text chords, tangents, all the things that you would normally have associated with a render. So I found that it's super handy to keep just a text file of these shaders, and I can just copy them in and replace them when I'm starting to question whether like I messed up in the shader or not. It just helps me get it back to fundamentals really quick, and then it can work forward. But here's a list of ready to go printf shaders that I'd recommend. If you need to have something ready to go. And so it's also helpful sometimes to just get a second opinion if you have code that's written that is easily portable to a different API like D3D12. We had a case where this is obviously a really simple example, but the top image is Vulcan, the bottom image is D312, and we noticed that the top red cube looked a little bit off, and Brad tracked this down to like it being a bug in both the shader and the API on the Vulcan side. The shader, the bug in the shader was for both APIs, but Direct3D12 for some reason was a lot more forgiving about how it handled missing resources, or sorry, underspecified resources. So there's this entire section about debugging crashes. I'm going to skip it, but I'll just show you the slides real quick. But debugging crashes is you get to think really hard, and it's unfortunate, but that's the way it is. But again, you want to break it into two different categories. Crashes before you trace rays and crashes while you're tracing rays. There's 4 walls of text that you can read once you download the slides, and basically it's just steps on walking through the API and checking the critical fields that you would when you're trying to track down a crash. One thing I do want to say about tracking crash while you're ray tracing is that there are, I work on DXC a little bit, and while there is, generally, when you get a crash, it's probably not a compiler bug, but there is a greater than 0% chance that it might be. So if you suspect that there is a shader compiler bug, well, the best way to approach that is it's just to comment out the code and then reintroduce it until you find the source of the problem. And then file a bug on our GitHub so we can track it down and fix it. If you're going to do that, though, whatever resources that you're using, you need to read from it and then write to it either in the payload or write to it directly out to a resource. The reason why you want to do that is if you don't touch a resource, the compiler's dead code elimination will just yank it out, so you'll never see it. So keep that in mind if you're going to use the, if you think you suspect a shader bug, a shader compiler bug, but it's highly unlikely. The other thing is, if you are set up to go with NVIDIA's Aftermath, I saw some really cool demos of it on Sunday as well. It seems really helpful. Unfortunately, I haven't had the time to track it down yet, but I definitely recommend that you do if you're running into crashes. Sorry, NVIDIA, I have some feedback about Insight. If you're watching, this would be really useful, not just for me, but I think for everybody else too. And like I said, I saw the pro version on Sunday at the expo, and so I know what glorious ray tracing debugging can look like. Just a plea from the random guys on the internet who are doing ray tracing as a hobby. Okay, so that's pretty much the end of my talk. There's some folks that I want to thank for helping me get to this ray tracing journey. And here's the link to Eric's original Sphere Flake. And also, I didn't get to mention it, but Will Usher has a really awesome blog about SBTs, and there is a tool or a little toy app that he has on the web that allows you to just visualize what the SBT looks like. And also, you can insert shader records and whatnot until you can get an idea of what the Stratton size looks like. Additionally, all the sample images that we use is available on my graphics experiments GitHub. And it's just a collection of graphic samples that are done from a hobbyist point of view. And it's in Vulcan, D3D12, and Metal. And the whole point of this project is just to have fun with computer graphics. And the ray tracing portion just walks you through the entire thing from UV coordinate generation all the way to a progressive real-time photoreal-based path tracer. And that's it for me, and I think everybody probably wants to grab a cold beer.
Questions, anyone? Yes. Nobody had any questions for Vulcan? Okay. Well, the networking reception is right around the corner. You're going to go out the door and to the right, and it's around the corner. We have drinks and some sliders and pizza, and everyone's welcome to attend. So head on over.